Okay, so good morning again. I just see that students at Shevchenko National University are joining the room, and so today is an important day for Ukrainian synchrotron and neutron community because it would be our second workshop. First one was conducted last year, and we would start from the opening session, and I would like to ask Alexander Kordyuk, Luke Patthey, and Marcin Sikora have few words about from this, because you are basically together Polish Institute, Ukrainian National Academy of Science, represented by Kyiv Academic University and SOLARIS, were basically among other main initiators and main seed to create such a community. And please, Alexander, few words about.
Okay, thank you, Danylo. First, thank you for organization. And since I will speak a bit about Ukrainian synchrotron and neutron community later, therefore I just want to pass the word to Luke and Marcin, because actually the project of which we call it MAVKA now, yeah, the project of Ukrainian beamline at Solaris, which was essentially now contributed with main contribution from PSI now. So I would then pass this word to Luke and Marcin.
Good morning, everybody. Can you hear me?
Yes,
Yes,
perfect.
Okay, from my side also, I would like warmly thanks Danylo, Babich for the organizations of this workshop, and I'm very pleased to be invited to present something, and also I'm very honored to actually represent PSI in this field, and indeed we are also PSI and Switzerland very pleased being able to help and to give positive contributions to the Ukrainian society, scientific society, mainly by actually helping in providing some in-kind contributions and expertise to build actually what I think fantastic research tools you will have available hopefully in a few years from now, which is these Ukraine beamlines located at Solaris, which is actually the result of a very nice collaborations initiated by LEAPS, which is this European Liga for Synchrotron radiations and FEL radiations. And together with our colleagues from Poland in Krakow, in Solaris, and with our colleagues from Alexander in Ukraine, we are really looking forward for this project. And we would like very much then this project help you to develop your scientific interest and your research in the future, going from master students, PhD, postdoc, and research activities in Ukrainians, which we believe it's actually key issue to actually to open your society to also modern photon science. And we are very convinced that there is lots to do. And we are also, as an institute in Switzerland, will be very pleased to collaborate with everybody who are around these tables by one way or another through these beamlines, but also with exchange programs or so on. So with that, I wish a very successful day of meetings, and I hope I saw the programs, it's very rich, so I hope everybody, all the young guys will also profit very much of this meeting. So with these words, I give the words to my colleagues from Solaris. Thank you, Danylo.
Okay, so my name is Marcin Sikora. I'm a scientific director at Solaris Center in Kraków. And it's my honor to be already second time on this workshop of Ukrainian Synchrotron community. I'm really honored, and that's also kind of pledge for us to really work hard to bring you to the world of synchrotron, especially the young scientists, and also to work hard on construction of the beamline. We are very happy and especially thankful to look to really starting this, pushing, finding the first resources to build the beamline. There are other synchrotrons being interested to join us, so we are really optimistic for the moment that it's really going to happen. Also, there is a team created at Solaris who is really starting supporting. So over the last year, from the last meeting, there is really a progress. In the plans for the beamline in construction, we still struggle with some problems that maybe you will hear, but we are really optimistic. We will go and we will finish that project. But also, in addition to MAVKA, we really welcome you to Solaris because it's open facility to anybody, especially to Ukrainian scientists. And we also see a progress. We see new users over past year. Even in this workshop, there will be presentation from the research, which I'm really proud of, that the users are coming from Ukraine to Solaris to use our facility and to do very good science there. So yes, I wish you also very interesting workshop, many interesting discussion. Today I will not be presenting. There will be Ewa Partyka-Jankowska presenting the Solaris in all the offer of Solaris to scientists, but there will be also presentation from Artem Yakovlev about the MAVKA beamline and from Tomasz Sobol about PEDIX beamline, about the X-ray photoelectron spectroscopy. So I wish you also a very interesting day and many interesting discussions. Thank you.
Thank you very much for warm words to all of speakers. And yes, I want to confirm that we, in our workshop program, we have first synchrotron users at Solaris who already did research there and will present some results. So it's very huge progress, and I think we are very proud that probably partial influence on that was our first Ukrainian Synchrotron workshop, which initiated a kind of increase of interest to synchrotron research within Ukrainian academic community. And we would like to move forward with motivation and basically education of Ukrainian scientists, how to use synchrotron radiation, what kind of different techniques can be used for that, and what kind of different large-scale facility can be used. And the first talk would be in that direction and would be presented by Professor Luc Patthey from Shevchenko Institute, and he was already introduced, was at the opening. He is a main spark for initiator of the Ukrainian beamline at Solaris, and he will speak about introduction to synchrotron radiation and X-ray free electron lasers in condensed matter research.
Thank you, Danylo. So I will start to share my screen. Let me see if, oops, I think this is that one. Share, why do I, hello, I guess. So, just a minute. Do you see my screen?
Yes, that's perfect.
Good. So, thank you again for being here. I thought as the very beginnings of this workshop, I could give a light introductions to synchrotron radiations and X-ray free electron laser applying condensed matter research. Please, to my colleagues who are old folks on the field, I will actually try to make more advertisements on this kind of research rather than actually giving high levels talks. So the motivations is actually to motivate the young scientists, which is around the tables, to demonstrate actually this is actually very useful techniques to actually approach relevant problems in science. So as I will try, oops, it doesn't work. No, I think I should do it like this. Okay. Synchrotron radiation fell. This is actually light source, and we all know how important is light. Our eyes use visible light, which is emitted from the sun. Do you see my? No, I try to put my as a laser pointer. Sorry, I'm not yet set. I would use green. It doesn't work. Okay, do you see my pointer? So, hello?
Yes,
Yes, we can see.
Okay, good,
Perfect.
good. We all use our eyes as a detector to see nature, which is irradiated via the light emitted by the suns. And there is a pretty amazing stuff is if you look the wavelengths emitted of the sun, you will realize actually our detector is perfectly matched to the maximum intensity of the light emissions from the sun, which is in the visible. I guess this is a pure product of the evolutions. I'm not a biologist, I'm not in the field, but as a physicist, I would say our eyes is a perfect detector to use to work in an environment which is related with the light emitted by the sun. And the nature as well is very well adapted. We can see our wonderful nature, but the nature has been using the light as a source of energy. So we understand then actually the light is not just important to see some things, but it's also a driving force for many different processes in our surrounding. And as you may know, light is nothing else as a physicist. For physicists, an electromagnetic radiations, we call it EM, which is actually as functions of space or times. This is an oscillations of the electrical field in one directions, and perpendicular to this electrical field, you have a magnetic field oscillations, and these oscillations, these perturbations propagate at speed of light in one directions, and the electrical field and magnetic field oscillate with in phase, just rotated by 90 degrees in the direction of oscillations, and they are separated by in space by wavelengths. And in our language, any photons or any electromagnetic light can be defined by a photons, which has actually an energy related to the frequency, which is reverse of this wavelength. So we understand this is visible light, or light is electromagnetic radiations. And we are using this light daily. We already know by education, so to say, then actually these lights can be reflected like in a mirror like this. It can be refracted through a change of index of propagations, index of light, which is actually change the speed of light in the air or in the liquid, or it could be absorbed. You go with one wavelengths, and then the media absorb this length, these photons, and due to the internal process, you have different absorptions in the different wavelengths. You can also use this, if you look your small laser pointer on the CT, you can see actually spots which are related to the diffractions. And nowadays we know also then with light we can use it for making movies. So light is actually very well used and understood in the visible light in many different topics. But when we are talking about lights, we always think about visible lights. For us, Visible light is more than just visible light. It can be extended as function of the wavelengths you are using to also X-ray, which is usually a smaller wavelength than the visible light. And there is a very interesting property with these X-rays. They are actually penetrating in the materials, so we can make actually X-ray picture, and people even play with these pictures to make some kind of art. Or you can actually, because of the wavelengths is so small, then you can actually look more in detail the nature, how the structure is done, and you could, in this case, make actually X-ray diffractions on atomic structure. So the electromagnetic wavelengths actually range from the radio wave up to the gamma ray by going through the microwave, terahertz, infrared. And we see here, actually, the visible is only a very short fraction of it. We have on shorter wavelengths than visible light, we have UV and X-rays. And as you may know, then these wavelengths, which is actually related here, the visible wavelengths is in 10 to the minus 6 meters, so typically a few hundreds nanometers, when the X-rays is actually in the can go up to the angstrom levels. And if you translate these scales to the energy, you will start to have actually from the X-rays starting to the EVs to the few kilo electron volts. And if you can scale these wavelengths to different objects which surrounding us, like building, humans, cells, small objects, cells and molecules or atoms, and those objects has a given size, and you will be able to see these objects with electromagnetic light, with electromagnetic radiations, which has a wavelength which is comparable to the size of this object. And to our days, we have been very well set with radio frequency, microwave, and also to visible with laser as a good source of X-rays, but as an electromagnetic light. But there has been a gap in the X-rays regimes, and today we have developed as a physicist few equipments which are synchrotrons, as we have at SOLARIS, which actually producing X-rays like the MAVKA beamlines, which allow us to scan the photon energy to a range where we see the interest of object we will be able to see. On the top of synchrotron, you have also X-ray FEL, which is actually also available on this energy range. And on the top of the energy range, what is important, you need to have actually an information on the time scales. And as you may know, nature which surrounding us is in the order of seconds up to maybe milliseconds for this wonderful hummingbird who can actually have motions of his wing very fast. And if you have a very fast camera, you may be able to make movie out of it. But if you want to look process in nature at the size of molecules, big molecules, a little bit smaller molecules or atoms, you need also to have X-ray source which has a different timescale capability. And the synchrotron radiations is extremely good to cover timescale from a millisecond to nanoseconds, when the FEL radiations actually fill a technology gap we have for so far, which is in the pico down to the femtosecond scale. So basically with synchrotrons or with FEL, we will be able to cover space, energy range, or volumes in dimensions in the X-rays going from nanometers down to angstroms, and in time scale down to femtoseconds. And this is, we are by this way best suited to investigate nature at the atomic levels, and also to understand, for example, what's going on when a chemical reactions would take place, because these chemical reactions typically, or oscillations of atoms, occur in the femtosecond or few hundred femtosecond scale. X-ray source is actually indeed not completely new. Already, it's a well-known picture here for Röntgen, who make actually a picture of, we believe, the hand of his wife. He has actually developed an X-ray source, and he could actually demonstrate the capability of this X-ray source to penetrate in the hands of our body, and actually to see bones and to see just what is inside the body and not just the outer part. And for that, he's using X-ray source, and where we see this X-ray source develop photons going from few tens of kilo electron volts, and with actually some backgrounds and with some spikes, which is related to emission edge. I will come back to that in a later stage. But the holy grails to our days is actually to generate X-ray source, which has a high brightness and high flux, because you can realize then this X-ray source is fairly low intensity and emits X-ray in all possible directions. So it's not the best suited X-ray source if you want to approach small object of small size. So you need to develop X-ray source which actually has a high flux and high brightness, and like you have a lighthouse, you can actually have a radiations which is irradiated in one specific directions with the source size which is small, and also in a very specific energy range. That means the flux will be the number of photons per second, and the brightness will be the number of photons emitted by this source by second, and by surface unit, and by angled units, and by wavelengths units. So basically is as much as photons which can go in a small area. So you have, and with a very specific wavelength. This, to our days, the X-rays source has developed massively since the X-ray tubes, and we see the evolutions as function of the time of the brightness. You move to fixed anode tubes to rotating X-ray tubes, and then we had the first synchrotrons, which has been identified and used in the early 1970, and we developed new types of synchrotron radiation, third generation and fourth generations, and to our days we have been moving to FEL radiations, and we move to diffracted limited X-ray synchrotron source, which is actually today's very important topics. And you see how the brightness has been evaluated as function of time, not just by factor 2, but by many order of magnitudes. From the X-ray source, the order of magnitudes has been increased by 10 to more than 20 order of magnitude. And when you have this kind of tools in your hands, you can really start to investigate much more details, pictures of or movies even of objects. Like this is a small flyer where we use X-ray from synchrotron radiations. And thanks to the transparency of the X-rays, we can make tomography and look really the details of during the fly of this how the muscle move and how the behavior of this animal goes. You can also address the same questions on more technological object like chips, and then you can see actually really deep in the systems how the transistors are created in 3D geometry. So you have really deep details of your chips. So if you buy chips in a different country and you would like to see, well, do my transistors really do the transistor design is really what I ordered, then you can actually put these chips in the X-rays and make tomography, picography, and investigate this object. X-ray source actually are not new. This is actually well known in star of neutron stars. You have Crab Nebula, which is actually has been deeply studied by the NASA and ASU and University of Michigan. And you see here, if you look actually in blue, you have actually a source of X-rays, and in red and yellow, a source of optical visible light, and in purple infrared radiation. So synchrotrons is actually already exist in the universe, and we have been able to generate these synchrotrons, these synchrotron radiations through a synchrotrons, which is nothing else than an electron accelerator, where electrons move at speed of light in the storage rings. They are generated by a Linux, they accelerated in the booster and store in the storage rings. And in these storage rings, we put either bending magnet here in red or ondulator, and those objects will generate through accelerations of these electrons, which move at speed of light, synchrotron radiations, which will move towards the beamlines and being able to use to the experimental and interact with the matter at the beamlines. This is actually, as I said, has been identified for the first time in 1917, when in the raspberry, the physicists realized that my electrons, when they go at speed of light, go through a bending magnet, they feel the force of Laplace, and then they have accelerated. They have an acceleration of tangential direction, of centripetal interaction accelerations, and because they go at speed of light, they emit electromagnetic radiations with a very small cone of irradiations depending of the ratio between their speed and the speed of the electrons and the speed of the light. And to our days, we can actually use this bending magnet to generate synchrotron radiations over a very wide energy range. You see here typical spectrum, radiation spectrum from bending magnets. Depending of the electron's energy, you can actually shift this energy, the centroid of energy, to the high energies. Or you can use to our days a new device, which is actually ondulators, where actually instead of moving, I will come back here instead of irradiate synchrotron radiations in the corner on the bending magnet, they irradiate in the straight sections, where we build a series of magnetic structure, where the electrons will actually wiggle left and right or through this magnetic structure, and at each wiggling, it will irradiate synchrotron radiations, and these synchrotron radiations will have actually will irradiate at a wavelength which depends of the periods of the ondulator, meaning the periodicity of the distance in centimeters, of my magnetic structure, and depending also of K parameters, which is actually some kind of measurements of deviations of those electrons, and which are proportional to the maximum magnetic fields generated by these magnets. And you see something very interestingly, instead of having a smooth background, you have actually spikes of this ondulator. So you have here a massive increase of brightness by more than 5 orders of magnitude at different wavelengths. And you can move your experiment or your photon source from one spike to another. You have here the fundamental and here all the high harmonics. And depending of if you open the gap of this ondulator, you will change the B fields, and then you will change the positions of these harmonics. And you can really tune the X-ray wavelengths a la carte as you want to the purpose of your measurement. Why do we get these actually spikes? Is because we have very specific resonance conditions which take place in an ondulator to have these radiations. And I try to not put too much math, but to explain that with the small cartoons. What are these conditions of radiation, condition of resonance conditions for an ondulator? Let's say you have now the magnetic structure of your ondulator. The electrons travel along the ondulator in these directions, and the electrons has this red trajectory which oscillates because it's field, the magnetic field, which change alternatively from north to south. And the speeds, the transverse velocity of the electrons is 90-degree phase shift by this dispersion. That's clear because here the electrons come back to his central position. So this is where he has actually a zero transmission, zero transverse velocity. And if you look now, this trajectory, and you assume, okay, here, let's say the electrons emit light at this place, and the light also propagates in the same direction from the electrons. So if you look the phase relationship between this electromagnetic wave, the radiations, the synchronous radiations, and the electrons, as function of the positions of the electrons in the ondulator, half a period later, you have these oscillations, the electrons come here, and you see the wave of the electromagnetic will also propagate at the same times, which actually I mimic by this gray box. And after one phase of 1 period's length displacement of the electrons in the ondulator, you realize actually you need to have to match the same condition than you have before, and you realize then actually the electrons has been slipped regarding to the oscillations of the electromagnetic phase. So it's only on these conditions when actually after 1 period of propagation of the electrons, when the phase of the synchrotron radiations has actually an exact 2 pi phase change regarding the electrons, then you enter to these resonance conditions to have these enhancements of these emissions of radiation. So this is actually, with hand wavings, the conditions of resonance for an ondulator. So every time after 1 period of the electrons, as soon as the electron has traveled 1 period of the ondulator, and the intensity, you will get a resonance effect when the light has propagated by the same quantity plus 1 wavelength of the light, and then you get to this very spiky condition. This radiations synchrotron has been used at PSI since more than 20 years. This is the SLS, and we have actually many different beamlines here, building several beamlines, and you see how it's looked like inside. And recently, in 2023, we went to an upgrade of these machines. We replaced completely the rings. You see here the bending magnet. We emptied the rings, and we built a new rings to increase actually the brightness of this facility by more than a factor 35. And for doing that, we had to change all the insertion device to actually match the new property of the SLS. And before, the SLS has a very narrow vertical beams, but pretty broad peak in the horizontal directions, when now the new machines has also very sharp, small peaks, beam size in the horizontal direction. And for making profit of that, we had to change all our insertion device, which means one of these insertion device will be dedicated to SOLARIS for the beamlines, Ukrainian beamlines project. And this is actually one of these ondulator which come from SLS will be built at SOLARIS to build these MAVKA beamlines. And on the top of this ondulator, we will also transfer a few equipment from SLS to this project. Good. This is actually basic crash course on synchrotron radiations. If I allow me to move very quickly without going too much into details in the next X-ray source, which is the X-ray free electron laser. We have one also at PSI, which is the SwissFEL, sitting in the forest, which is a large facility of about 740 meters. And here, instead of having electrons moving in circle, the electrons move in a linear accelerator. We accelerate them to high energies, typically from 0 to 6.8 GeV. And there they go against to an insertion device as a synchrotron radiation. But instead to have one insertion device, we have many of them, typically 20 ondulator on the top of each other, behind each other, which means the synchrotron light emitted by the first ondulator will start to have an energy transfer to the electron bunch, which travel from the first ondulator to all the ondulator. And as in a laser, these radiations will start to interact with the media, which means with the electron itself, and have a transfer of energy depending on the phase of the electrons he has regarding to the radiation, and it will occur to generate some kind of micro bunchings in the electron package which travel to the ondulators lines of this FEL, which means if I look here as function of the ondulators, this will be my first ondulator here, and here will be my last ondulator at the end of the lines. I have at the beginnings here typical synchrotron radiations, which actually increase linearly with the numbers of ondulators. And suddenly in the log scales, I have a pickup of intensity is when I start to generate this lasing of radiations. It's when each electrons oscillate in phase regarding to the light generated by the first ondulators. This is the same process of self-amplification process as we have in optical laser. And very nice pictures, and I like to show to my students the difference between the synchrotrons and actually the FEL is like you have actually those electrons which is traveling around the ondulator, the machines in the storage rings. They all irradiate in a stochastic way or without relationship in phase. And it's like you go in Venezia and then you have almost a chaos. So that means the intensity of the radiations you have is not, it's not proportional to the number of electrons, but to the square root of the emitter. And the power will be proportional to the number of electrons. When you go to a current manner, then everything gets much more enhanced and the power behaves to the square of the number of electrons. And you become much more efficient by this way. And then you are much more also focused and pointing to one direction. And this is Maybe for the time of lack of time, I will skip that. This is a small cartoon how you can explain these micro-branchings, the physics of that. I will also skip that. Basically, the difference between synchrotron, synchrotron is typically 115-meter machines when we talk about Switzerland, a little bit smaller for SOLARIS, where you have one electron, the electron beams rotate all the times and serve many different beam lines and have a time structure typically of 10 to the 9 seconds, when the FEL radiation is a long and straight accelerator of 700 meters, and it's actually usually only one or few single users operating machines. So it's actually much more costly experiments to be done there because you have only one experiment at the times, when here you have many experiments at the time which can go same in parallel. And here we recycle the electrons per second. So the same electrons move around about few hours. And when here it's one single shot experiment, and after you've done that, you have to refill the machines with a new batch of electrons. So it's very energy costing. But the benefit is you have a peak brightness which increased by more than 10 order of magnitude. As summarized here, you have the peak brightness which moved from 10 to the 26 to 23, and we have a much far smaller photon durations, but of course you have the same number of you have also per pulse, you have a much higher pulse photons per pulse, which open also new physics in this field. You could also, our dream is tomorrow to make quantum movies or molecules movie to see how really in real time how molecules are behaving, how the chemistry chemical reactions act in real times, and this is behaving which actually occur at the femtoseconds. Or actually our dreams will be actually to, with a pulse optical laser, to generate maybe out of equilibrium's superconductivity and to actually observe these mechanisms in a quantum materials by using pulse source. Good, those synchrotrons, we have many around the world. This is a map where you see more than 50 synchrotrons in the world. We have also in Europe a lot of synchrotrons, and this I would like to actually emphasize. This is maps which is done by the LIBS, where you see here Krakow, and actually LIBS, this is an association, so to say, an association from all the synchrotrons worldwide, including also the FEL, to actually give the task to our colleague in SOLARIS to coordinate the buildings of this MAVKA beamlines for this Ukraine's scientists. And we are here, I'm here located at Shevchenko Institute. When X-ray fell, we have much less in the world. We have few machines, 2 machines in US. We have few machines in the Far East, and also few machines in Europe. Okay, so now let's move a little bit more towards more in details what we can do with X-ray interactions with matter. Now you have matter, you have, I mimic here actually crystals, where you have the surface and the bulk, you irradiate with your X-ray the systems, and it can interact by different channels. It can be attenuated or transmitted through the systems, and then you can see X-ray. This is typically the picture of the X-ray, the ends of the wire from the first X-ray radiography, or you can have actually diffractions. This is elastic scattering. We call it Thomson, where an X-ray can be scattered by atoms in an elastic way. So the energy, there is no loss of energy. You can actually have also scatterings through inelastic scatterings, where the photons will timely lose part of its energy through electronic transitions. We call it Compton. or you can have actually you can excite atoms, and then you will have fluorescence radiations on the surface or on the volume, on the bulk, on the different systems. So you see on the different atoms. Or you can have actually absorb your photons and emitted electrons, or emitted no-J electrons, and we call it OJ or photoelectron spectroscopy. So depending of the photon energy, you will have different cross sections for the different process. Let's say for the photoabsorb or Compton or Thomson scatterings, you see then here the total cross sections has actually, it's a sum of the Compton and Thomson plus the absorptions, and you see the absorption has a non-smooth behavior. Is just related to absorption edge, where the X-rays is absorbed by the electronic cloud of my atoms, and you have different electronic transitions available in depending of the atoms where this attenuation, where this absorption has been done. And you see then the X-rays is very good to actually either make X-ray absorptions, spectroscopy. Here you have the maximum of sensitivity. You can also do diffractions, and you can also do inelastic X-ray scattering. Let's focus now in the absorption edge. You see here as function of atomic numbers and the energy of photons. You will be able, depending of the energy of your photons, the soft X-ray, being able to probe K shell absorptions for light metals, M edge for a little bit very important metals transitions, like the metal transitions first row, or being able to measure also M edge for heavier metals. And the MAVKA beamlines will be very strong in the area of the tender and the hard X-rays, and therefore it's open a lot of physics. You're working on K edge, L edge, and even also M edge. Let's focus now in X-ray spectroscopy, what we will be able to do. You can do actually as a photo emissions or X-ray absorptions of resonance. You will actually probe your electronic density of states by absorbing photons, and then you will the energy will be transferred to photoelectrons, and by recording these photoelectrons, you will be able to have a picture of the electronic structure of your systems. So you could also work at resonance, where you select the photon energy exactly depending of the energy difference between the occupied state to the unoccupied state. This is the so-called X-ray absorptions, where you see a strong absorptions change as function of photon energy. And this is very useful to either study hybridizations between orbitals in molecules or in condensed matter. You can actually study symmetry of final and initial states, and you can also have an information depending of your polarizations of the light, have actually details informations of the orbitals of interest you are probing with X-ray spectroscopy. Now, if you have a small focus, you can do the same things, but by actually scanning with your X-ray, your sample, and using X-ray absorption spectroscopy or fluorescence to scan your sample, to have actually on your sample chemical information through this X-ray absorptions spectroscopy. And MAVKA will be also perfect beamlines to approach this technology. Another more versatile approach, you can use these X-rays And you can actually, as I said, look in transmissions. You can use this photoemissions spectrometer. Alexander is an expert on that. And you can measure those photoelectrons. You can actually use also a detector to look how many photons are emitted by my system. You can record also a spectroscopy on this of these emitted electrons. Basically, you can have many different detection schemes and have a deep understanding of all the spectroscopy on my materials. A piece or a typical techniques then I've been very active on it is to do photoemissions, where you promote your electrons from your solids to an unoccupied state by absorbing the photons, and you can record those photons which leave my systems by an analyzer, like here. And if you record the emissions angles of my photons, not just the energy, you can also have any informations on microscopic in the K momentum scale, so to have any informations on which directions these electrons has been traveling in my metals or in my system, and reconduct the band structure of my systems. And band structure, so basically ARPES is actually a wonderful microscopy techniques in the momentum space, the K space for electrons, where you see here the occupied state, the Fermi levels of my system will be here. You record here the energy, binding energy. This will be the band structure. And you see here in momentums, in two different momentums directions, all the band structure dispersions of here. I give an example, Kagome, it's a hot topic to our days, and you can really zoom in. You can do really imaging as we do in X-ray pictures, but there it will be actually in looking pictures of electrons dispersions in the solid state systems, where you have really great details on the electronic structure of my system. Against Alexander here is also an expert, and he may talk more in detail on that. So it has been used intensively in quantum matter, and this is, if you Google yourself, you do ARPES in Fermi surface, you will have a zoo of fantastic and relevant developments and research activity in this field. One important thing is, and this is my last slides, you can use these techniques actually to probe either the surface of my systems or more bulk of my systems, or to look interface of the systems. And because the mean free paths of the escaping electrons are strongly depending, are very sensitive to their kinetic energy. And you can be here in the minimum, at the minimum of the mean free path being very surface sensitive, or increase the kinetic energy of the electrons by having higher photon energy, and then you become more bulk sensitive. So you move from the UV regimes, which is this regime, this surface sensitive regions, to the soft X-ray or to the hard X-ray photo emissions, and also MAVKA will be also excelling in this field. So it will be giving us or you an excellent tools to actually probe electronic structure or condensed matter more in the bulk manner. With that, I would like to conclude my talk by actually telling you then forward you actually making a link to actually the talk from Artem, who will introduce you the MAVKA beamlines to be built at SOLARIS, and it will be beamlines dedicated for micro nano X-ray absorption, soft X-ray ARPES, and also high hard X-ray photo emissions spectroscopy. With that, I thank you for your attentions, and I'm ready to take any questions if questions you have.
Yes, thank you very much, Luke, for the amazing presentation. And I guess it's very useful for Ukrainian researchers and also students to understand how all these large-scale facility instruments as a synchrotron are functioning. So is there any place?
We have a question.
Yes.
We have a question from Kyiv. I think you can, we can't really move the speaker, but he will speak up and we will hear you. Yeah. They can hear you. They can, okay. Okay, but they can't see you.
I just wanted to ask, can we use technology similar to that we use in Free-Electron laser to generate coherent gamma rays?
I'm not sure if I understood the question, so I will repeat. The question is, can we generate current gamma ray with those sources? This is the question.
We use Free-Electron laser to generate coherent X-rays. And I just thought that maybe we can use similar technology to generate coherent gamma rays in the future.
Actually, we are facing to technological limitations. So this, as I tried to explain, the wavelengths you can generate is depending of the perturb of the ondulators and the energy of the electrons which go through this to these ondulators. And we are actually, to the best 2 days, we can generate up to 100 kilo electron volt. And 100 kilo electron volt, for my understanding, is still in the X-ray regimes. It's not the gamma ray. It's not in the gamma regime. So basically, even with synchrotron radiations, the answer will be no. We will never be able, or at least maybe in 50 years, I don't know. Currently, will not be able to reach the gamma regimes with this type of source, and even more, not being able to get coherent radiations, because coherent radiations means FEL, and that will be even more complicated to generate FEL process through a long ondulators lines on the gamma range. This is out of reach to technological point of view. I'm very sorry to give you this negative answer, but we have to be honest here.
Okay, thank you for your answer.
Yeah.
Okay, any other questions? If there is, probably we can move discussion towards email. You can, if there will be any questions from other participants, you can send them to the organizing committee website, and we will contact invited speakers and probably if there will be any more questions. Thank you very much, Luke, again for a nice presentation, and we are moving forward, and next invited talk will be also introductory about synchrotron light, but now the synchrotron lights will be used more in visible ultraviolet region, and it will be Dr. Oksana Chukova from DAISY who will present use of such a synchrotron light for luminescence to start as a tool to unravel luminescent processes in next generation materials.
Good morning, dear colleagues. Do you see my screen? I think, I'm sorry, I shared wrong
No,
screen.
you're
Yes?
sharing perfectly. We see the proper
Yes.
screen, I guess.
Okay, thank you. Thank you very much, Luke, for your talk. It was an amazing talk even for me, and maybe it will be difficult to say something so strong as you, but I will try to deliver some some different information. But first of all, as one of active participants of Ukrainian Synchrotron and Neutron community, I would like to thank all of you who is here today for attending our event. And many thanks to the organizing committee for inviting me to present the talk today. My talk is devoted to use of synchrotron light as a tool to unravel photoluminescent processes in next generation materials. And like next, I just sorry, I just will find how to move to the next slide. Okay, the next slide. There are some students today, and I would like to also to start from the beginning, but from another point of view. So I would like to say a few words about how synchrotron radiation came into the materials science, because at the beginning, synchrotron experiments were thought up as experimental tool to study the behavior of particles and to verify some theories in fundamental physics. At that moment, that come from the first experiments, at the moment of the first experiments, they had some theory predicting that particles, charged particles, those are moving by Q trajectory will emit the light, but actually here you can see a picture of the first synchrotron light photo. I think this is the first. It was unexpected to people who did this experiment that such light is so bright. They sent one technician with a stick, like today we have selfie sticks. So they put a mirror on a stick to see what is happening, and they afraid to approach to that light. So at the beginning it was unknown that the synchrotron light in the future will be used in material science. But now I also would like to mention another story I read recently in the internet. It was interesting for me. Then when Henrik Hertz once was asked about the possible application of his discovery of radio waves, he replied, "Nothing, I guess. It is no use. Whatever, this is just experiment that proves that Maestro Maxwell was right. We just have these mysterious electromagnetic waves around us that we cannot see with our naked eye, but they are there. Today, this useless for his point of view. Radio waves are used from FM radio to wireless internet and so on, and many branches. And the similar story can be told about synchrotron radiation, because now it is used in material science in many branches for many purposes, and usually we can divide synchrotron experiments in material science into three main directions. There are imaging, scattering, and spectroscopy. Imaging also could be subdivided into two branches, two fields. There is imagine that based on comparison of different images, on comparison of images, those are obtained from materials with different properties, with different absorption, elemental composition, with different refractive index, and so on. And the other direction is tomography. In this experiments, the initial light beam is divided on two beams, and one of them is coming through the sample, another one is not, and at the end we are comparing two signals. So if we are talking about scattering, this is like diffraction. This is diffraction in synchrotron. It X-rays because the wavelength of X-rays is comparable with distances between atoms and electron and their sizes. So in a case of crystals, we will see this the diffraction in like droplets. These droplets are organized in cycles. In the case of biology molecules, we will see like pipes, and from these pipes we also will get information about structure of biology molecules, and nowadays this is a very important direction in synchrotron material science, because in DESI we even have a Center for Structure Biology. This is research center, but from my point of view, it doesn't carry out investigations. They take molecules by molecules, and they are doing this scanning and doing maps for biology molecules, and maybe in the future we will have atlases of biology molecules with their structure. So this is possible with application of synchrotron radiation. And spectroscopy. Spectroscopy with as material science with application of synchrotron radiation is also can be divided on three subdivisions. There are hard X-ray spectroscopy, soft X-ray spectroscopy. Maybe I will not and give more attention for each of these, but hard and soft X-ray spectroscopy are based on the fact that synchrotron light excites excite electrons of core levels, and registering their spectroscopy, we can have information about structure of the matter. And after hard X-ray spectroscopy and soft X-ray spectroscopy, we are moving to low energy spectroscopy, and here is our here are our luminescent experience, and this is a place of our photoluminescence study. Why we need experiments with photoluminescence at synchrotron light sources. Usually, luminescence can also be observed in laboratory, but in lab we can achieve theoretically 200, maybe 180 nanometers excitation and continuous excitation, and that's all. Okay, it is also possible to use some cathodoluminescence and some beams for excitation, but these are not continuous sources, and there is gap in excitation. And if you are working with wide bandgap materials, a lot of information is hidden. A lot of information hidden in a range from 10 to 100 electron volts. This is not a range of X-rays. This is a range of vacuum ultraviolet light. And in this range are working and beamline stations with studying luminescence with application of synchrotron lights are working in this range. So there are only 5 beamlines over the work. Those propose possibility to do luminescence experiments with application of synchrotron light. It is not so much. And there are beamlines in, there are 5 countries. I made a mistake, 5 countries and 6 beamlines, because Sweden has 2 beamlines at those luminescence experiments with synchrotron excitation are possible. So there are Germany, Sweden, Brazil, Japan, and China. Even United States has no such beamline. They had before, but after upgrade of their synchrotron, now they have no such beamline. So synchrotron users from United States, those are working with luminescence, should come to Germany, Sweden, or Japan. So the most of these beamlines are using bending magnets for excitation, because bending magnets give lower energy. We don't need high energies for photoluminescence experiments, but 2 beamlines in Sweden are used undulators, and their energies excitation are much higher than others. So one finest beamline can use excitation for 4.5 electron volt to 1,300 electron volts, and other beamline can give excitation up to 12 kilo electrons volts even. But these beamlines have some disadvantages. Some samples can be destroyed. I know that even often samples can be destroyed under such radiation, luminescent samples, and they have gaps, energy gaps in excitation range due to application of undulator. So here you can see from Max 4, there is finest beamline and Femtomax. So the another disadvantage that finest luminescent beamline is located in the one branch together with another beamline facility. So they are changing twice a year one end beam station with another beam station. So luminescent beam station is available 2 times a year for from 2 to 3 months only. Other time is devoted to another beam line, and it is possible even to find in the at YouTube videos about how they are changing one end station to the another end station, so they are not working together at the same time. The beam line that is available at China provides much lower energy. They are working in wavelength region from 130 to 130 to 360 nanometers. That means that they can achieve around 10 electron volts energies only. The luminescent beam line is in Brazil is working from 180 nanometers, even lower energy possibilities, but yes, they are working. They are started only a few years ago, and maybe in the future they will reach more high energies, but why they have this limit 180 nanometers? Because this is a limit, wavelength limit. From this point air starts to absorb, and in order to get a high excitations, high energy excitation, or let's say lower wavelengths, we need to connect samples, at least sample chamber, directly to the synchrotron ring, and to have a vacuum during all the way of synchrotron light to the sample. To allow the excitation lights to be not absorbed by the air. And there is a vacuum issue in Brazil, so they still cannot connect their beam line directly with common vacuum to the synchrotron. But this is successfully done in DESY. Here you can see in DESY we have 2 kilometers and 300 meters long synchrotron ring, and our beam line number P66, time resolved photoluminescent spectroscopy, is located at the top of the tunnel. The most not the most, all the others beam lines are located in these 3 buildings. Those are marked in blue in the same horizontal plane with a synchrotron, and only our beam line is not in the same plane. It is the top of a tunnel. This is done to have some space between, you can see here, this is a tunnel, and where is a synchrotron light running, and at the top of the tunnel we have our beam line. We are working with a reflected synchrotron light, and there are 6 meter distance because the reflection mirror and our beam line. If something happened with our vacuum, then there is a special valve that will be automatically closed, and we will not waste the vacuum in synchrotron ring. So that is how is organized in the level of synchrotrons. After bending magnet, synchrotron lights is coming to the first mirror. It is a water-cooled mirror, and it is a little bit collecting a light and sends the light up to our beamline. So you can see light is going like I show here by yellow arrow, and then up. And here it's coming here, and there is first beam shutter automatical. I told that it will close. After that, the synchrotron light is going to the second mirror that is also collecting synchrotron light in the another plane, and after that synchrotron light is going to our primary excitation monochromator. In our primary excitation monochromator we have two gratings. One is aluminum grating working from 100 to 330 nanometers. Another one is platinum grating. Platinum grating is working from 30 nanometers to 120 nanometers, or probably 150 nanometers. We are usually using to 120 nanometers. After that, we have third mirror that is collecting a light in the sample chamber. You see here sample chamber. It is still under vacuum, and this third mirror is collecting light on the sample. So there are our parameters, and there is a sample chamber, how it looks in lights inside. So the light is coming here. Here we have a cryostat and a sample holder where we can place up to 40, usually no more than 30, but up to 40, and record is 90 samples because we can put the samples from two sides and rotate the side of cryostat. So we put these samples inside the cryostat once a week. Then we pump vacuum dependently on quantity and quality of samples. It could take from 12 to 30 hours to achieve the vacuum that it is enough for our measurements, and that is enough to do not waste vacuum in a synchrotron ring. Our cryostat is a flow type cryostat, so helium vapors are coming inside. We put our samples on this sample holder using silver glue that has no luminescence to achieve a good connection between the sample and sample holder, because if we are going to low temperatures, we will need this good connection to cool our samples. So we need to work very carefully with our samples and with our sample holder, because we cannot touch it by hands, and usually we cover it for the time when we install the samples to do not waste the vacuum. Also, because of vacuum requirements, we cannot investigate the samples, some organic samples, and the samples those explode gases. So we even have a special vacuum testing box at our beamline to test are the samples wasting the vacuum or not. So there is a photo of a sample chamber, of a sample holder inside our sample chamber. So we have two cryostats, and you know that liquid helium became very, very expensive last year. So we bought a closed cycle liquid. Closed cycle helium cryostat, but it weighs more than 15 kilograms. So we have a special crane to install this cryostat with the samples inside our sample holder. Here you can see pictures how Ukrainian users are and our beamline manager are installing their samples inside the liquid inside our sample chamber. So there is a crane and the cryostat with this sample holder, they are at the crane. So, and there is a place, and sample chamber is here. Here you can see the cryostat with the samples, how we adjust the samples here. So it is on the place. So our beamline P66 time resolved luminescent spectroscopy is involved in several programs, and we had DESY summer students this year. They spent 3 months at DESY studying everything about synchrotron light and doing experiments here. This is my student, Alina Popova. She is from Ukraine. Came to DESY for summer school. So we also hosted this year some nephews, users, and nephews like students, not students, for nephews twinning program, and also our beamline is participating in NFFA project, and we have NFFA users in particular even from United States. So, and here you can see that it is possible to adjust the sample, but we need human presence here to adjust the samples, because we put like 70, 80 samples at the same time. So we need users to change the samples to adjust the light on the sample, but all the other procedures can be done using remotely and using internet. So we can even see remotely our X-synchrotron light on the sample, but in order to move up and down, right, left, or rotate a sample holder, we need people. So vacuum is controlled using internet and interlock. This is interlock system, so it is not possible to manage this from outside of DESY, but our beamline manager is sitting in another building and controlling the system remotely for his office. And also experiments, all moments in experiments are also controlled, could be controlled remotely. So one more moment that each time we need to measure our excitation light. Usually we do this. We are starting.
Sorry, we are a bit short in time. Can you continue more to the final because we have like 3-4 minutes.
Okay, thank you for this. So these are our my own recent results. You can see that we are correcting our maps and can get a spectra. Also, our recent results, you can see that there are excitation band around 155 nanometers. Here it is not possible to reach this excitation in the lab. So about time resolved experiments, these are some decay curves of luminescence emission obtained at different excitation. For example, here is barium fluoride at 56 nanometer excitation in comparison with the cathodoluminescence results. Here is halide perovskite and its decay time at various excitation with synchrotron light. So, and I also would like to say that DAISY supports Ukrainian science, Ukrainian synchrotron science, Ukrainian users, and we had a Horizon project. So this support was recognized by National Academy of Science of Ukraine, and the first visit of newly elected President of National Academy of Science of Ukraine was to DAISY. Here you can see Anatoly Zagorodny, and here he is. He brought some diploma to the former director of DAISY, Helmut Doch. He just leave his position. So this was some colloquium devoted to this event, and there were a lot of international guests, and our president of National Academy of Science of Ukraine was among the foreign guests, and also DAISY supports as much as possible and would like to bring much more support to MAVKA beamline. So here we at SOLARIS, where is the lines and the floor where our beamline will be, and we are staying. I think we are staying at during the, we are following by future our beam, and currently DAISY consider how to submit proposals to find more money for development of MAVKA beamline. So also we are going to contribute with maybe some equipment that is already possible in DAISY. And thank you very much for your attention. And thank you very much for possibility to give this presentation.
Thank you, thank you very much for very interesting talk, and especially now transferring from Luke, who was presenting more like theoretical, not theoretical, but more like in general the concept, how you perform research, what you study. In your presentation, we nicely were able to see how it's happened really, how is the experimental chamber working, that we need to care about vacuum, that we need to care about a lot of different elements during the experiment. And exactly like this, I know that in MAVKA beamline it will be also directly connected to ring vacuum, and it will be the same issues with with taking care about vacuum system. So, and for all possibly future Ukrainian users who are attending this event, it's very important to understand how basically operation would be there and what they can study. So, and we have time for one short, quick question. Is there any questions in the auditorium?
Yeah, I'm just curious, how much energy does an average synchrotron consumes, like in kilowatts per hour or megawatts per hour?
Sorry, I cannot answer.
I guess this is an answer to me, and I have this answer, but not in head. So I promise you, I put in the chat in a few minutes after getting back the numbers. Okay? Good.
I have only information here. So about the energy on our sample. So in our parameters, about photon flux on the sample. Can you see here? 2 to 10 photons per second in the
and if you listened Luke's presentation, he was explaining what does it mean this flux, and you can calculate what is the power on your sample. But then about, just also will quickly answer, about total power is much more complicated task because you have a lot of infrastructure and everything for beamline communication. So probably Luke was mentioning he will put it in the chat and I will communicate it loudly after the next talk. Thank you very much, and we are moving forward. We slightly delayed in time, but I hope that we will be managed. Probably we will take a bit of time of our coffee break, but the next speaker is also one of is Professor Alexander Kordyuk. He is a president, director of Kyiv Academic University, and his role also, he is also president of or head of Ukrainian Synchrotron and Neutron community, and he will have a talk about synchrotron light, Ukrainian synchrotron community, and how you can use synchrotron light to study quantum materials or to have because synchrotron light is a photon science, so the main idea is photonics of quantum materials. Thank you, please.
Thank you, Danylo. Can you hear me? Can you see the full screen? Can
yes,
you see
yes, perfect. That's amazing.
Okay, good. Good. Thank you for presentation and thank you for organization this event again. So my talk will be more or less physics, more formal. I have some, I think, half of slides from previous year from the talks, but I will just try to say something new, comparing something new about organization and a bit about physics. Here, this is just for attracting attention, right? These images, these photos, these are just from this spring. These are two events for us, just for events for meeting about workshop about progress of MAVKA construction, as you said, as you could know already about it, and from our beamline at SOLARIS. And I will talk about this stuff. But what I was to talk it is first about Ukrainian synchrotron and neutron community, about what we are doing and about the progress, current progress. But to also speak about quantum materials, I want to speak about them more, let's say, seriously, or just to define how to define them from point of view electronic structure. And about photonics of quantum materials, what is this actually? And say also a few words about today's Nobel Prize in Physics, which called macroscopic quantum tunneling, and what is relation between all of this. Starting from 1 year ago, from this event, which was also organized in the same place, right? I want just to say that it was it was even more talks last year, and all of them are, almost all of them are accessible by this link. It is on YouTube. You can check them and see and compare. But then actually, that was the first, we call it the first workshop of Ukrainian synchrotron community. After this, we expanded community to also to neutron, and we now called Ukrainian synchrotron and neutron community, right? And this is the last slide from my talk at the European so-called USO, European Synchrotron and FEL user organization. So there are different organizations, and I reported also about progress of the last year. It was some progress of developing of our community, and this is important that this European Synchrotron and FEL user organization, it consists of 32 European member states, European members from European states and associated countries, and Ukraine is 32nd, and it is already included in this organization already 2 years, and even more, maybe 3 years, right? And only now we became official organization. But this is very important, and one to be in such organization, and one of the important projects of this organization, I want to mention again this Nephews project, which gives opportunity now, especially for widening country, and especially for Ukraine, from people from Ukraine to participate in in this experimental sessions, to participate to make in so-called beam times, and now practically anyone could apply can get this support, who apply to synchrotron and get beam time there. And I again say about that, so invite all people to try to do it. There are 3 programs there, and actually it is contribution, I think, important contribution of our USyNC in increasing of Ukrainian participation in this program. Here I got some information from Piotr Pivovarczyk, who is coordinator of this project, about Ukrainian participation. And if the last year it was only 4 cases, or two teams which use them. Now we have much larger contribution. So it is early stage researchers. It was 2 plus 5 now, and twinning program is 13 researchers, and TNA, transnational access, which actually give you access to a real experiment with your project. It is 31 researchers. And actually these 2 another programs, I will not now discuss these details. It is better to go to the site and to see, but they are still open. We have still 1 year of working of this project, and it is especially very important for young people that there is possibility to go into this field, and it is a very important project, so don't miss your chance to do it. So going back to USyNC, we finally became official. It is now so-called громадська організація, ГО, так, and with its number, and it is so-called неприбуткові організації, yes. So we should now, it is already long ago, we should do it, but we should make some meeting where we should elect the president, which will do this some active research. And for this, for this official documents, to making it officially, we are grateful. It was mainly made due to Oksana and Yana, so we are grateful to them for this. And this is already photos you saw from this workshop at SOLARIS, and where Ukrainian beamline will be, right? And this is people who are working on it. It is already quite a big team. And among the benefits of this beamline, I want to say that it is we see it as a center of condensation for Ukrainians at synchrotrons, and this is point of a starting point at SOLARIS. And at SOLARIS you have also other beamlines, and for example, this is our beam time at another beamline, Uranus beamline. It is very nice photo emission beamline. And with this Nephews project has funded almost all people here. So two people were funded by transnational access, 2 people by twinning. So our postgraduate student, and Igor was funded, another PhD student was funded within this early career researcher program, right? But also it is here teams here except 2 Polish HOS beamline scientists. Here are all Ukrainians. You see Danylo here, and also Sergei and Alexander came from Dresden. It is our German partners. And it is important that we consider this future Ukrainian beamlines first, and also this making remote experiments, not remote, but making experiments in research infrastructures in Europe, such as synchrotrons, is important part of our project, which is our Ukrainian-German project, which is called GUKUMAT. This is German-Ukrainian Center for Quantum Materials, and its aim is to build in Ukraine the German-Ukrainian laboratory, and later convert this laboratory into user open facility and key research laboratory. And therefore it is first open for all the people who are interested in such an experiment here and worldwide, and also it is open for partners to form this key research laboratory. And therefore it should be, I think, also interesting for physics, for faculty of physics. And the physical scientific aim of this project is to theory-assisted search for new quantum materials. And synchrotron experiments is the most important tools in this respect. Actually, Luke already covered in his nice talk, covered this topic, and I only want to say that it is also this project is continuation of the previous project, was UKRATOP project, and you see how it was successful in terms of very nice publications. And the last publication was in Nature, and that was actually about discovery of superconductivity in new material, in topological material, is platinum bismuth 2 material, and new states. And this material is, I would say, ultimate example of quantum materials which we are looking for. And these are results just to have flash results from our beam time at Solaris, that we see that the surface state on this platinum bismuth 2 can be operated easily by evaporating of here is rubidium on the surface, and how we did not explore it in detail yet, and we see that it is only one step to study it, and it's very interesting. But I already mentioned this term quantum materials, and this is usually people ask what is quantum materials. But to explain it and to suggest how we can quantify it, in a sense, to say that classify it, yeah. We should do it in terms of electronic structure. And the next couple of slides, it is just to explain what do I mean about electronic structure, because I'm sure that not all here can understand it now. But this is very simple. Electronic structure, this is just to understand it, it is starting from a photoelectric effect. If you shine on the sample by photons, and it is nice if this photons in monochromatized, like you get from synchrotron, you have some spectrum, yes, and spectrum of electrons. You measure the electrons, photoelectrons, and due to energy conservation law, you have some information about that binding energy which electron had in solid. And this is so-called photoemission spectrum, but it is, if you just zoom in on the highest energies, you see that this structure is very interesting, very complicated, and this is called valence band. This is about electrons that participate in chemical bonding, and in also these electrons which form the metals. And if we can resolve also the angle at which electron escape the samples, then we have such a structure which is actually very similar what people calculate and what people call the electronic band structure, right? But this electronic band structure, this is the structure that define all the properties of materials, and especially the electromagnetic properties and such, for example, superconductivity. It is defined by the electrons with the highest energy, and these electrons. This is near the Fermi energy, and in this respect, I will skip this since it's already, I think, was shown. But I just want to say a bit more about structure of the spectrum for you to understand later to define what is quantum materials. So what we have usually, we have the distribution of the with such a method, we have the distribution of electrons in momentum energy space, and it is actually what you see in from your analyzer on the detector. But this distribution could be called also the spectral function, and it has some structure that it is formed due to let's say two effects. It is interaction of electrons with the lattice and interaction of electrons between them or with other degree of freedom like phonons. And interaction with lattice make you such a kind of which is called bare electron dispersion. If electron do not interact only with crystal lattice, it would be we would see such a thin line, and because of this, since experimentalists see this, they could say that it is because you have uncertainty principle and you have the Pauli principle, that electrons in inversed space in energy momentum space, they occupied the states. They can occupy only one state and each electron, and therefore this space for electron is such kind of real space where they localized in each state. In each state you can find one electron. Actually, if with different spins, then two electrons. But it is important then all the electrons which you have, they just occupy the states. Since we have now we count the electron which conducting electrons, so-called, then they are approximately their number could be as much as number of atoms or number of unit cells in the solid. It could be twice or number of unit cells. So it's a lot of them. Therefore, we do not usually see these dots, but we see some lines. But in addition, this would be if you have just a box or line, if in one-dimensional space. But if you have periodic system, you have already like interference of this pattern. You have this when electron interact with periodic potential, you have as a result they become Bloch electrons, it's so called. But in experimentally we see like result of interference, except this instead of this free electron parabola, you have already multiplied parabolas. And what is important that you have new scales which called brilliant zone, which is inversely proportional to this scale distance between atoms. And what is important is there is gap opening when this replica crosses, and this gap is called band gap. It could be about scale of electron volts. If it is 5 electron volts, it is and your Fermi level goes there. You have insulator. If it is 1 electron volt or less, it is semiconductor, but it is quite large in a sense. So it is quite large, let's say, for us, quite large scale. And this is example of real experimental data. And from this data, you see that you have some bands, and these bands, the width of the band is defined by this interaction of electron with lattice. And as stronger interaction, stronger scattering, then wider this electronic bands. But also there are small gaps. And in this example, this is example of so-called excitonic insulator. This appears as a result of additional order which appears, and this additional order gives you another gaps. And a few examples of this, it is ordering in between interactions in interaction space, and this ordering opens superconducting gap. It is usually much less. It is less than 10 milli-electron volts or even less. And another, it is a so-called Pierce gap due to, for example, charge density wave, charge ordering, additional charge ordering. Simple example, the simplest example is dimerization. You have in addition to large periodic potential, you have some small addition, and the small addition opens you smaller gap. And this is also example in momentum space how this gap opens in transitional metal dechalcogenides. And I'm speaking about this because this gaps is exactly what the feature which in electronic structure helps you to define what to call quantum materials. Because in principle, a term of quantum materials was introduced already 10 years ago, almost, yes, to just to put under umbrella the most interesting cases in condensed matter and superconductors, strongly correlated system, charge density wave, topological materials, and to somehow classify them, it was suggested the term of emergence, that it is emergent phenomena. For example, in superconductivity, in principle, it's clear that all the material should be, the properties could be described only if you understand the electronic band structure, electronic structure. But it is already quantum effect. But it is so-called semi-classical approach. But if this some parts of this, for example, electrons, they interact between each other and emerge new quantity, like pairs in superconductivity, then we call it quantum materials. But in terms of electronic structure, I would say that if interaction is incoherent, you have just widening of the spectra, and it is also interesting because from this widening you can get important information from this interaction, and you can understand, for example, the origin of high temperature superconductivity. But if you have a coherent interaction like superconductivity, like charge density wave, which you have some interference from this, then you have additional gap opens. And in more general, to say that you have additional feature in electronic structure. It could be gaps, or it could be, for example, some surface states, like in topological materials. And this is classified now as quantum materials. And when I say, when I put in this, so when I say photonics of quantum materials, when I put it in quotation, I keep in mind the suggestion about collaboration of KAO and Faculty of Physics to make a new program or block in the educational program, which is actually devoted to the SYN, which is, from one point of view, it is some overview, some experience on different modern techniques, mainly synchrotron-based techniques, which is like photonics or electrophotonics. And from another kind, it is very interesting materials which are interesting, which are the hot topics now. And in combination of this, we plan to make such an educational program. And then what I want to say more, okay, and this is actually I said about our plans about this beamline, but it is only one beamline on one synchrotron. And in Europe, there are a lot of such a synchrotron. It's about, you see, about it is about 20 facilities which is under LIPS, League of European Accelerator-based Light Sources. And in the world, it is about 60 such a synchrotrons, and actually we plan to build such a synchrotron in Ukraine also, and with help of LIPS. And it is also, I think, very perspective topic. Okay, I see that the old schedule is already passed, but still I expect that I have still 15 minutes about, right? So I will. I want to speak now about superconductors. Just briefly mention superconductors and classical quantum materials, and then their relation to this year Nobel Prize. So superconductors were discovered long ago. Cameron Onnes got his Nobel Prize for it. And their theory was also, so-called BCS theory, was suggested also long ago and also got Nobel Prize. And it is in this theory, people realize that there is some attractive interaction between electrons due to additional quantities, which is called phonons. Then this interaction gives you some gap. So electron, to escape from solids, they should also break this additional bonds. And every time when gap appears, it is energetically favorable because it lowers the kinetic energy. And actually interesting development, very very huge development was with opening with discovery of high temperature superconductivity, which appeared this material appeared very complex in their properties, although structure were not finally so complex. But what is important, why it's so? Because here we have actually this image is represents the physics of cuprates, high temperature superconductors, the so-called phase diagram. And in this phase diagram, as a function of here doping, but a function of charge carrier concentration, you have different phases on the same materials. And it is antiferromagnetic insulator or it is superconductor here and here. And it is so complex because here you have exactly the interaction of different gaps or different quantum phases. And this is interaction of superconductivity, spin density wave, charge density wave. It is very interesting. Because of this, I will skip all of this. Just want to say that just want to now speak about macroscopic quantum tunnel and what is this. And many people, even experts in superconductivity, were wondering why people got this year Nobel Prize, because there are a lot of Nobel Prize already for superconductivity and for similar effects and for quantum appearance of superconductivity and macroscopic quantum appearance of superconductivity. But you know this story about quantum computers, how perspective they are, and superconducting quantum computers. I mentioned it, and I told more about it last year. And but all this main element of the superconducting quantum computer, it is so-called superconducting qubit. And it is based on so-called Josephson effect, Josephson junction. If you have connection of, let's say, tunneling contact between two superconductors which are not contacted but have, for example, insulator, thin insulator in between in tunneling regime, then when electron can tunnel single electrons, and that was believed that two electrons, the pair, was much more difficult to tunnel, but it appeared another way around, and it was they can tunnel, and this tunnel is very interesting. And based on this tunneling, Josephson, as theoretician, got Nobel Prize, and people who observed it later got their Nobel Prize already, you see, in 70s. And the effect is that the superconducting condensate in each superconductor can be, it is complex, it is wave function, can be associated with some phase. And in this contact, you have a phase difference between these phases. And if actually the current through this contact, it is just related with this phase difference, but such a periodical law. And another effect, if you apply the voltage in to this contact, you have a constant change of this phase. And what today's what this year Nobel laureates has found that you can make a large system, a macroscopic system, which behaves in quantum way, and just that this contact behave like insulator. You know, this such a let's say oscillator in oscillator circuit in electromagnetism. It is standard, but it is interesting that you can make such a question about phase, about this phase difference, which is very similar to the equation of mechanical oscillator, right? Just instead of X, you have this phase difference, and instead of mass, you have capacitor, you have capacity. And why it is interesting? Because you can make it very small, this capacity, and this means that like in mechanical oscillator, if m is small, then frequency, this is its frequency can be much larger, and you easily goes to quantum regime, because quantum regime, when h Planck constant multiplied by this frequency became larger than kT, than temperature, then you can, at this temperature, you can observe this quantum states, and you can somehow operate with them, and you can observe some tunneling. Therefore, it is interesting that if we consider this potential, which is due to this Josephson effect, is like this, potential like this. So it is called so potential as this tilted. Okay. And if it is interesting, if system is here and you measure it escape from this from this minima, right? From this gap, you have just its escape due to temperature fluctuation. It is linear with temperature. Some value is linear with temperature. But when you lower in the temperature, you have only now quantum fluctuations, which does not depend on temperature. So then you are already in quantum regime, and this means that your energy level here is quite discrete, and you can operate with them, and you can make them 3 or 2, and you can manipulate them, and therefore you can just make in such a macroscopic system, you can make a system which could have quantum levels. And then you can entangle different such systems, and they make a quantum computer based on this. And actually, it is many people that time explore similar systems, but it is Martinez who actually became head of the laboratory of Google, who make this a huge progress in quantum computing. Okay, I see that time is almost finished. I just want to suggest you maybe lectures of Sergei Frolov if you are interested in this topic. He is from Ukraine, but it was in the time when he became a professor in Pittsburgh, and it's very nicely explained the problem. And just I remind the people who was in the last year conference about our result in this direction, how actually synchrotron or such a measurement electronic structure is important to make this device, to make Josephson junction. We actually need to yeah, I understand that I wanted to put too much here, too much information, but I want to say that it is important to know in this tunneling from which portion of the Fermi surface, in which material the electron tunnel, or in pair tunnel, from which portion of the Fermi surface in one superconductor through some filtering layer and to another superconductor, because in this way you can adjust where electron come and where electron goes, and which gap is open there. And this is very important for the material with high temperature material with high gap, and it is very important to use material with higher gap than aluminum because to decrease this decoherence and to make a progress in quantum computing. Okay, I understand that it is already too much. Therefore, I just want to finish with this again, with this MAVKA beamline, that it has many benefits for Ukrainian researchers. And but the main benefit, except I have mentioned already, that we consider it as only the first step for building of Ukrainian synchrotron, the East European synchrotron in Ukraine. Despite it is quite expensive project, but I estimate it quite real even in this situation because there is some European money or the money for reconstruction of Ukrainian infrastructure. In this sense, the synchrotron is the most interdisciplinary tool, and it is, I think, it is the most important to build a synchrotron in Ukraine. Okay, so this will be also important challenge for Ukrainian synchrotron and neutron community. You see that I did not mention neutrons at all here, but still it is a large infrastructures and also gives you interesting possibilities to explore the materials and to explore the physics and to find new materials. And therefore, I invite all of you to join this our society. And we will soon will have a meeting, and I invite you to join this meeting also. So thank you for your attention. I see that's it for today. Sorry for such how it's called already. We have some interference with other events here. Therefore, you see that I could not even focus on this talk as I planned. Sorry, but if you have some questions, I'm ready to answer.
Thank you very much for your presentation, and I hope that definitely the ultimate goal of Ukrainian neutron and synchrotron community would be a own Ukrainian facility. And we have time for a quick question. For one quick question. But as we are, if there is no question straight away. Luke wants to have a question. Perfect.
Yeah. Alexander, do we have already a place, a location for this CELS foreseen?
No, of course, the good question, the good answer, the honest answer is no, in a sense that it is still not in this on this stage because but we are working on it in a sense. For example, I'm telling about interference, and today just we have a meeting our let's say Center of Innovation. Which are trying to build here the so-called scientific park, Academic City. And this scientific park is very similar. Actually, they took it as example, Berlin Adlershof. Not, unfortunately, not PSI, but Berlin Adlershof, but it is, of course, you understand. And and we are thinking about the place here, but I think it's unlikely because it would be place for such a synchrotron as SOLARIS, but not a place for such a synchrotron as Swiss light source. And it should be outside. But here we have the people from Kyiv. How it's called? Kyiv. I missed all the words now. I'm switching between different languages. You see. So
Shevchenko National University of Kyiv.
No, not Taras Shevchenko, from Kyiv Council, right? From Klitschko, and they already thinking about this, but also the nice place it's outside Kyiv and but also another alternative is closer to border, and this could be Lviv or Chernovtsi or Uzhgorod, I don't know. It's Lviv, looks more attractive maybe. And I already told about this with Sadovy, who is the governor, how it's called, governor, mayor, how it's of Lviv. So we are speaking about it, and I feel my aim also to get them interested and to get them compete about possibility to build a synchrotron in this place. So we will see, but still, but I agree that this is an important point even before asking for money, right?
Thank you.
Okay, thank you for wonderful talk. And in the schedule we have a 10 minutes break, but we are already 20 minutes later. So I would suggest that we will have, if it's possible, for next speakers 5 minutes little break, and then we start and probably we catch up during the lunchtime. So we have 5 minutes breaks and students can take coffee. Also in the faculty, they are not on Zoom, and I see that they are sitting in front of the of our camera and didn't. So basically we have 5 minutes break and we start our session at 11:25 European time and 12:25 Ukrainian time. And so 5 minutes break. So I guess we are ready to start, and the first talk, as I was introducing, will be done by Dr. Ewa Partyka-Jankowska about, sorry if I misspelled your...
No, it's completely correct.
And it will be about research opportunities as SOLARIS Synhrotron and generally about beamlines and what kind of opportunities Ukrainian users can expect while applying to SOLARIS.
Danylo, thank you very much for this nice introduction. I will try to share my screen. Can you see it?
Yes.
Perfect. Okay, thank you very much. So good morning, everyone. My name is Ewa Partyka-Jankowska, and I am Deputy Head of Scientific Department at SOLARIS. And this is really my great pleasure to have this opportunity to talk about our research opportunities during this meeting of Ukrainian Synchrotron community. So let me start this presentation with a few words about Synhrotron SOLARIS. So SOLARIS, this is a third-generation light source, which was constructed between 2010 and 2015, and it was done in close collaboration with MAX4. It was financed from EU funds, and already at 2018, our infrastructure had developed enough that we could support first users. I must admit at that time we had only 2 beamlines, but anyway, we started operation. So today our facility is financed by the Ministry of Science and Higher Education, and we operate as a unit of the Jagiellonian University. So moving on, our center is a major hub for research, and we actively promote collaboration, both across Poland and with international partners. So for example, we are a member of the League of European Accelerator-based Photon Sources, which is formed by 16 organizations representing 19 light sources in Europe. In addition to that, we also contribute with approximately 10% of research time to the Central European Research Infrastructure Consortium, so-called CERIC, which gathers unique research facilities in 8 countries of the region. And now let's take a look at the design of our Synhrotron. So we have 2 accelerators, the linear one with the energy of 600 megaelectronvolt and the storage ring. So the storage ring, this is a very small storage ring with the circumference of 96 meters, and it operates at the final energy of 1 gigaelectronvolts. We have 12 bending double band achromat magnets inside, And the storage ring operates in a decay mode with maximum current of 500 milliampere and a total lifetime of 15 hours. So it means we have injections twice per day. What is important, this Synhrotron is optimized for soft X-ray energies, and its critical energy is around 2 kiloelectronvolts. Okay, now I will give you some general information about infrastructure, and later on I will go into the details of each infrastructure, and I will show you also some results which were obtained at those infrastructures. So at the moment, we offer research at 7 experimental beamlines and 2 cryo microscopes. So the users, they can perform the research exploiting IR microscopy at the CERIC beamline, VUV spectroscopy at Uranus, soft X-ray spectroscopy at PIRSC and Felix. Then we have soft X-ray microscopy at Demeter, tender and hard X-ray spectroscopy at Astra, hard X-ray microscopy and tomography at Polix. And we, as I said before, we have also 2 cryo electron microscopes. And we have already the end station of the SMAUG beamline, which will be dedicated for small angle X-ray scattering. So we can perform at the moment experiments with the laboratory source, but we do not have a beamline yet. So we are working on it. And there are several projects which are under construction, and also we are awaiting financing decision. I will talk about this a little bit later. Now I will go to the details of each infrastructure. So let me start with the first beamline, which was built in Solaris. This is the PIRSC beamline, and it's operating with users since 2018. And this beamline is dedicated to soft X-ray spectroscopy and dichroism research, and operates in the energy range from 100 to 2000 eV. So the beam size at the sample is around 250 micrometers horizontally and 40 micrometers vertically. We offer 2 detection. So as I said before, this is for soft X-ray spectroscopy. And we offer following experimental methods. So we have X-ray absorption spectroscopy, XAS and NEXAFS, as well as we perform also circular and linear X-ray magnetic dichroism research. And we offer 2 detection modes, so with surface sensitivity and bulk sensitivity. As we work with soft X-ray energies, we have to perform our research under ultra-high vacuum conditions, so all the samples have to be vacuum compatible. The measurement can be performed at varying temperature, starting from cryogenic temperature, and we have also access to magnetic field along the beam axis. This is a small magnetic field of 140 millitesla. But anyway, this is sometimes enough to perform magnetic research of the materials. And what are the possible applications of this beamline? So this is really good beamline if we want to determine oxidation state and local atomic coordination, or we want to study structural anisotropy or chirality, or we want to perform research on magnetic properties of materials. And so many studies on this beamline focus on new materials for energy storage. And here I selected one example. Here are the results of a recent experiment on new cathode material for lithium-ion batteries. So the researcher, they tracked the evolution of L3 edge of manganese, cobalt, and nickel, and different charge and discharge states. So they wanted to understand how the redox processes look like and to identify the most active elements. And this is very common topic of our research or of research at our beamline. Now we move to the Astra beamline. So this is like PIRSC, this is beamline, which is dedicated to X-ray absorption spectroscopy, but it operates in a different range. So we have range from 1 keV to 15 keV. So this range does not require ultra high vacuum conditions. So we can measure a variety of specimens, including liquids and gases as well. And this beamline specializes in EXAFS and XANES method, and in recently added Raman spectroscopy. So those methods are perfect if you want to study oxidation state, coordination environment, you want to get information on local structure. At this beamline, you can also perform in situ and operando studies at near and ambient conditions or with controlled gas atmosphere, and also at varying temperatures. And here I have selected one example of the research performed at this beamline. So there was a team from West Pomerian University of Technology, and they were exploring next generation catalysts for ammonia synthesis. So they designed a very promising catalyst by impregnating aluminum oxide with cobalt and molybdenum compounds, and it was followed by activation process. However, the standard laboratory method they used, they didn't allow to fully determine the active phase structure. And only by combining XANES and EXAFS, those scientists could really understand the mechanism which leads to the active form of the synthesized material. So this is also very common topic studied at Astra beamline. Okay, so now we move to our photoemission beamlines. We have two photoemission beamlines. So the first up is Uranus beamline. So this beamline is used to study the band structure of solids using angle and spin resolved photoelectron spectroscopy. So this beamline operates in the range from 8 eV to 500 eV. And of course, if we deal with this range of the energy, everything is performed under UHV conditions. And so here we have the probing depth of a few nanometers. And this beamline is really proud of it that they recently installed a new manipulator. And so far I know the accessible temperature will start from 2.5 Kelvin. Yeah, what else? So this beamline has been also recently equipped with a spin detector. Spin detector is now in expert commissioning mode, but anyone can apply for it. And the typical applications of this beamline are studies of valence band electronic structure of solids, films, crystals, superconductors, and so on. And one of the very interesting research cases which was studied at this beamline concerns tin. So tin, this is really ordinary and well-known material, but it turned out it can reveal unique electronic properties under extreme conditions. So I'm not sure whether you know, but historically, the low temperature form of tin, so-called alpha tin, caused problems during harsh winters because this low form destroyed organ pipes in churches. But now our international team of scientists, they managed to stabilize this form at the room temperature by applying small forces, and they discovered some very interesting properties. Namely, they showed using ARPES that alpha tin belongs to the class of Dirac semi-metal, but transforms into Weyl semi-metal when an external magnetic field is applied. Really interesting research. And the next photoemission beamline, this is Felix beamline. It offers also photoemission spectroscopy, but works in a slightly different range. So the available energy range starts from 40 electronovolts till 2000 electronovolt. And this station offers a wide range of photoelectron spectroscopy modes. So we have XPS, we have ARPES, we have also spin-resolved ARPES, and additionally, also X-ray absorption spectroscopy at this beamline is available. So this is really typical surface end station operating under UHV conditions and at temperatures varying from cryogenic to elevated. And this is a perfect tool if you want to study electronic structure of inorganic and organic solids, and also if you want to determine chemical state and coordination. And if you want to learn more about this beamline, so Tomek Sobol will give a talk. It was scheduled at 12, but there will be some short delay. Okay, the next beamline, POLIX beamline. This beamline is designed for multimodal microimaging and microspectroscopy, and it operates in the range from 4 to 15 keV. So there are 3 available methods. We have X-ray microtomography with spatial resolution starting from 1 micrometers. So this imaging method gives information about the internal structure, about the internal structure of small or weak absorbing objects like biological samples, for example. So the second method, which is available at this beamline, this is X-ray microfluorescence imaging. And this technique is used to obtain maps of sample compositions. And the third technique, X-ray absorption spectroscopy. This is a method which we use when we want to study chemical phases which are present in samples, or we want to get information on local atomic structure. And I have prepared for you an example of the application of this beamline in agriculture research. We had a team from Warsaw, and they wanted to understand the mechanism driving zinc distribution in plant roots. So they wanted to understand how zinc moves through plant roots, especially when there is zinc heterogeneous soil. So it means there are some regions which are zinc sufficient and some regions which are zinc deficient, just like in nature. And to do this, they performed micro X-ray fluorescence map across the entire root system. And then they find out that under partial zinc deficiency, zinc is transferred between zinc sufficient and zinc deficient roots in the same plant. So it means that root supports not only the shoot, but also themselves. And in this way, adapt to the soil natural heterogeneity. Okay, so moving on. We are already at the Demeter beamline. This is again a soft X-ray energy beamline with the energy range from 100 to 2000 eV. And this is designed for X-ray microspectroscopy and dichroism investigations. I am sorry, I have some problems with my voice. So this is the only beamline at Solaris which has right now 2 branches. And at those 2 branches, we have 2 microscopes. So we have the PIM, photoemission microscope, and the STXM scanning transmission X-ray microscope. The PIM microscope probes, of course, only under UHV conditions surface. But with STXM, we can get information, we can get volume information under near and ambient conditions. And possible application for this beamline include chemical imaging, magnetic and electronic state imaging. Okay, I selected for you again a research which concerns spintronics applications. So we had a group of scientists from Poland and Italy, and they investigated thin layer systems to find a suitable materials for spintronic devices. So they studied nickel oxide layers, which were grown on varying thickness of magnesium oxide substrate. And additionally, they covered this nickel oxide layer by a ferromagnetic layer. And they discovered that when the thickness of magnesium oxide is getting bigger, the nickel oxide spins rotate from in-plane to out-of-plane orientation. And they also observed that ferromagnetic and antiferromagnetic coupling leads to the creation of a multiple domain structure in this nickel oxide thin films. So in other words, they found a way to tune the magnetic anisotropy in nickel oxide. And we have also a beamline which operates in a completely different energy range. This is the CERIC beamline. And the CERIC beamline is dedicated to spectroscopy and microscopy with infrared. And there are 3 techniques available. So we have FTIR microscopy, which is dedicated to sample mapping and imaging. Then we have SNOM, AFM-IR microscope. This microscope combines classical atomic force microscope with IR spectroscopy. And the spatial resolution of this method is about 20 nanometers. And finally, we have OPT-IR microscopy with 2 light sources. So we have a laser with a wavelength in the visible range and an infrared radiation source. And the spatial resolution of this method is specified by green laser wavelength. And typical application of this beamline. So we can classify tissues in biopsy. We can do biomedical imaging. We can also analyze the composition of polymeric and inorganic materials. And also possible is determination of hierarchical structure of macromolecules. And here I have very interesting research example. So this is application of this beamline in cancer research. And to be specific, this is pancreatic cancer. And as you know, diagnosing pancreatic cancer at an early stages is very difficult because this cancer does not show any characteristic symptoms. But our researchers from the CERIC beamline, they developed a method which involves IR imaging, which is combined with machine learning. And they were able to recognize pancreatic tissues and classify patient. So they collected really many FTIR images with a database of more than 670 millions, which is one of the biggest data set which was collected up to this time. And as I said at the beginning, we have also 2 cryo-electron microscopes. And we started, I think those microscopes, the first one was provided to users since 2019. And the users in the experiments, they can use single particle analysis, cryo-electron tomography, and also microcrystal electron diffractions. And the possible application of this infrastructure are determination of the spatial structure of macromolecules at nearly atomic resolution, and also imaging of cells and their fragments, viruses and bacteriophages, micelles and liposomes. So broad range of applications. Okay, so this part, which I presented up to now, this is part which is in operation. But we are also working on the new infrastructure. So we are building currently 3 new beamlines. So the first one, which I said at the beginning, the smoke beamline, will be dedicated to small angle X-ray scattering. And we have already the end station, the experimental hall, but we are waiting for the beam. The next beamline, that's gonna be area beamline, and it will be the first beamline dedicated to macromolecular crystallography at the SOLARIS Synhrotron. And this beamline will allow users to analyze the spatial structure of proteins, nucleic acids, and small molecules. And the third beamline, well known, I will not go into the details because we have today talk of Artem, and he will tell you all the details about this beamline. So far I know it should be ready at the end of 2027, beginning of 2028. And there are also other projects. So for example, the Felix beamline, which is already in operation, will be soon extended by a second branch with SNAP XPS end station, and should be also ready at the end of 2027. And we built also Operando end station. This will be a compatible setup with standard and hard X-ray, and it will be a movable setup. We also work on some complex laboratories for our users, and we started also construction works on a helium liquefier, and it should be ready in the second half of 2026. Okay, so we have infrastructure in operation, infrastructure under construction, and we have also dreams and plans, and now we are awaiting the decision regarding financing of 3 projects. So the first one that's gonna be ambient pressure hard X-ray photoelectron spectroscopy end station. The second one, beamline XRD XAS beamline for surface diffraction and scattering of hard X-rays. And the last one, HEROES beamline for high resolution tender and X-ray hard and X-ray spectroscopy. Okay, and this is my last slide. So I just want to tell you a few words about how can you get access to Solaris. So we have, if you are ready to publish your results, the access is free of charge. So we have 2 calls for standard and long-term proposal twice a year. And what Alexander Kordyuk already said before, we have this nephew project, and through this nephew project we can finance your access to Synhrotron Solaris. And there are also other possible ways. If you want to apply for beam time at Solaris, so as part of your expenses is covered, you can apply through CERIC or RIANA project. And just some statistics, some numbers. So up to now, we have more than 1,800 submitted proposals, more than 400 publications. 25% of our primary investigators are with foreign affiliation, and the success rate is 50%. And we have also 14 users from Ukraine. So they are measuring at Uranus, PIM, and Astra beamline. But you are all welcome, and we are really looking forward to your participation in experiment at Synhrotron. So thank you very much for your attention.
Thank you very much for very beautiful and nice overview about generally Solaris and possibilities of research. So we have probably time for 1-2 questions. So is there any questions? I think Luke wants to ask a question.
Yeah. Thank you, Ewa. Can you tell us what is the operations mode of Solaris? Is it working? Beam time is usually allocated per weeks, or do you have also machine days during the weeks, or how is it going?
Okay, so we have now 6 days of operations. So Mondays, these are machine days. But starting from Tuesday, we have beam time until Monday 8 a.m. So 6 days of operation.
Okay, good. And I don't know how to pronounce it. Smaug.
Smaug.
Okay, good. So you have the end stations, but what will be the source? It will be a bending magnet?
No, Wiggler.
Ah, it's a Wiggler.
Wait, no, I'm wrong, because that's gonna be for area beamline. And here, so just
I guess it's because bending magnet.
I will just check where it is.
Yeah. It's actually
because this is close to MAVKA. MAVKA is on undulator, and Smaug is on bending magnet. Yes, area will have Wiggler.
Okay. Good. Okay, so I just was confused if it's actually because you have the end station from Smaug.
Yes, this is completely new station. It's standing already in the hall, in experimental hall, with laboratory sources. We can perform already experiments, but yeah, this part is missing.
Okay, thanks.
We have to build beamline.
Yeah.
I may have a short question about XAS and XRG beamline. So it will be what would be? It will be hard X-ray.
Yes.
And what would be the source? And it's probably.
So the source will be bending magnet.
Also, okay.
Because we have area next to it. Yes, in this sector, and the area will be on Wiggler, so we have here that's gonna be a bending magnet source.
And what is the purpose? It will be probably still at the design phase, but what would be the beam size? It will be more like macro X-ray absorption diffraction.
Okay, I don't know the details about the beam spot size. Yeah, it will be designed to surface this diffraction and scattering of hard X-rays. But I'm sorry, I don't know the details.
No, that's fine. That's what basically I wanted to know. Thank you.
We applied for financing. We'll see whether we get it or not.
Thank you. So then, if there is no more questions, I think we should move forward to the next speaker, which would introduce us the MAVKA beamline, Ukrainian beamline as a SOLARIS, which is a cooperative project led by LIPS, and one of local coordinator in SOLARIS, Dr. Artem Yakovlev, would present the story.
Hello, could you confirm if you can hear me well?
Yes.
Okay, so I apologize in advance for my voice. Unfortunately, I'd gotten sick, but hopefully it will be fine. So I will talk today about the MAVKA beamline, which is being built at the SOLARIS Synchrotron. My main place of work is Institute of Nuclear Physics at Krakow, but part-time I'm involved in the MAVKA project with SOLARIS Synchrotron. So I will not stay here for a long time on this slide because I believe people gave already introduction about Light for Ukraine initiative. I will just note that somewhere before 2023, the Ukrainian beamline SOLARIS was proposed. And then Professor Luc Patthey, who gave presentation day earlier, he made a very nice feasibility study, and he confirmed that such a beamline can be built with undulator source donated by SLS. And later, can you also get my pointer, excuse me? So later, last year, we had our community established and our first workshop where this beamline was introduced to the public. And in June this year, we had a very nice workshop at SOLARIS with members from PSI, from DESI, from Ukrainian community, where we discussed some details regarding this construction of this beamline. So I believe vast majority of people know what MAVKA is, but for people who don't, I will just give a very short introduction. So at the beginning of this year, we decided to call the beamline MAVKA, and MAVKA is kind of a forest spirit which comes from Ukrainian folklore. She is also present in many classical Ukrainian literature works. So most of kids know it from like literature classes at school. And it's often associated with spring and nature rejuvenation. So we hope that this beamline will be kind of a symbol of Ukrainian science reconstruction and renovation, because at many places it was completely destroyed and heavily damaged by ongoing war. So the funding for the beamline was estimated around 6 million euros. So thanks for the efforts of PSI and specifically Luc Patthey, the Swiss National Foundation granted 1.5 million Swiss francs. So this money will go, majority of this money will go to the front end construction for the beamline, but also for the staff salary and some optical components. So also because SLS is now undergoing the upgrade, it has some, it offered some things as a donation for construction of this beamline. Specifically, it's the big parts are undulator, bendable toroidal mirror, and monochromator. And also this list is not finished because, for example, we are talking about slits, hatch, and other things which we can reuse from SLS upgrade. So this value of 1 million in-kind contribution is growing. And other side, the Solaris side will cover all the operational expenses and support for this beamline, for the construction and operation of the beamline. So on this slide, there is like main members of a team, but of course, like I put here extended team because all the departments from Solaris, PSI, and other institutions are working together on this project. So I am the coordinator at Solaris. Dr. Anna Vach is responsible for one of the end stations which we plan to put on this beamline. And also Marcin Zayants and Marcin Shikora are people who oversee the construction of the beamline from Solaris side. Also from PSI side, Luc Patthey is a project leader and Danylo Babich is a project coordinator. Also, we have now full-time employed engineer which helps us with the design of the beamline. And from Ukrainian side, Professor Kordyuk is our main contact from the Academy of Sciences, but other members of the community are involved. And I will just add here that we have initiative from DAISY and two help centra from Germany who are preparing a grant proposal, which might support the construction of end stations on the beamline. And also we have discussions with other institutions. For example, recently we had discussion with Trieste, with Synchrotron in Trieste. They offered for us some components because they're also undergoing an upgrade. So the legal framework, after a very long discussion of what is the best way to build such a beamline, we come up with such a structure where all the equipment is donated to the Solaris Synchrotron. And Solaris Synchrotron, together with NASU, they sign the agreement that once this beamline will be completely constructed, that ownership will be transferred to the National Academy of Sciences, to the institutions of the Academy of Sciences, because the Academy cannot own it by itself. So we don't know which institution it will be, but I believe it will be decided later. And under this agreement, Solaris will cover all the operational expenses and also majority of the staff at MAVKA beamline. But NASU receives exclusive use of 25% of the beam time at this beamline. So now something about technical details. So Eva already gave short introduction. MAVKA will be built on this part of the storage ring in the new hall. So here how it looks like from inside, and this hall is very helpful because it's long and we will have this length of the beam line will allow us to focus the beam to the micrometer size range. And here is just a very illustrative layout of the beamline. So it will have an undulator as a source, then front end, which is now being produced by the SLS. We will have the first bendable toroidal mirror and monochromator, and at the end we will have KB system, which will focus the beam, but this KB system, we don't have it yet, and design is in development. So main parameters of the beamline are source, as I mentioned, is U19, which will be donated by SLS. Front end is also will be similar to, actually almost the same as front end for SLS 2.0 upgrade. The photon range we expect from 0.5 to 9 kiloelectron volts. But here you can see that unfortunately we will have most probably we will have a gap, and we will have to use the even harmonics to cover the whole range. Photon flux at the sample we expect to be from 10 to 10 to 10 to 12 photons per second. And the beam size, we don't have the exact ray tracing, of course, yet, but we expect it to be in the range of 10 micrometers. And this spectrum is the minimum gap of 6 millimeters of the undulator, which are now allowed, which accelerator group from Solaris allowed us to have for now. But in principle, if Solaris can in future approve the beam dynamics, and if everything goes smooth, the best spectrum which we possibly can have is this minimum gap of this undulator, which is 4.2 millimeters, and spectrum will look like this. But this result is already great because this energy range is quite unique for Solaris. So here you can see energy ranges for all the beamlines, and the only complementary beamline would be Astra beamline, which has range from 1 to 15 kiloelectron volts. But it's quite different because Astra is a bending magnet source and unfocused source, and MAVKA will be focused and with higher intensity because of the insertion device and undulator. So currently we plan to have 2 end stations at the beamline. So first one is under development. It will be a micro SAS X-ray absorption and XPS beamline. And the second one is being designed by Dr. Anna Vach from Solaris. It's AP-HAXPES, or ambient pressure hard X-ray emission spectroscopy. So proposal for this end station is submitted, and we await the result from the Polish Ministry of Sciences and Higher Education. So hopefully it will be funded and it will be constructed at the MAVKA beamline. So the briefly timeline of this of the construction of the beamline. Now we are in design stage. We already started production of PSI already started production of some components, and we expect production to finish before 2027, where we can deliver all the components to the Solaris and start the installation. And optimistically, commissioning and first experiments we expect at the end of 2027. And of course, there are a lot of challenges associated with this project. For example, as I mentioned, the ownership structure is quite difficult because, like, beamline is situated in the European Union, but Ukraine is not part of EU, so we will have to navigate all these legal fields. And project still requires quite a lot of funding. So I mentioned the Swiss Foundation and donations, but still around 3 to 4 million euros in funds or equipment are necessary to finish the beamline. Also, I believe we lack human resources, so we need more people working on this project. Also, there are some technical details which I will not go into the detail with. Little about. We have prepared this list of work packages of the things which equipment and support which we need for the beamline. So there are some like urgent parts, like for example, one of the complications is that like front end and undulator from SLS, they use different control systems, EPICs, and Solaris uses Tango control, so all the software has to be translated to Tango, and so on. And if you can help, or you know someone who can help with with extraction of the beamline, you can contact me at Solaris or Danylo Babich at PSI. And in conclusion, some more optimistic things. So I believe that legal framework will be finalized by the end of this year. Front-end production has already been started, and also the calculations, reagent-stated calculations for the front-end are almost finished. So we expect that undulator will be delivered to Solaris in the second quarter of 2026, and installation of undulator and front-end we hope will be done in the beginning of 2027. And of course, I want to acknowledge the donations from the Swiss National Science Foundation, from PSI, also support from the Polish Ministry of Higher Science and Education, and all the LIPS members and other institutions and facilities who expressed willingness to support this project. Thank you a lot for your attention, and questions welcome.
Thank you very much, Artem, for introducing us a Ukrainian beamline, which will hopefully be built at Solaris. And we have time for 1-2 questions. If there is some questions from audience. Okay, then probably we should move forward. And the next speaker will be Dr. Tomasz Sobol, which
Hello.
would...
Luke has some question? I am...
No,
I congratulate you for the talk.
Okay, thanks a lot.
So the next speaker would be Dr. Tomasz Sobol, who would present about another beamline at Solaris, and it will be the Felix beamline, and we are looking forward for a presentation.
Yeah, hello everyone. Can you see and you can hear me?
Yes.
Okay, perfect. Perfect. Yeah, so I'm Tomasz Sobol. I'm responsible for the Felix beamline, for the operation of the Felix beamline at Solaris. This is the photoemission, photoemission and the X-ray absorption spectroscopy beamline, which is operating in the South X-ray range. So here I bet you know where the Krakow is. So it is the southern part of the Poland. So it's quite fairly close to Czechia, Slovakia, and Ukrainian border. So here is the Solaris' place. This you already see at the Eva's presentation. So I will not say you how this ring is really occupied by different beamlines, but here I just want to tell you fun fact. So about the Felix beamline. So when you are entering the experimental hall, so here is the enter, here is the enter for the experimental hall. First picture that you ever do, or you ever take in the Solaris will be containing, you know, Felix beamline, because this is the first facility, first beamline that you will be see when entering the Solaris experimental hall. We are built on the 6th bending magnet section, but we are not using the bending magnet radiation, but we are using the undulator source, Apple II. We are operating in the soft X-ray range, so our mirrors and gratings are conduct from the silicon, which are covered with the gold. We are using the plane grating monochromator setup with 3 different gratings with the three different numbers of lines, 600, 800, and 1,200 lines per millimeter. Right now, we're mostly operating with this middle one, the 800 lines per millimeter, because of the best energy resolution and the intensity ratio. Our beamline is prepared to already prepared, like half of the beamline is already prepared to introduce the second branch, which maybe I will talk a little bit at the end of this presentation, which already is in the construction, period. But now, yeah, here is we're also using this refocusing mirror to refocus the beam at the end station, the Felix end station. Okay, so here are the parameters. Yeah, we are using ondulator Apple 2. We are operating is quite wide energy range from 40 to 2000 electron volts. It's for us, it was very important to a little bit extend this range because I think 3 years ago, this range was a little bit narrower. But now, because because of the battery, really this battery science, and because of the scientists want to do a lot of absorption spectroscopy on the lithium cage. We have to extend it also the range, or just commissioning the beamline for this lower energy range to also be able to measure the Lithuanian absorption edge. So that's why we almost start from the UV, but we are mostly operating in the soft X-ray range. The beam size is around 60 per 100 micrometers, so it's good enough for most of the case studies. That one of the cases. Because of the ondulator, we have access to almost all polarizations. So we have both linear, horizontal, and vertical. Circular for the first harmonic, and for the higher harmonics, we're using the elliptical, this circular elliptical left and right. So we can do these dichroic studies, electronical structure dichroic studies. Beamline team. So I'm the coordinator of the Felix beamline. Edita and Barbara, they are working with me as a beamline scientist at the Felix beamline and this branch. And Agata Sabig is our new member, which is developing and running the near ambient pressure project. Running this project. Okay, so here is the view. From top view, from picture view of our end station, how it looks like. It's quite complicated, but I will explain you everything in a few moments. But first, I just want to introduce you this effect that we really measure, the effects and the process which we are focused on. So in general, as I bet almost all synchrotron methods, we are measuring, we are studying how the light interact with the sample, with the materials. In our case, it's mostly the solid state. Sometimes we can also measure the organic materials, but yeah, mostly we are measuring the solid state, metals, semiconductors. And what we are really focused on, we are focused on the photoelectric effect. And what that means, so if you are illuminating your sample, surface of a sample with the light, especially with the UV or X-rays. So in general, in neural laboratory, you can just use the UV lamp or X-ray lamp. But here in the synchrotron, because we have access to almost, a very wide spectra of the electromagnetic wave, so we can use, for example, both, even in one experiment. If you illuminate it with this with this light, you can emit. The sample can emit. They have emit photoelectrons, and we know exactly what is the photon energy that we are introducing into our sample surface. So in general, if you want to measuring the photoelectric effect, the photoelectrons, we have to introduce the light with the EV or kilo electron or the kilo electron volt and energy range, because these energies allow electrons to be emitted from the sample surface. And And later, these photoelectrons have a certain kinetic energy. And if we are measuring this kinetic energy, these techniques are called photoelectron spectroscopy. And this is what we mostly do at our beamlines, so measuring really this kinetic energy. But what we can else do, we can also measure the drain current of the samples. So in general, this is some kind of secondary effect that is also happening during the illumination of the X-rays. So and we can measure just the drain current of your samples. And this is sort of the X-ray absorption spectroscopy technique. I will not really go into this X-ray absorption spectroscopy here, but in general, what you can do in our beamline, you can measure both techniques, both methods from the same sample, from the same spot on the sample. So you don't have to rotate anything. First, you can, for example, conduct the photoelectron spectroscopy measurement. Then you can just quickly change to this absorption spectroscopy and measure it from the same sample, from the sample position. You can measure both. What really information we get from the photoelectron spectroscopy? Here we have the atom, like very simplistic view of the atoms, and as we know, all the electrons that are around the core of the atom have some quantum number labels, 1s, 2s, 2p. Here on the oxygen, this electronic structure is look like that, and in general, you can split this electronic structure, and you can split it to you have these core electrons to the core electrons, where are very tightly bound with the core of the atom, and valence electrons, which are a little bit not so attracted to the core of the atom. And in general, if you could be able to gain information, like eject these electrons from these orbitals, from these orbits, you can really get the information about the chemical state of your sample, of their material, of the element, how the element is building your material. But if you want to measure the electrical properties or bonding character in your material, you have to get information from these weakly bound electrons, which you call valence electrons. And what is very important, these electrons have different binding energies. And these binding energies is related to the Z number. And Z number is the proton number, right? So this is like very heavily, it's related to the whole atom, the whole element. And because of this formula, we can use the photoelectron spectroscopy to really distinguish the elements that are binding our materials, because even if the electrons occupy the same orbitals in the different elements, still the binding energy is different because Z is different, right? So this is a very important thing. And the main formula that has driven this process is this one, when the kinetic energy is equal to the photon energy, so this UV or X-ray, X-ray light, and here is the binding energy, and here is sort of the potential. This is called the work function. In general, it's the energy from which the electrons start to be emitted from the material. This is sort of the related to the material that we are using, that you are want to examine. And here is this the formula that is driving this process. So in general, when you can measure the kinetic energy, you know the photon energy, you know the binding energy. And that's how we're measuring really the photoelectron spectroscopy. This is like general idea what is behind this process and this technique. But okay, here this is the sort of the example how the spectra, like this spectra, photoelectron photoemission spectra looks like. So in general, you can see here they have different labels of these levels, 3P, 3D, 1S, from the different materials, and you can very easily distinguish these different energy levels from the different elements in this technique. Now, but from like, I don't know, 20, 30 years right now, the detectors also allow us to measure the emission current. Not the angle, the emission angle. So electrons are, emitted from the material, not really like they can be emitted in the various angles, and now detectors can also measure in this angle. So in general, we can just accept certain photoelectrons with the certain emission angle, and with the formula, with this formula, we can really combine the kinetic energy, this emission angle, with the wave vector. So in general, we have access to measure sort of the dispersion relation. So the relation between the kinetic energy and the momentum of the electron. And it's very important for these electrical properties from the semiconductor materials, these new novel materials, novel topological materials, when you can really gain access to this very high result valence band measurement. And this technique, which combining this measuring kinetic energy and emission angle, later this combined with this momentum, we called angle result photoelectron spectroscopy, ARPES. And here is I think it's from my PhD. So this is the bismuth 2 telluride 3 material, this topological material. So you can measure really the dispersion relation in these materials. This is how the valence band looks like in this mode, in this ARPES mode. Okay. What else here? What elements you can really measure at the Felix? So in case of the photoemission, almost every element can be measured. But from the absorption spectroscopy point of view, we have access to only few edges. So here, yeah, because when you're illuminating the sample with certain energy of the light, you have access to the different absorption edges. So it's different electrons which are different combined with the atom, with the core. So they can give us information about the different edges. So K edges we can measure from the lithium to silicon, the LH until the bromium, and M edges until the ytterbium and lutetium. So here in the Felix, you can really measure a lot of elements, not only with this photoemission or photoelectron spectroscopy, but also with the absorption spectroscopy. Okay, so how the end station looks like? End station is quite not so easy. Here is the analysis chamber. So here you putting the sample in, and here is the hemispherical analyzer. But also what we can do here, what we are having here is the preparation chambers. We have two preparation chambers where you can really prepare your samples. Sometimes you are not able to transfer your very clean surfaces of your sample in for example in air, or even you don't, or for example you don't have the vacuum suitcases. So you can sort of produce your samples inside these chambers. Of course, sometimes you only doing part of the preparation here. Sometimes you do all the preparation here, but in general, you can do it at this beamline. So here is a low log. Here is two preparation chamber. Here's the analysis chamber. In the preparation chamber, what the parameters are in this two prep chambers. So in general, the base pressure is something around 2 to -10 millibars. We have in this main prep chamber, we also have the lead. So in general, you can measure the diffraction pattern of the electrons and the surface quality of your sample. Here, this big one is the this MBE chamber. So it's a fuse. You can just evaporate materials inside this chamber. We have permanently there installed tin, cobalt, and iron. But you can also bring your own stuff, your own fusion cells or electron cells, and you can install it, because we have 2 free ports when you can install your own your own cells. You can dose the gas. In this chamber, we try to limit this, but for this Gauss dosing and the reaction at the surface with this different atmospheric pressure, the different pressure, we have this second preparation chambers, and you can dose up to like 10 to -5 millibars. You can spatter your materials, and you can anneal. We can prepare tungsten here. So in general, we can anneal up to above 2000 kelvins. Also, what you can do, you can cool down. So it's around 100, 120 kelvins. You can also cool down your sample during these preparation steps. And you can cleave here also. What is the analysis station? So we are using the SPECS. POIBOS 225, so this is a big one, the big hemisphere with the deflector system. So it's very the deflector system, we have 6-axis manipulator and it's working very well. In general, this is very important for the ARPES studies, right? Because you have access to all three angles, the polar, tilde, and the azimuth. So it's very important to be sure that you are measuring the correct axis when in the ARPES mode. So, and this is working very nice now. In case of the photoelectron spectroscopy, we're measuring the XPS and ARPES, which I was talking about, and also spin ARPES, but the spin ARPES is, right now, it's my pain. It's my pain, so if someone asks me, maybe after the presentation, I can answer this question about the spin ARPES, because I have one slide at the end, but in general, it's pain because this detector is very hard to commission and very hard to measure right now. It is very hard to measure with it right now. But in general, yeah, it's also attached to our analysis chamber. In case of absorption spectroscopy, we measure the electron yield, fluorescence yield, and the partial electron yield. Because of we can combine these two techniques, photoelectron spectroscopy and absorption spectroscopy, we also can measure the resonance photoemission. Access to the all polarization give rise to the circular dichroism effects in both methods, and also, yeah, we are measuring. We can cool down the manipulator, like cool down to this liquid helium regime. Okay, so sample. We have, we are using Omicron flux style holders because, yeah, we are ultra high vacuum. We are ultra high vacuum system. So the samples are fairly small. So maximum size is around 10 millimeters. But in general, yeah, it's enough to carry out these measurements. So here you have few examples. So here you have like huge copper crystal that you can measure, or do some kind of preparation on the top of this crystal and then measure it after this in situ preparation. And here you have very fun stuff, because here I think it's something like 7 per 7 millimeters square, and there is a 16 samples. There is a 16 different gratings that are, the one group prepared. And in general, the these small beam spot size allow you to measure all 16 of these samples, like installed on the one flux style. Yeah, we are ultra high vacuum, so in general, we're measuring the solid system. Sometimes when we prepare it very well and with the great care, we can also measure some sort of organics, but still it must be dry somehow. And because we are using the photoelectron spectroscopy and the absorption spectroscopy in general, it will be very, very good, and the sample will be conductive. For measuring, we're using the SPECS Lab Prodigy. So in general, we don't have any like in-house software for now. So we are just using this commercial one. SPECS Lab, but it's working okay. So here is the example. I think it's the tungsten selenide sample. And it's the Fermi level of Fermi level, or this on the valence band of this material. And because of the deflector system, we can because in our case we're using the deflector system, so in our case it's very easy and fairly fast to measure whole Fermi level in like 5 minutes or below 5 minutes. So this, I don't know, we measure this, maybe we take more, because I can see that the resolution is okay and the intensity is also it's okay, but in general, this sort of the measurement, valence band measurements, taking like from 5 to 15 minutes. This kind of measurement right now. Typical energy step is from 10 to 100 millielectron volts. It also depend on the sample quality and the temperature of the sample. So it's up to the user, but in general, yeah, this is the range that we are using for the PES experiment. Angular step is something, yeah, the resolution is 0.1 degree, but it's also up to the sample. Data format, yeah, so you can save your data in these formats. Now we are working also on this to help user with analyzing the data. And we are working on the software which helps users to analyze the data. And I think the first version of the software is both for the absorption spectroscopy and the photoemission ARPES spectroscopy. ARPES will be will be introduced to the users from the next year. Here are a few examples that are already published from our beamline. So here, for example, you have the example of the circular dichroic angle resolved measurement. The guys from the ULISH, from the Germany, they study, I think, tungsten selenide and telluride, platinum telluride, and how is the orbital character of these bands that are very near to the Fermi level. And in our case, it's also very good and very convenient because first harmonic, so these very low energies, the photon energies that are producing from the undulator, the intensity from the linear, horizontal, and the vertical is almost the same, but also is very high for the circular left and right. And in general, this dichroic, circular dichroic, this orbital angular momentum effect, you can measure very, very fast because of this very high intensity of this linear vertical and the horizontal, and but also for the because of the very intense light in this circular regime is also very fast. Yeah, you can do it quite fastly. Here is the next example. Here is the example how you can combine absorption spectroscopy in the photoemission spectroscopy to measure nanomaterials. So here we have some of the example of the core shell materials. So in general, nanomaterials. So these materials are built from like different layers of these different layers of materials. In general, the question was this group from the Gdańsk University have this question that these materials of the layers of the materials are like, you know, they have some these layers are like sort of the they have regular composition of the elements, or sort of mix. These layers are mixed with the different elements, and with this problem they came to us. And in general, by combination of the photoelectron spectroscopy and absorption spectroscopy, and also because of changing energy, the photon energy in the photoelectron spectroscopy, they was allowed to really resolve this composition of the layered systems. And in general, they came up with sort of the mosaic structure of the layers of your core shell nanostructures that they are producing in their lab. So in general, by combining the techniques, you can also get the information from the different parts of your surface, and you can distinguish what is really at the very top of your material and what is like few nanometers down. It's a little bit deeper. What is the chemical composition, and then what are the properties of these different layered materials. And here is another example. Here is the sort of the the solar cell materials, and the guys from the Germany, they make also. They were very interesting. What is really happening on the interface between the perovskite material and the substrate, which was the titanium dioxide, and they have sort of the organic material in between, and they want to figure out what is really going on in this interface. So they measure it, the photoelectron spectroscopy, in two different energies. So the kinetic energies varies of these core levels, and then because of it, and they were able to say what is really going on here inside this interface. What really the chemistry is there, and what type of the bonding character is there. Okay, and they also combine it with the absorption spectroscopy studies. Here is the sort of something new that I am trying to develop at the beamline. So to focus a little bit more on this high energy RPS. Here is the example that I don't know, I collect this data like last year. I was just trying to check out that the system, this geometry is good enough to measure it, this angle resolve for a little bit higher kinetic energies, for a little bit higher photon energies. And it turns out it was fairly okay. Of course, it's not perfect. There are better beamlines, then you can do it. But in general, as you can see, You can also measuring this electronic structure, the ones about the electronic structure, the higher kinetic energies here. But this is something this is ongoing. So this is something that I try to develop and understand more. And this is sort of the future of the beamline. Okay, so at the end, yeah, so the summary is that we can really conduct the photoelectron spectroscopy, astrophoton spectroscopy experiments in other Felix. And what is really the case now? Yeah, is what is really the new is the end station that will be installed here on the second branch. We'll be installing Arben pressured XPS. So in general, we will be able to conduct the photoelectron spectroscopy experiment not in the ultra high vacuum, but in the ambient pressure conditions like 1 millibar, 10 millibars in this sort of conditions. So in general, you can really measure this in situ reaction on the surface. You know, you can do you will be able to measure it during this time, during this process. Thank you for your attention.
Thank you very much for the wonderful talk, and I guess there is few questions from audience.
Oh yeah, okay.
At least two, and mine will be
perfect.
So Luke was first who put it, so please.
Tomek, sorry.
Yes.
I understood your message. We have to ask you the question. What's the issue with the spin detector?
Yes.
Is
Okay.
it a commercial versions or it's a?
Yeah, it's a commercial. It's a Ferrum one. It's a Ferrum one. So
okay.
In general, I heard there are few are working.
Yeah.
And I think this one is the Max Lab. Now we have the second one here also at the Uranus beamline.
Yeah.
Which is operation, but this is the different geometry. We are using the one with the rotator. And I don't know that this rotator, it's tricky machine. So in general, you can rotate the vector, the spin, like before before introducing really the photoelectron on the detector system, and that is very tricky. And I think, we are trying to working on it. Working on it, but in general, it's very time consuming. It's very, it's very hungry for the beam time.
So and this is not a problem of the detector. This is actually a problem of the transmission.
Yes,
because you rotate your detector around this axis.
I would say I was a little bit angry because at some point, because I spent a lot of time to commissioning this detector, and at the end, after 1 year, it turns out that the power supply was broken. Right, because it's very hard sometimes to notice these strange behaviors of these power supplies, and that's why I was saying that this is a pain. But in general, at the end, I can show you this last slide. This is the last slide, and here is the room temperature measurement of this tungsten selenide, and this is normal ARPES that you see right now, right? This normal ARPES, and you can convert this signal, for example, this one, to the spin detector, and this is the signal from the spin detector, and this is really the data from the spin detector. It's still not spin resolved, but I just want to check how you can really, go through from the ARPES to the spin, and it's fairly okay, right? It's looking more or less the same, and because this material have this the spin polarization out of plane. And in our case, it's a little bit easier to measure because then we don't have to use the rotator, this rotator thing, because we don't have to use it. And there is a spin asymmetry, okay? But for the most of the materials you have, for a lot of the materials, the spin polarization is in plane, right? Is in plane for example, topological insulators. And then we have to use the rotator. And in general, everything doubles because you have to measure not 2 times, but 4 times. Then you have to do this, all the math. Then you have to do this all the math. And in general, it's for me, when I was trying to do it, it was always like asymmetry at the level of 1% or stuff like that. Even if the spectra looks okay, the asymmetry was like, lost somewhere, somehow. And for the, out of plane, I was able to measure. And this is the example from this beginning of this year that they are seeing here. But for this in plane is terrible. because I think I don't understand it fully. And, you know, because, but I was feeling that at some point we are start losing the beam time because we want to try to, you know, resolve this problem. And for me, it was too much because everything is working, like, you know, the preparation stage, the photo emission, the RPS, the XPS, the absorption spectroscopy, everything was working, everything was happy at some point. And for me, it was like a little bit waste of the beam time to measure for like 5 or 6 or 7 days the same spectra all over and over, just with the slightly change of the parameters of the column, you know, this spin detector column, and every time gets even worse and worse data. And of course, we still committed to this, you know, topic, but I limited this commissioning time for this spin detector. So every call we have 1 week, maybe 1.5 week, when sometimes we invite other guys to help. Like Łukasz Plucinski, I don't know, maybe you know him, but he's our like consultant in this case. And, you know, we have some new ideas. We have the idea what sample is good, what sample is bad, you know, stuff like that. So in general, we have the progress, but it's still ongoing.
Okay, good, thanks.
And there is another question from Professor Alexander Kordyuk.
Yeah, so thank you for excellent overview. Yeah, I have several questions, but to make it short, maybe on the slide 12, the shortest, what is most interesting for me, it is annealing system. What is the source of heat?
Okay. So I didn't show it, but in general, you installing your sample on the flux tile, right? But we don't really use the manipulators with the annealing system on it. But we are using sort of the different type of the packs that you first introducing onto the pack. You're introducing the flux tile, and then this whole pack goes to the vacuum chamber to, for example, the load lock. And on these packs, on these PTS holders, you have different types of annealing system, like EB, resistive one. You have only packs for transferring. So in general, we have inside these packs, for example, EB, when you can anneal with the electrons, right? From below. And in general, we try to avoid annealing because only manipulator that we have with the annealing system is the one that we measuring on, right? So in this analysis chamber, because for example, you can manipulate with the sample temperature in the narrower range, but still you can do it. But in the prep chambers, we're using these packs, so different types of the holder, but still very well combined with the flux tiles. So you don't have to remove the sample from the flux tile, but they are really combined. But they are combined.
But can you anneal it and then measure RPS, right?
Yes, exactly. So we have the groups that preparing tungsten, then try to evaporate something on the tungsten and do those sort of, you know, the reaction on the tungsten, and it's working perfectly.
Good, interesting. Yeah, I'm interested because we are interested to do this in the same in our
So
future chamber.
So in general, there is a lot of groups that are coming here, even with the vacuum suitcases, right? So they have the substrates transferred in the ultra high vacuum. They transfer it to our prep chambers, do this in situ, you know, monolayer or sort of the reaction on the surface, and then introduce it to the analysis. So it's
okay, interesting. And just short about the last slide of where you shown gold at different energies. It is what the scale is quite big. So this thin stuff, it's not a surface state, right?
No. This is not the surface state. This is some sort of the bulk state.
It's not possible.
This is So in general, if you measuring with the UV, right, and you are focusing on this surface state of the gold, you don't even see this state, right? This one, right? Because the surface state is like here, somewhere here.
Good.
So in general,
Okay, thank you. Very interesting.
If there any know any more questions from the audience, but I see some people who would be interested in our path in the audience, but probably they will ask question later. I have a very
We have a question.
okay, please.
Raise the hand, but I turned on the mic.
Hey, one short question. You showed this spin polarized detector and the spectra of tungsten telluride, something like that. And
tungsten, right? Yeah.
It was recorded at the room temperature, and
yeah.
So the spin polarized part, just the regular this from surface and bond structures. I mean, to me, it looks surprisingly excellent quality for the room temperature. What is the reason behind such good contrast, good data overall? It's just like
this is the sample. This is the sample because if you prepare it well, and because you can scan with the very small beam size, right? Beam spot, and you can find this flake that is. I can even in the room temperature. This is like very fast scan. This one, for example, this one is very fast. Like this is taking like 2 or 3 minutes. I just was checking roughly where I am, and in general, this detector, this specs, this Phoibos 225 with the deflector system allows you with this great resolution, the angle resolution and the energy resolution allows you for the very good samples to be so sharp. I mean, this is not. I mean, yeah, we have sharper spectra with the room temperature, but you know, then the sample is the limit, I believe. And we are preparing. If you are prepared well in the ultra high vacuum, so it's clean, right? You can, for example, exfoliate, evaporate, and you know, yeah.
Okay, thanks a lot. I guess that should be. I also have some questions, but we should probably.
You can always, you know, send me an emails.
Yeah.
You can find it
anyway.
Yeah. But you can find my email on the website. So don't hesitate. Contact me if you are interested.
Yeah, thank you very much. It's very interesting beamline, and somehow probably MAVKA beamline would be extension of such beamline in spectral range.
Yes, definitely.
If there will be XPS and absorption in the same state.
Perfect.
So thank you very much, and we now
thank
have
you
in break for I would say 40 minutes, and we start next session at let me say at 2:30 Ukrainian time and 1:30 European time. And thank you very much for all of your attention, and I guess students can have some food at the Faculty of Physics. See you soon.
Hi, Andrew.
Basha, hi, how are you doing?
Yeah, good, thanks.
Good to see you.
Nice you're here.
Yeah, well, great to join you. Thanks for the invite. I really appreciate this. And one day I will, you know, we've had these discussions with Zoya Petrenko about.
Yeah, you say it and she say it, and actually.
We haven't found a date yet, but at the very least, we hope to come over to Lviv to meet up on Ukrainian soil. So it's Zoya's probably very busy at the moment. Maybe after this, I'll send her another gentle message saying I don't want to push her because I'm sure she's got many things to think about.
Yeah, actually, I also was extremely busy these days. I actually now returned. I think we can start. No, not you.
You still have 1 minute.
Okay.
Danylo, hi. Hey, how do you want to do this? Do I just share my screen?
Yes.
Yeah. Okay. So let me just make sure, you know, it's the usual problem with Zoom. You've got a million windows open and you've got to try and find the right one to share. So maybe should I do that? Is that the good thing to do?
Yes, if you can try.
So somewhere out there, oh my goodness, sorry.
Just
it might help if I was actually, yeah, here we go. I think this is the...
You're supposed to have all the rights to start the presentation without interference from a high from Kyiv.
So you should be able to present it. I'm not sure.
Okay, let me just... so can you see my screen? Oh, no, because I'm not sharing it yet. You can't see my screen. Let me just get back to Zoom. Bother. So how does that look?
Yeah, now we can see your screen and your presentation.
And it's in display mode, is it?
No, it's perfect. So it's basically full screen. So we can see.
Super. So do I start?
Yeah, so let me introduce.
Okay,
so
Danylo,
just after 40 minutes break of intense session, now we are moving towards more collaboration, scientific collaboration session block, which will be related to connecting Ukrainian science to European research infrastructure. And first talk would be, we are very glad to have Professor Andrew Harrison, former director of Diamond Light Source, a very related person to Synhrotron research, and currently he is a director or head of CERIC, and this organization is celebrating 10 years of scientific excellence, and we are looking forward for your presentation. Thank you very much.
Danylo, thank you, and thank you very much for the opportunity to engage with the research community in Ukraine. I should say, originally I was actually a scientist as well. I've become a director and a manager, and spend more of my time talking about budgets and science. But once upon a time, I was a materials chemist. I would use synchrotrons and neutron facilities and microscope facilities to look at my materials. And one of the challenges was, if you wanted to use different techniques, you'd have to make different applications to these facilities. And sometimes you were successful and sometimes you were not. So if you needed to use, say, 3 techniques, it might take you a year or 2 to get access to all 3 techniques. And a fundamental philosophy for CERIC, which is very much open to your community, and I'll come to that at the moment, is that we provide a single point of access to a collection of very high-end facilities based in Central and Southeast Europe. So CERIC is the Central European Research Infrastructure Consortium, and we serve a wide range of techniques, from hardcore materials science and condensed matter physics, which is very close to the hearts of many of you here, all the way through to cultural heritage and the life sciences. So CERIC has 8 member countries: Austria, Croatia, Czech Republic, Hungary, Italy, Poland, Romania, and Slovenia. And they each offer, as a contribution in kind, one of their research facilities. And between them, they offer 60 different instruments across Central and Eastern Europe. So we just quickly go through what those are, and I'm going to broaden the focus in a moment to a range of other facilities. So if we go through those facilities in alphabetic order of country, then in Austria, with the Technical University of Graz, we have expertise, but also very high-end instrumentation in small angle X-ray scattering, both in the lab and at the electrosynchrotron in Italy. So that's actually where I'm sitting at the moment. And they have light scattering techniques as well. But also what's important in this and other cases is they provide support laboratories to help prepare samples and in some cases analyze the data. In Croatia, we have access to the ion beam facility in the Ruja Boskovic Institute in Zagreb. So they have an ion source, a 5 megavolt tandem accelerator ion source, which is in the process of being upgraded with associated facilities for analysis. So they've got time of flight, secondary ion mass spec, they've got particle-induced X-ray emission spectroscopy for elemental analysis, and so forth. So a wide range, and they can also irradiate and implant ions in samples. In the Czech Republic, the partner facility there is, first of all, a support laboratory for surface science at Charles University, where they have a range of instrumentation to look at the chemistry and structure of surfaces, mostly by techniques like ESCA. But they have an X-ray photoelectron spectroscopy beamline also at the Electrosynchrotron. In Hungary, we have the partner in the form of the Neutron Scattering Center in Budapest, the Budapest Neutron Center, and they offer a high-intensity neutron source that then feeds a range of instrumentations for neutron diffraction, spectroscopy, imaging, irradiation, and activation analysis. And then the other 4 facilities include 2 synchrotrons. So right beside me, I can see it through the window here, is the Electrosynchrotron, which is in the process of being upgraded. So they're going to increase their brilliance by a factor of about 100 by the end of next year, when they have a major upgrade of their machine. And that will bring back on stream a range of really European leading instruments in diffraction spectroscopy and imaging, plus a complementary cryo-EM facility. The other synchrotron we have is in Poland at Krakow. And for those of you who are not familiar with SOLARIS, this is a relatively young synchrotron, but it's going through a really steep rise in capability and capacity of its instruments. It's, I think in the last 2 or 3 years, they practically doubled the number of instruments they offer to the user community. Very impressive growth there. Romania, in Magurele, just outside Bucharest, has a materials institute which offers very high-end transition electron microscopy and EPR measurements, and associated with that, all of the sample prep techniques you need to do to look at these samples effectively. Also, a certain amount of instrumentation for in situ, in operando electron microscopy. And then our 8th member country is Slovenia, and they're in Ljubljana, just an hour from here. They offer NMR spectroscopy, both in the life sciences and the material sciences, over a wide range of spectrometers, 4, 6, and 800 megahertz instruments, with, touch wood, in the year to come, an upgrade to a 1 gigahertz instrument. So those are our founding member states with their facilities, but there are still gaps in our portfolio. So what we've also done in recent years is bring on stream a number of additional associated facilities. And very briefly, that includes a particular spectroscopy beamline at the ESRF. It involves a collection of life sciences facilities that were funded in Italy as part of the post-COVID recovery initiative. So that brings us mass spectrometry at the University of Salerno near Naples, holotherm and mass spec for radiocarbon dating at Salento in the heel of the boot of Italy, and next generation sequencing technology actually here in the science park at Trieste, plus 2 European Commission funded joint research centers. So the Nanobiotechnology Lab at Ispra in northern Italy, and the battery testing facility with associated neutron instrumentation at Petten in the Netherlands. And we're in the process of engaging with other potential associated facilities. So at the moment, we're going through the process of approval of the Nano Center in Ljubljana. So this is a center of expertise in the fabrication of nanomaterials, but also the associated characterization, spectroscopy, microscopy, and various surface sensitive microscopies and magnetometry measurements. We're well into negotiations to bring another neutron facility on stream. So that's the FRM2 source at Munich. And then finally, and we'll come to this, I'm sure, is the discussions that we're having with your research community. And it's great to see you, Sasha, in this meeting, and you and I have met in Krakow to discuss the beamline that you would like to have built there with complementary facilities in Kyiv. So how does CERIC work? So I guess, I said at the outset that a key philosophy is to offer a single point of access to a range of techniques. And it's more than that. It's also to open up the power of these techniques to a wider research community that might not normally use them, who are not necessarily experts, but whose research could be transformed by having access. So we provide support for non-experts to prepare proposals. As I've said, we offer one entry point, and you can ask for a range of techniques to tackle a single problem based around a science case. We also offer support laboratories to help you prepare the samples in an appropriate form, particularly for microscopies or for biological samples, where the prep techniques are very specialized. We provide support for researchers to come from their home institutions. So we support travel and we support accommodation, all the logistics for 2 users per instrument, because in many cases, access is only part of the challenge of doing the experiment. You need, in some cases, have funds to actually come and do it. And then we also help you if you have remarkable results. We have a good communication office that can spread the message of success. And in doing so, what we hope is opening up these instrumentations to a wider user community, and also enabling people to bring several different teams together to tackle more complex problems. It's already the case in biology that the highest impact papers tend to be multidisciplinary teams to look at different aspects of a complex problem. And we're starting to see that happening in the physical sciences as well. So there are a number of access modes. If you're a non-expert, you could make an approach to us and discuss the science that you would like to do, and we will advise you on how to write a proposal. You would then submit a draft proposal, we can critique it, and then you submit a full proposal. So on the left-hand side, you see this 2-step process. Those people who are already experts, who know exactly how to write a good proposal, can jump in at that second stage. But in both cases, those proposals are then judged, peer-reviewed by a panel of experts, and those are the successful get the access, and they get the support for travel and all the access to the support labs. In addition, we offer fast track. Sometimes your science cannot wait for a review process that can take months. We have 2 calls a year, by the way, 2 open calls. So we also allow people with really urgent problems to come directly to us if it's something that's particularly hot, where we would like to bring that very urgent science to our proposals. And then finally, when the instruments are being commissioned, in some cases, we also work with expert teams to help the instrument to be commissioned, and at the same time, those expertise can get access. So a brief history. So as Danylo said at the outset, we've been operating now for about 10 years. So right from the start, there were 7 countries offering 25 techniques in 2014. Poland joined us in 2016. In 2017, Croatia, already a member but hadn't actually decided what to offer us, offered us access to the Ruja Boskovic Institute. And in 2019, we started to focus our activities in certain strategic areas. So we get substantial funding from all of our member states, but in particularly from Italy. So we actually have a core budget that helps us to support development of instruments and projects in certain strategic areas. And the first area was to fund the development of instruments and projects and studentships in the area of energy materials. So for example, if someone wanted to look at the chemistry inside a battery in a synchrotron X-ray spectrometer, then we had an initiative to actually develop electrochemical cells to put in the beam to look at processes in operando. So we supported a number of strategic initiatives through our core funding in 2019, and I'll come back to the impact of that. In 2020, I'm sure we all remember that COVID hit, and actually CERIC was one of the initial organizations that figured out a way to maintain operations safely. It helped develop some of the policy and procedures to make sure that it didn't just shut down with COVID, that it kept going. And at the same time also offered fast-track access for research directly around the priority area of COVID-19. 2021, we started to come out of COVID, and we anticipated an expansion with these additional associated facilities. And by now, we then have these 60 techniques in 11 countries, which across the partner and associated facilities. So very quickly, just to give you an impression, and I've got one slide on Ukraine, we support research across a wide range of fields. Here they're presented largely about sort of areas of societal impact, so ranging from health and food all the way through to energy materials, the environment, electronics and sensors. But we also have a substantial activity in what you might call fundamental research. You don't get applied science without science in the first case. We have an industrial liaison office that reaches out to industry to encourage it to engage with our facilities. And what we see is that a significant number of our publications, over 10%, have the involvement of industry, and a significant number of our publications also are associated with first or second degree patent citations. One of the things that we have to do to our funding countries, to the minister is more interested usually in what impact we have on society and the economy. So the graph, I'm sorry, it's a little bit messy on the right-hand side, but the line that rises from left to right and is the highest line on the right is represents the number of applications in energy materials. So when we started this initiative to support projects to develop instrumentation across what you might call energy materials, we saw a strong and sustained rise in the number of proposals in those areas, and we're starting to see very strong publications come through as a consequence. And then across our member states, it's also important for us to demonstrate that in funding CERIC, we also grow the communities in those countries. And I'll just point to two things here. I'm colorblind, but I think the two colors in the left-hand side are blue, and it's either green or orange. But anyway, I'm pretty sure one color is blue. The blue color is the number of proposals submitted. And of course, Italy is has the biggest research community, has the greatest number of proposals. But as a percentage of the number of researchers in those countries, we see a very strong engagement, for example, in Croatia and Slovenia. And there's some very strong evidence now that by supporting this kind of access, you really stimulate the engagement of those countries and the growth of science in those countries, because an important element here is to support and grow science in Central and Southeast Europe. So finally, Ukraine. I've really enjoyed the engagements that I've had so far. Sasha, you and I met in Krakow, as you can see in the bottom left, in May, looking at the possible site of a beamline that will be, we very much hope will be built in the area of nanomicro X-ray spectroscopy, with support also from Germany and Switzerland. And one of the discussions we've had is about that becoming a Ukrainian partner facility with Ukraine, a member of CERIC. And the photograph beside that is the contact that we have in your ministry, Zoya Petrenko, who has been very encouraging about this engagement, and Ukraine being a member of CERIC. And you not only you be very welcome, but you already engage very strongly. So we've had almost 120 proposals from your research community over the 10 years. Your acceptance rate is very high. It's almost 60%, which is above the average, and indicates that you're proposing excellent science. And we've also had a history of supporting Ukrainian science in particular. So in March 22, we launched an initiative to fund research projects specifically to employ Ukrainian nationals. And so far, we've had two very successful projects: Anatoly Nagorny, a project to develop these electrochemical in situ cells for SACs and SANS measurements. And we're still hosting Eleonora Afanasenko, who's engaged in the synthesis of functional moth materials. And then on the right, there's just an indication about the scope of science. So very little biology, but very strong showing in material science. And I suspect that, you know, the work that your department and your group supports, Sasha, for example, is very much in that field, but also very strong showing from chemists, and that's typified by the kind of work that Eleonora is doing. So very strongly engaged already with your country, and we would like to work yet more closely with in the future and do what we can to support the continuing excellence and growth of science in Ukraine. And I think I finished there, but I'm very happy to take questions if there's any time left over. And I guess I should unshare, shouldn't I, at this point?
Yes, I probably can also. So, thank you very much for the wonderful talk, and it's very interesting information. And I see there is already a question from Alexander. So,
yeah, could be, of course, many questions, but I wanted to ask the statistics about, I didn't know it, statistics about Ukrainians. You mean they applied not as from Ukraine, but from just this Ukrainians, or they applied from Ukraine? If Ukraine is not a partner, how it's possible?
So we're actually open to scientists from any country in the world.
Okay.
And so far, yeah, scientists from Ukrainian institutes have made 120 proposals. So that's just the way it is.
Yeah.
If you were to become a member, then so sometimes people say, so what's the advantage of being a member? Why should we contribute? Well, if you are a member, you then sit at the table that helps shape strategy, but also it's the money we get from the various governments, particularly from Italy, then gets redistributed into projects, into studentships, postdocs, instrument development across the member countries.
Okay, because I thought that this support for these two researchers is only from participating countries, not.
It's actually all countries. It's all countries. Yeah, yeah.
Okay.
Well, all countries within Europe. I think if you're an American who wished to come and use it, would say, okay, you know, sorry, you're already rich enough. You don't need this sort of support. We anticipate that there are other countries within Europe that could benefit from this support, and if we can help a Serbian research group grow, or a group from Moldova or wherever, we also think it's a good thing to support them as well and help grow the community, and the capability for them to become members as well. So I should say, Alexander, that we do have an active program of engagement to look for opportunities in other European countries, particularly in Central, Eastern, and Southeastern Europe. Well, I shouldn't exclude the Baltic, should I? But yeah.
Great. And I also wanted to ask, what is a typical average number of facilities for one proposal?
That's the average, if I'm absolutely honest, is between 1 and 2. It's about 1.5. So you can apply with just one technique. Okay. There are some that apply with, I think our record has been 5 techniques, but I think
if you can't apply with one technique, or you can.
No, you can apply with one technique.
Okay.
It's allowed, but we find on average, I don't have the number at my fingertips, but in my memory, it's about 1.5 on average. And I would say typically, very, very few are asking for 3 different techniques at once. And by the way, when I say technique, I don't mean 3 beamlines at one synchrotron. I mean a measurement of the synchrotron, a measurement of the neutron facility, and a measurement at an electron microscope facility.
Yes, thank you. Okay, maybe other questions, because.
Okay, we can't raise the hand because we're running this.
Okay.
Yeah, well, there is no button for us. But a quick question: when expanding the network, are you looking for the non-overlapping techniques from the new countries, or how is this? What's the logic in the expansion? in terms of
that's a really good question. I think there are two motivations for expansion. One is to engage more strongly with a new community, in which case, if you come along with a valid technique, if it was a third synchrotron from a third country, unlikely in Central Europe because the rest of them are in the west of Europe, then we'd say, sure. Where we want, and if it fills a gap in our portfolio, so much the better. But I think membership is open to everyone, regardless of what they offer, provided that it's a valid type of technique. Where we seek to fill gaps in our portfolio of techniques, then that's where we would go out seeking associate facilities, regardless of the country. So, for example, we recognize at the moment we are not as strong as we should be in neutron scattering. The Budapest Neutron Center is waiting for an upgrade, and when it does, fantastic. But until then, we feel that we need to strengthen our portfolio. So we deliberately reached out and we found another neutron facility. So it's, but membership, it's really about the building the community. Yeah.
Okay, so I guess the last question was from Faculty of Physics of Taras Shevchenko National University, where they have facility like collective use facility of microscopy like TEM, SEM, and so on. That's why probably they were asking. I don't know if they interest to join or provide such for facility, but yeah.
We would be very open to a discussion. So there are areas where we are very oversubscribed, and actually electron microscopy is one. So we're in the process of doubling our portfolio in cryo-EM, but also in materials electron microscopy. The Margarelli Center is fantastic, but it has limited capacity. So we would be very interested in a discussion on TEM, SEM, force microscopy. Yeah.
Yeah, that's what they have exactly.
Yeah.
Okay.
So just put them in touch, Danylo, and we can have that discussion. Yeah.
Perfect. Thank you very much for very interesting and amazing talk. And we are now moving forward for the next speaker, which would be the Pavlo Plotko, and he would speak about also scientific cooperation between DAISY and Ukrainian research infrastructures and Ukrainian research communities, more like in more general way.
Yeah, thanks, Danylo. And I'm not really from this community, but I learned today a lot, and it's always very nice to see how well connected you are, and the work is really incredible. It's always was a pleasure to follow what is going on in this one. And today I will just roughly talk about the DAISY and the new Centrum of Deutsche Center for Astrophysics and why it could be important for you. And today it was already mentioned DAISY, and Oksana gave a very nice talk about the DAISY. DAISY also involved in MAVKA, so I will just focus on one aspect, which is students. And the German Centrum, it's a new Centrum in Germany, and I want to tell you why it could be interesting for you and why there is overlap. And since I'm not really from this community, I just wanted to briefly tell who I am. I actually was studying in the Faculty of Physics. I am astronomers, but I think we always was friends with the optics department. Yeah, this was nice. And after that, I did a PhD at DAISY. This is my connection to DAISY. Again, I was doing Synhrotron, but Synhrotron in the space, so it's kind of different Synhrotron. And I was involved with the DAISY Ukrainian working group, where together with Andriy and other, we kind of trying to work and cooperate with Ukraine. So I kind of know what is going on. And since recently, I joined the German Centrum for Astrophysics, where responsible for international scientific affairs. And the one I think that is focused on the Eastern Europe, which includes Ukraine. So we will work very deeply with Ukraine, and this is very nice. And also we are trying to do some called like recovery of Ukrainian astronomy, where the effort, where together with Ukrainian astronomers, we're trying to bring investments to Ukraine. And I said there was a lot of mention about DAISY. I want to mention two things. The first one is DAISY Ukrainian School, which happening every year. And we invite Ukrainian students to come to DAISY for 8 weeks to do some research It covers all the topics of DAISY, particle physics, photon science, material science. And so please, if you know students or your students, please apply. Because I think every year now we have roughly 14 students, and it's really nice to see where they can come to DAISY and can learn, they can talk, and they can bring this experience and knowledge back to Ukraine. And what is lovely for me about this program that it's not only that you came for 8 weeks and then you're done. No, we're trying really to create a community. For example, every time, it was 2 times when DAISY came to Ukraine, every time we try to organize a meeting with the formal students, really to keep these connections and build up. And also what is my favorite part, that I know that many or some of the students which were part of the program regularly meeting after the program. They didn't know each other before, but now they're friends. So they meet in Kyiv like once per few months. And it's really lovely how we can kind of introduce or meet different students. And that is for more like bachelor and master students. If you're more advanced, we're talking about like PhD or like last year of master, there is a RAC International Summer School, which was organized by DAISY, and is focused on the X-rays and the neutron sources. In 2014, there was like 5 fellows for Ukraine. This was very nice. In 2025, there were only 1 fellow for Ukraine, if I'm correct. So please, next year, if you know anyone who could go there, please apply. We really want to bring as much as we can, but we really need applications from Ukrainian students and PhD students or young scientists. That would be incredible. So that was all that I wanted to add on the DAISY side. And then coming to the German Center for Astrophysics. And the reason why I want to tell you, because it's a very nice story about how Germany is putting money to science to rebuild the region. And it's very new centrum. It was established officially in September this year. And it will have a lasting effect. And this will become the biggest astrophysics center in the world. And as I said, there's 2 reasons why I want to tell you. The first one is to show you how countries can put money in science in order to build up the part of the country. And the second one, I will tell you about 2 projects which will have overlap with your fields. It's not really obvious why, but there is a lot of overlap. And to explain you why Germany decided to put money, I need to briefly tell you about the Germany in general. And Germany, especially the Eastern Germany, was always a mining region, actually kind of similar to Eastern Ukraine. You have a lot of minings, and all the society, all the business were focused on the mining region, and it was like mono industry region. And then Germany decided to close all the mining, close all the factories, and move to the sustainability energy, which is nice. But one of the results that people started to lose jobs. So you can see the decrease of the population, you can decrease of like how people see the future, there is a political issues. And this is why Germany decided to put money in this region, to put a huge amount of money. We're talking about billions euro projects. And it will be focused on research, innovation, and science. So they're building the factories which will produce silicon chips. They're putting money in the research in order to create a new regions, basically. And one of the projects which won in 2022 was this German Center for Astrophysics. And the money was secured for the next 15 years. And we are talking about the 1.2 billion euro of investments, which are roughly 170 million euro per year of the budget. So it really will be the huge facility. And in 15 years, we should have like 1,000 employees. Now, only after 3 years of like project stage, we already have 110 employees. So it's really very growing up projects, and will have a very big impact on the region and on the Eastern Europe. And talking about why there's connection to you, I want to mention 2 huge projects. The Einstein telescope, which is a new gravitational wave telescope which was built in Europe. I will talk about this slightly later. The other project is a Square Kilometer Array Observatory, which is a radio observatory, but now they're talking about some common project with a diamond light source. I think it was mentioned before. So they started really to discuss collaboration. So there is already collaboration with the light facilities. And the gravitational wave telescope, if you look closely, what is gravitational wave telescopes in the nutshell is just interferometer. It's a huge interferometer underground. And if it's interferometer, it's mirrors, lasers, and that's what you are working on. And the Einstein telescope is a new generation telescope. So there will be a lot of research to make it possible. And there will be research in terms of laser beams, the opticals, the vacuum, the cryogenics, so everything that basically you're working on. And even more, if you look about the general umbrella, what the Einstein telescope will do for the next years is research in material science, in the quantum optics, in lasers, in sensors, in controlling. So that would be a lot of connection to you. It's, as I said, European project. Ukraine is not part of the Einstein telescope yet, but I think we slowly going in that directions. I think last week, the DAISY, Deutsche Center for Physics, signed a letter of intent with the Ukrainian Astronomical Society to kind of show that we want to work together, and maybe we can start discussion about Ukrainian participation in the Einstein telescope. And if this happens, there will be a lot of studies, not only in the gravitational wave astronomy, but also material science, the lasers, the optics. So there are possible connection to your fields. And thanks. I don't really have any last slides. I think this is the last thing that I wanted to tell.
Thank you very much for very interesting talk, Pavlo. And I guess it's quite nicely related to our subject because we need only not 1.3 billions, but probably $500 million for Ukrainian Center of Synchrotron and Neutron Research. So we need a bit less money, but it's very interesting experience, and I think very important to learn from this and probably somehow implement this in domain of synchrotron research. And
yes,
especially
this,
probably
for example,
it is a future motivation to have collaboration with astro community as well. And if there are any questions, please feel from audience, please feel free to ask. Alexander, you wanted to ask?
Yeah, maybe if no one asking, I would ask briefly about this principle. This is this is principle of triangle. What is different in of this telescope comparing to this interferometer, LIGO like?
So the idea is that with different configuration, you will be sensitive for different range of gravitational, it's called in measuring hertz in the frequency. With a triangulation, you will be sensitive to other part of this so-called spectrum, where you will see the different types of events. So it's kind of the idea that you need to move your range, the same as if you have X-ray optics and you want to go to gamma, it's not as easy as just use the same technology.
So it is like triangulation, a triangulation measures the curvature of the Earth. In this way, maybe this triangulation measure also the mode which change the curvature of the space, right?
Yes, this is the true for all types of the configuration that LIGO has. LIGO measure the same thing. The idea is really to move to other spectrum of gravitational wave telescope, from X-ray to gamma rays, basically.
Okay, and this is in Görlitz, yeah?
So there is 3 facilities for Einstein telescope now. because the project is not yet choose the where to put. There are 3 candidates. The girl is this region, and that would be in Eastern Europe, then the Netherlands and the Italy. And it's still all, I would say, in the R&D phase. They're trying to choose which site, or maybe 2 sites, which technology to use. So it's really the plan for the next 10 Europe, and Europe is very slowly, as we all know. So no, the site is not decided, the technology is not decided. The decision should be made in 2 years, and then it will be probably 10 years of building. So
okay, thank you.
Thank you. And I have one more question, because I know that in audience there is students from Faculty of Physics, and I wanted to ask you, so this program is also for bachelors. What is the bachelor age of?
So if you would apply for the normal school, DAISY school, I would say 3rd year. You should be 3rd year when you apply. So you can visit the DAISY after your 3rd year.
Okay.
For the DAISY Ukrainian school, you can try apply on your 2nd year. So that one. So 2nd, 3rd, 1st year of students.
I'll ask another question, if I may, about the 4th year students, because I know that last year our 4th year students could not come to DAISY because technically they were, during those months, they were not students. They have graduated from bachelor's and their master studies have not started. And so they're like in limbo, they can't come. So
I can give you, I think, a new diplomatic answer that if the faculty finally will provide some documents that the students are in transitional period and they will be a master students from September, and there will be a signature of the dean and someone from the Red Corps, I don't know how
the main building, yeah.
Yep. Then they can apply, but we need this document.
You need this document upon the application, so like in spring.
Yep.
Oh, okay, good.
Yeah,
so
just something to guarantee that he will be a student, remain student.
And then they can try to apply, because I think we knew some cases where it happened before even. But yeah, if this document will be provided, it will be much easier for selection. So that can you work with that. Without this document, there is no possible way, unfortunately.
Now we know that. Now we will be instructing our students from 4th year who are applying to think of that before they apply. Okay, thank you.
Yep.
Andrei has written that it is insurance issue, right?
The issue that they're officially working in Germany. So in order for that one, you need to be a student affiliated.
Okay,
yep.
Thank you. Interesting.
Andrei said the same. If the dean signed the documents, which we know that in the past times it was very difficult to get this document, but now hopefully the situation changed.
Yeah, that's the general hope here. Yeah.
I think there will be no problem with signature with Dean for such a purposes. Okay, thank you very much for interesting talks, and I want to express my gratitude to the post speakers, and we are ending the international cooperation block session, and we have now 7 minutes of the break, and then we will start our last session of today, which would be related to synchrotron photoemission and X-ray spectroscopy. Thank you very much.
Thank you. Thanks very much.
So good afternoon everyone, and we are progressively moving to our last session of workshop, and the next speaker would be the Dr. Valentin Volobuyev from he has 2 affiliations. One is, I guess, Kharkiv Technical University, yes, and second one is from Polish Academy of Science. So, and the talk would be related to controlling Dirac-Rashba and double Dirac surface states in topological crystalline insulator via ultra-thin transition metal layers. So, you are welcome for presentation.
Can you see my screen?
Yes.
Yeah, okay. So it's in presentation mode and everything is fine. So, hi everyone, and thank you very much for inviting me for such important event for Ukraine. I think for Ukrainian scientists, it's very important. So I would like to thank the organizers. So basically, I'm a researcher and I will talk about science. And so I work with topological materials, with, in this case, topological crystalline insulators. You know, there are some surface states in these materials, and I will talk mainly about these surface states and their evolution with deposition of transition metals. So, okay, and that's outline of my talk. I will briefly give you introduction into what is Rashba effect, what is topological crystalline insulator. I show you how we do this structure because we use molecular beam epitaxy to grow this, and we investigate as well their structure. So I characterize as well my samples. Basically, I give you motivation why is important such research, and definitely these results. I show some angular resolved photoemission spectroscopy images. So just briefly remind you about maybe it's not necessary because Professor Rashba was originally from Ukraine, from Kyiv, and I think he worked in Institute of Physics in Kyiv before. So basically, such effect. It's sorry, it is. Oh, I cannot see. Okay, like this. So there is you have a bands which is usually degenerate, but if you have material with strong spin orbit coupling, and somehow you create this inversion asymmetry, so this band will be splitted. So this is spin degenerate, and now it's as you can see, it's splitted. So basically, this effect was observed firstly in quantum wells, asymmetric quantum wells. So there is like band bending effect, and creating this triangular quantum well at the interface. And this is definitely non-centrosymmetric materials. What I'm going to talk today, basically, I work with for 6 materials. As you can see, it is heavier elements, and so there is definitely large spin orbit coupling. However, it's a centrosymmetric material, and it's as well good. Maybe right now it's not a question whether Rashba effect should exist in this material, but like you see the gold is centrosymmetric as well. But in such material, you can see that these so-called Rashba parameters quite large. And this is Rashba parameter. It characterizes this the amount of the splitting. So when we start to talk about applications, there are like application spin charge conversion when we have adjacent usually ferromagnetic material to material which is spin orbit. So you can with a spin pump, or you can in opposite as well, like you can, for example, rotate magnetization of adjacent layer, just simply passing the current through your material with large spin orbit. So at the interface should be this Rashba states. So, and I work with for 6 materials. So they have this 1-1-1 surface which is polar, and definitely it creates electric field. which breaks time reversal symmetry, which breaks inversion symmetry at the surface. And one can expect as well big rush-by effect in these materials. As well, my materials, it's actually so-called topological insulator, topological crystalline insulator. And this is this structure because of, I forgot to tell, but rush-bar and topological materials have similar this spin texture, which is basically in topological insulator. As you can see, it is protected by, usually if you talk about Z2, by time reversal symmetry, and in rush-bar case it's not protected, unfortunately. So in this talk I would tell you about lead-tin selenide. It's actually from so-called tin telluride material class. So in this material, one can see that there exists a band inversion. It occurs in the 4 points of Brillouin zone. And because it's 4 inversion, it's even number, this material cannot be considered as so-called Z2 topological insulator. So Chern numbers for this material is equal to 0. But like there is so-called mirror Chern number, which are non-zero, and the surface states, basically Dirac cones, which we can observe for 0, 0, 1, 1, 1, 1, 1, 1, 0. So they are protected by symmetry of 1, 1, 0 planes, by mirror symmetry. So because it's so-called topological crystalline insulator, it's interesting that we can go from one state to another. We can change, and for example, the properties, like from normal insulator to topological insulator. So basically one can see that it is demonstrated for 001 surface. That's one of pioneering work which was done in Poland. So basically one can see that there is a topological transition. And for 001 surface, we can observe formation of so-called double Dirac cone, because I forgot to tell you that here, as you can see, there is, when we project to the surface, the states, they are coming from two trim points, time reversal invariant momenta points. So therefore, these cones are hybridized, and we, as a result, see such a double Dirac cone structure. And this is shown for 111 surface, which is basically here you can see the change of the temperature for lead-tin selenide that we can see this band inversion. We can see formation of topological surface states as change in the temperature or tin content. And today I'm going to talk about this topological crystalline insulator material. In this case, we should be around here. So yeah, I would like to say that for this material, 001 surface, it's a cleavage plane, so you can easily work. But like to receive other surfaces, it's not so easy. You cannot simply do cleavage and get nice clean surface, which is necessary for RPS. So basically, for this reason, we use molecular beam epitaxy, where it is possible to grow such material. So we use compound sources. We have possibility of dope this. We heat our substrate. So basically, it's a chamber where I grow these materials. That's another one, but that's for other like 2,6. And I use in this work this barium fluoride substrate and KCl to provide different orientation of the films. So that's the results of structural characterization. As you can see, we have nice tricky read pattern, which says that we have smooth surface in our film. That's AFM image that you can see atomically, atomic steps on the surface. By SEM, we can characterize the composition of our film, how it's whether it is different from we originally planned. Similar this compositional characterization we can have from X-ray diffraction, because it's like linear dependence of lattice constant, so-called Regard's law. We can see this as well, if it is important, the strain in our film, so we can characterize using asymmetric reciprocal space map this film, which we can see both depending on the strain. We have position of the maxima, it will be different. Dr. Sobel told us today much and before him about this RPS investigation. I wanted to remind you, but I just say a couple of words that it's based on external photoelectric effect. So as you can see, we illuminate our sample with a soft X-ray or UV. Then we have this hemispherical analyzer where it's basically a capacitor which separates our electrons according to their kinetic energy and the momentum. So there is momentum dependent angle and kinetic energy, so which can be recalculated into the binding, so this kinetic energy into the binding energy and this angle into K vector. But what we need somehow to come, because surface of the sample sensitive to the air, to environment, yes, we have to somehow protect our surface. And for this, we usually use such a ultra-high vacuum suitcase, as one can see that it is attached to our NVE machine. And then we came to Uranus synchrotron, where we had many measurements, which I will talk later. So we use this another way, and that was we used in the beginning, that we can simply cover with selenium our material, come to the synchrotron and heat it up. Selenium will evaporate and we will have clean surface. Of course, you can come with to the synchrotron with your cell, and you can do deposition in situ. There is such possibility. Or, for example, Dr. Sobel told today us that they have electron guns for evaporation, so you as well can evaporate material like iron or other cobalt. Okay, so basically, that's the RPS results which obtained in Uranus. So as you can see here as well, for our samples with 30% of tin, one can definitely observe this formation of Dirac cones. It's 111 surface. And I would like to mention, not about application, but about science, because it's interesting prediction which we wanted as well to test in these materials. Basically, it is so theoretical people promise us to see surface magnetism if we dope our material with some transition metals. due to RKKY, and as well it should come only through this topological surface states. So, but yeah, there is promise. Okay, I will show later the results. So here is preliminary characterization. We wanted to know before we come to the synchrotron what will happen when we deposit this transition metal. That's basically the manganese deposition. So as you can see, initial state, and when we start to deposit, we just see decrease of intensity, but we don't see some, you know, like if it were a polycrystalline film, that we see some rings, etc. So we just see that it comes with some disorder at the surface, but yeah, but not completely. This is AFM images before and after iron deposition. Don't look at the surface because it's to this white spot, because it's ex situ measurement, and it appears afterwards. So basically, as you can see, it's still one can dissolve this atomically smooth steps. So we expected that our material will work when we come to the synchrotron. So, and basically here is the result. So as one can see, with consequent deposition of manganese, we see that Fermi energy goes up. So basically this Dirac point goes down. But in addition to our topological bands, we can observe some additional levels, yes. And this is basically this Rashba effect. So what we see, we called Rashba-Dirac. Yeah, if you want Dirashba or whatever. So, and this is for 1-1-1 oriented film. That's with manganese deposition. And it is stronger. So we as well estimate this Rashba parameter using this equation, and it is quite high, like 3.5 EV on angstrom. And as one can see, that it is it saturates. So basically with manganese, what is happening with manganese, we bring additional carriers. It definitely drives your it creates band bending, it drives your Fermi energy up, and because there is spin, large spin orbit, broken inversion symmetry at the surface, we can observe such states. So basically, and one definitely can see this quantum well levels. Yeah, I don't know whether I can call it Volkov-Pankratov states, but anyway. So basically, you see that with the deposition of any metal in not any, but with certain work function. So there should be formed such asymmetric quantum well, and that is why we should observe this particular Rashba effect. And similar effect we expect that if you do similar with electric field, applying electric field, so it's gating effect. So this is again 1-1-1 surface, but that's iron, and you see quite similar pictures. The interesting stuff was because we can dope our film, yes, and in the case below, by the way, you can see here as well this constant energy surface map, and you can see that it is concentric circles, and that one should see in the when you see really Rashba states. But when we dope our material very high, so we use like bismuth, so the Fermi energy, in this case, deep in the conduction band. One can see that with deposition of iron, our Fermi energy doesn't move, but it produces this Rashba effect, as one can see. Yeah, so there is no movement in the Fermi energy, but strong movement of the this alpha coefficient. So basically, right now people started thinking about this effect because what is initially predicted by Bychkov-Rashba model, it gives you much smaller splitting in comparison what is observed in experiment, and currently it is like this, that electric field, it interacts mostly not with a spin moment, but with orbital. So, and even without spin polarization, you can have this orbital angular momentum texture, and that is as well can be useful. So anyway, so there are other reasons, not only electric field, but as you can see, it is important this orbital angular momentum. And indeed, so this is circular dichroism images when we illuminate our sample with a different polarized light, and definitely we can observe such effect of helical states in our material. So as for the origin, again, it's there is photon energy dependence. As you can see, the states doesn't disperse. So that proves that we have definitely the signal from the surface. As well, we do this core level spectroscopy, and you can see that with deposition of iron, we see on the tin and lead some additional maximum, and that's connected to so-called chemical shift because we change environment of our component with deposition. That's deposition of iron, basically. Sorry that you cannot see it. Yeah. So again, why is it important? So people, other experimentalists already saw such kind of effects that if they create such some interlayer, or in this case of our topological crystal, you can directly that there should be something on the surface that most probably Rashba. Yeah. So in this case, it's I guess bismuth selenide, and as you can see, there is, in addition to Dirac as well, this topological surface states, and people think that it enhanced efficiency of such devices is as well connected to the presence not only topological but as well to the Rashba states. So basically, it should be better. And I will touch briefly this 001 surface. So here we can observe this double Dirac cone, as I said, and with deposition of manganese, as you can see, the distance between these cones are shrinking. So basically, you can see here, and there is a theoretical work which says that with deposition of some material on the surface, this wave function of such Dirac cones, they are currently in phase, but when you disturb one of the surfaces, so it should result finally in single cone, and that's what we observe. So in conclusion, I would like to say that we observe such for 111 surface is Dirac-Rashba states with it's actually a giant Rashba. 001 surface we see as a shrinking of this double Dirac cone, And we hope that it will be used, this information will be useful when the people project such spin charge conversion devices. So that's basically people who participate this. So this is two students who work with me with deposition and with RPS measurement instruments like Tchaikovsky did, EDXM, Wojciech Zaleszczyk, he do a lot of with MB, that's both of our group. So we hope that there is soon will be CERIC. Marta Lishkevich did AFM. We would like to support Uranus. This is Jacek Kaladzeyev and Natalia Olshovska who did support. And this is my former boss from JKU. He as well worked with me on this project, and Andrei Tsaha from Masaryk University. So definitely there is funding agency and Polish side as well, this National Science Centrum, Polska Akademia Nauk, FNP, they organize program for Ukrainians, and they as well support joint Ukrainian Polish teams and finance them. So I would like to thank you, and I would like to thank organizers for such a nice meeting, such a nice event, and European scientific communities that help Ukrainian scientists to progress even such a difficult time. Thank you very much.
Thank you very much for very interesting talk, and we have time for one, two questions. So I think Alexander Kordyuk would definitely have a first question, please.
No, if someone have questions, maybe, because actually for me many effects here are new for me, and actually I would be interested to ask many questions, but I understand. So as I understand, you are actually your main experience is in B, but you also doing ARPES by yourself, right?
Yes, exactly.
And ARPES, it is mainly at Uranus or somewhere else?
I would say I was postdoc with Gunter Spingold, and somehow at BESI I even saw your some publication or some posters with your family name. So we first went to the BESI currently because I'm situated in Krakow. I go usually to Solaris. Yeah.
So, no, I'm interested if interested in technical stuff. For example,
Okay,
this
okay.
temperature appearance of the gap with temperature from Dirac to gap evolution. I actually never saw it. I didn't follow the field maybe. It is, but for me, it's how one can measure it technically in a sense that you understand that it is you should monitor the position on in the inverse in the reciprocal space, right? And to be sure that you are not away from the sun.
Yeah, each time you are going to the
You are just
you adjusting the
adjusting it,
sample,
but
yes,
it's not the case that you measure the gap and measure the map and then choose.
No, you should adjust
You
because
just
as you
adjust.
know, with the temperature, everything will move, and you
So, but
you will cut in you can cut in wrong in the wrong
but
position.
is it generally accepted that it is so that Dirac that gaps opens instead of Dirac at high temperature? What is the mechanism?
Yes, the mechanism is
Andrei?
simple because if we go with
I see.
maybe here it will be easier to, for example, we have like 25 or 30% of T, and definitely if we go up with the temperature, we change the band inversion. Yeah, So this is.
No, I just do not understand how one can change band inversion, change in temperature. But okay, it's I think it's not a
because
short.
energy gap is temperature dependent, and in this particular material, as you can see, that's exactly energy gap.
Yeah, okay,
That's
I
different temperature.
Experience with this material. And when you shown actually this iron or magnesium on the surface, and you call it you say that it is actually effect of Rashba splitting, but it is not a degenerate band, right? Or it is still degenerate. It is not spin one state.
So both states, like here and here, they are not degenerate anymore, right? So
No,
even
but
if you
initially here, it is surface state. It is already topological surface state, which are non-degenerate already.
Yes. Here
But
is
how
already
it could be split in
topological states, but you can use normal state, and in this case you as well will receive Rashba, but without Dirac cone. Yeah, we have such measurements as well.
Okay, should read the paper. The last comment, which I know actually for sure.
This is not published yet results. Sorry.
No, but interesting. The one which you shown about circular dichroism. So for this case, I know for sure that these colors are nothing to do with spins, because if you have it for any materials, degenerate materials, you have this just blue and red, even for degenerate states. Therefore, one can't say based on circular dichroism that this is some story related with spins. That would be too easy, and people would not need to use spin detectors.
Of course. So these measurements typically sensitive to orbital angular momentum, and as I said, there is a review from Gustav Billmeyer, which explains what's happening, and in most cases, this giant Rashba comes from this orbital angular momentum, and the spin angular momentum follows the orbital. And you are right that it is nothing to do with spin. It's more orbital angular momentum.
Yeah, but
and
also
you are right that it is.
No, okay. I understand your answer.
And you are right that we measure RPS, and with RPS there is big difference with like initial and final state. I mean, like we are investigating the electrons in the solid, which are emitted in the solid, and there are definitely some factors which can affect, and especially for this angular momentum. You're right that you can observe it even for the samples which has nothing to do with large spin orbit coupling. So basically, it can be artifact. So you need modeling for that. You're right. Yeah.
Okay. Thank you. Thank you very much.
Thank you.
Thank you very much for the very nice discussion. And I guess we don't have time for any more questions, and we should move forward to our next speaker, which would be head of the laboratory at Kyiv Academic University, Dr. Volodymyr Bezguba, and he also would be speaking about topological quantum materials and how you can recognize them with RPS.
Thank you, Danylo. Thank you very much for the introduction, and thank you in general for organizing this wonderful workshop. and it's very nice. I enjoyed a lot of different talks today. Okay, so without further ado, my talk will be about how you can use ARPAS for topological quantum materials study, and why ARPAS is good for that. And I try to do it like an overview, so I might repeat some of the things which was said before, but I think maybe it's even good for some of the participants just to like get better understanding of the methods. So at first, I will give short introduction about what type of materials we are talking about, then the basics of ARPAS, and also a new type of spectrometer for ARPAS, which is FESUMA. And lastly, I'll move on to some specific examples, but probably in short due to the lack of time. Topological quantum materials in general, you've heard today already a few definitions, very nice from Alexander Kordyuk, for example. And when you add topology to that, first topology from mathematical point of view, it mostly corresponds to such types of things. When you have some manifold, it can be not even three-dimensional, it can be in any number of dimensional space. And there are such characteristics, for example, as genus of this surface. So like when there is some hole open in it which can't be removed in any way, that's already like different type of genus for this manifold. And turns out that when you are talking about when you are considering band structure, it's also a manifold, and very interesting effects arise when the topology of these band manifolds are topologically non-trivial. In 2016, actually, for discovery of topological insulators, for theoretical prediction of them, there was given the Nobel Prize to David Toules, Duncan Hardane, and Michael Kosterlitz. But now, in short, how it looks from the terms of band structure, in the middle you can see three different graphs. The first one is normal insulator, so you have one band which is above Fermi level and one which is below. There is some gap between them, nothing special is happening, that's insulator. If the parity of the band, or the Chern number of the band, some special factor of it is changing, and the band, there is a band crossing, but the gap is opening as a result of it, and it is called essentially a band inversion. When such things happen, that creates the topological insulator. So in this inverted gap, surface states emerge, and it's intrinsically it's a material which will conduct current on the surface, for example, but not in the bulk. And another example is topological Dirac semimetal, when these bands create the Dirac cone, essentially. So in that regard, probably everyone heard about graphene. Graphene is under normal circumstances. It has a small gap, but if you dope it slightly, or apply some strain, or do some other manipulations, it's essentially a topological insulator. And also another picture of band inversion, which you see it results here. Topological surface states emerge. Here there are Dirac cones. Also, another example of topological materials is topological superconductors. And here, don't get scared by this difficult band structure. I'll get back to it later with more details, but for now it's just to show that these are iron-based superconductors. The DFT calculations for different families of them, and the one in the bottom, which is here zoomed out, this sector in you probably don't see my pointer. Now you should see it. In this red region, it's the zoomed out part of it for iron, tellurium, selenium. And this opening from theory, it arises as actually an inverted gap. So parity of these bands, it changes. And here this was discovered in 2015 in theory. And in 2019, there was a paper which was stating that actually, and also in 2018, from the same group, the paper which was stating that actually you can realize topological superconductivity there. Why? What is so good about topological superconductivity? It can be the basis for quantum computers because if you have surface states and superconductivity on close to the Fermi level, it can create Majorana fermions, which can be experimentally observed, for example, in scanning tunneling microscopy through observation of Majorana zero modes. But it's a tricky thing, and I'll cover it in more detail a bit later, because these Majorana zero modes, they can be also these zero bias peaks, which are observed in scanning tunneling microscopy and which are signals of MZM. They can be also not zero bias peaks. Some other topologically trivial effects can look similar, and I'll mention that later. But essentially, yes, if you get such material with not a heterostructure where you have different types of like sandwiches of materials, but or some nano wires of top of something, or artificially placed atoms. But when it's intrinsic material, it's very nice because it's easy to use. And when you have these Majorana zero modes, they are topologically protected and they are very stable. So it's good to realize qubits on them. That's why everyone is chasing them so much now. Here you can also see some of the pictures from the SOLARIS from our beam time, which we conducted for the first time that we were at SOLARIS just at the end of this spring, beginning of this summer. So briefly about ARPAs, it's been mentioned today already a few times. Photoemission, when you light monochromatic light on the sample, photoelectrons are getting ejected from the sample. And if you scan them by energy and angle, essentially you get you can recalculate angle into the momentum, and you get the spectrum. But in this case, there is no angle yet. You just detect it by energy, then you get XPS. And I think you've even seen this picture today a few times before. But again, the band structure is quite complex because you have, in the reciprocal space, you have whole 3D brilliant zone. And here I want to make a simple, funny analogy with trees. So you have a 3D object, and in this case, it's actually a four-dimensional object because you have also energy. But essentially, you have Kx, Ky, Kz, and you can cut it in different directions when you make an experiment. So if you cut it horizontally, you get a cut like this, and this is Fermi surface, essentially. If you cut it along the tree, vertical axis of the tree, you get traditional ARPAS spectrum. And later it will be important. So, like I said already, when you distribute, when you also have resolution for angle, you can get not just density of states, you get the reciprocal, the nice cut of the reciprocal space, for example, like this one. And then by rotating the sample with polar angle, you scan the reciprocal space cut by cut and reconstruct essentially almost the whole brilliant zone, the part of it. The tricky part is that as a light source, you can use any monochromatic light. It can be laser, it can be helium lamp, it can be xenon lamp, but ideally it's of course synchrotron because with all the sources which I mentioned before, you are stuck with only one excitation energy. And the perpendicular to the surface of sample component of momentum, it's not conserved. You need inner potential. Again, you probably have seen this formula before. I didn't include it here. It's just the simple one. But the important part is that's the parallel part, like the momentum space in the surface, parallel to the surface of the sample, but not the perpendicular one. The perpendicular one you can scan only by varying the excitation energy. And that is very nice. Besides the high brilliance of synchrotrons, besides the small beam size, that's another big important factor for ARPAs at synchrotrons, that you can actually measure KZ dispersion as well. And another nice thing about ARPAs in general is that it has a very good analytical way. So a lot of information can be extracted from it. It's almost, when you ignore the matrix elements and some experimental effects, it's the real information about quasi-particles, about electronic structure of the material. So the self energy is being stored in this information. You can extract a lot of data about it. And this is example of the ARPA spectra, how you can do data analysis of it. For example, this is barium iron arsenide doped with potassium, and it's Fermi surface. So again, you need to orient sample in a correct position so that you know which cut you make, because again, it's 4-dimensional space. If you count on the momentum, it's 3-dimensional space, and depending on how you orient it, you can cut like this, or you can cut like this, or if it's not in the center, it can be cut like this, and that's not what you want usually. And after you make all this momentum distribution curve, you can try to fit them, knowing which bands you expect, and you can reconstruct the band structure like that. Now let's move to a different type of spectrometry. FESUMA, it's short for Fermi Surface Mapper. I think I won't stop too much on this slide. You can check it later in the recording or at the source by this link. But it's actually quite important because again, it's you can't easily look at this data as a one. You always have some sort of projection, and this graph I like how it summarizes very nicely what you hold, which parameters you hold constant and which you vary, and as a result what you get. Because for example, the KZ map which I was mentioned before, it's proportional to excitation energy, and then you get stuff like this, but that also depends on the angle, and like there are many nuances to it. That's the example of the tree which I was giving you at the beginning. And what is nice about Fermi Surface Mapper is that it, instead of okay, let's first talk about the detector itself. It scans layers in this direction. So you in this case you have just some aperture like here. So in the normal case of ARPAs, the detector has a slit, and so you have just one dimension of the angle. While here you have both, which can be recalculated to kx, for example. While here you have kx and ky, because you have both of these angles. And it's very nice symmetrical picture, which allows you to immediately get the Fermi surface like on this sketch. And this is the mini ARPAS lab, which was built under GUQMAT project. Right now it's in Dresden, Germany. This is like fresh photos from October. And as you can see, it's quite small, hence the name Mini. It's very miniature and but nevertheless quite capable. I'll show you some spectra a bit later. And here how it looks in the center, inside. This is the manipulator, quite interesting new construction, which again allows you the spectrometer is on the other opposite side, which allows you to see a very nice symmetrical picture and do a lot of extra stuff which was not possible before. For example, this spectra I measured just past week. This is platinum bismuth 2 doped with tellurium at Fermi level, and this kind of pictures you get immediately. So again, in comparison to traditional ARPAs, if you wanted to get the Fermi surface, you would first record this card for like 5 minutes, then another card for 5 minutes, and then you would need to glue them together, and then you would get such picture. But getting each cut means that you are also rotating the sample. When you're rotating the sample, you are risking that your beam will be slightly moving on it. And it's tricky and it's also more time consuming. In this case, you get this picture immediately and you know that it's from that point, from one point at which you are measuring. What I was telling you about geometry and it's placed in a nice way is that here you would expect helium lamp, it's 20 electron volts. Those who measured ARPAs or worked with this type of light source, they know that this angular range would be probably like from like only in this square. But here you see much more, because there is some extra length, extra voltage being applied, which speeds up the electrons. So it's still the same KZ. We don't do any magic here. But because they are accelerated and you measure at higher energies, you manage to cover higher range in K space. And here is also another example of antimonium tellurium with a nice Fermi surface, and this is the picture slightly below Fermi surface. At this energy it would be small, so I lowered these accelerations and got it in a better way here. I think I'll stop with Fasuma for that at the moment, and we'll just show you a few examples because again, not that much time. So like I mentioned before, topological superconductivity is a very desired property, and it's the type of materials which everyone is looking for at the moment. And iron-based superconductors are one of the candidates for that. Iron-based superconductors, they are presented by these four families. I'll be mostly talking about iron selenium and lithium iron arsenide. And on the right, on the left, you see the crystal structure. On the right, the band structure calculated from the DFT. And as mentioned before, here they all, except for 1111, they all have a gap between PZ band and DXZ DYZ. And later it was shown in that paper, which I also mentioned before, 2015, that actually this gap is inverted. So there is some non-trivial topology happening there, and there should be surface states. And there were actually studies which showed from ARPAs that they've seen something like surface states, but it is more complex than that. First of all, spoiler, studies from 2020, if it's topological surface states and if it's topological superconductivity, then one would expect that there are Majorana zero modes, and then you would see in scanning tunnel microscopy, you would see zero bias peaks. But in studies from 2020, it was shown that those were actually not zero bias peaks. They were other peaks, I forgot the name, but basically topologically trivial ones. Besides that, we also did measure this material. Here are some of the examples of the spectra. For example, on this one, you can see that the quality is very nice. Here there is superconducting gap, which here is the superconducting gap, which is not visible at higher temperature. And now we do this type of cuts and we measure many different spectra, varying excitation energy, like I mentioned before, mapping with different KZ, trying to map each band to the calculated surface structure, trying to figure out what was happening there. And our conclusion was that actually PZ, again, I'll show you once more this paper from 2018, where they show that PZ dives deep and crosses it here, and here the inverted gap opens. Here it shows that it dives like very deep. So it definitely crosses everything. But our finding is that no, it barely touches the DXZ DYZ. And actually, if it touches it, then there is inverted gap. But indeed, this is like the question of resolution, and one can speculate about it. But we also studied how much the factor of renormalization is playing a role here. And what is renormalization? It's how the theoretical calculations correspond to the real experimental data. And usually the experimental, in reality, in experiment, the sizes of the bands, they are a few times smaller than in calculations, or at least the same size, but not bigger, so always slightly smaller or much smaller. And in this case, with the normalization factor, which we extracted from the data with all the analysis, it turns out to be sub-millieV, so it's not enough to get any effect. And there were also some other papers, but to summarize them, there is a lot of contradiction around that, plus that thing which I said about scannerline spectroscopy. So this is the first paper which I showed you from 2018. This is our paper where we see that it touches, doesn't touch the DXZ DYZ. Here is another paper where with spin orbit, they say that there is something, but it's similar to ours, but slightly different. And then there is another paper from 2020 from different group where they again say that it crosses. And so essentially, it's not just us. It's there is a lot of contradictory results on this material, and it does look like there is no topological surface states there, but it's still a very interesting topological Dirac semi-metal, because like you see there is here type 1 Dirac cone, and lower there is also type 2 Dirac cone, so it's still a very cool material, just not a topological superconductor. Another candidate is lithium iron arsenide. Again, not much time to go into detail, but in short, here it's expected to have surface states, and sorry, here it's expected to have topological surface states, but yeah, that was correct at first when I showed this TI cone. And the idea of this paper was that with doping with cobalt, they would also get these ones. But again, we conducted the study as well, and this material was also subject of the studies with scanning tunnel and microscopy, of course, STM. Same story, no zero bias peaks, so they don't signal about Majorana zero modes.
Sorry, but we have lack of time. Can you accelerate a bit? Sorry.
Yeah, sure. So then, long story short, after mapping it, we correspond this what they see. We see similar feature. This is a very fresh spectra from this year from laser. We corresponded to a few different factors, one of which is KZ resolution is limited. So this is calculated band structure for this material over gamma Z direction over the whole Brillouin zone. And you can see that there are some, if the KZ resolution is bad, you will see these bands, which you kind of see here. And now very fast then about Solaris. We measured some things at Solaris this year, so it was we will use this data with rhodium for our study. This study which I was showing before about life as we didn't publish it yet. So this is doping with rhodium acts as doping with cobalt. So we move the band structure slightly below Fermi level. Very nice spectra. Another very interesting result, which was mentioned earlier by Alexander, we measured together platinum bismuth 2, which has Fermi arcs, very cool, unique material, where actually topological superconductivity might be a thing. And we found out that with very preliminary data analysis, and we need to do some more measurements on it, that when we dope it with rubidium, you see here there is no rubidium, more and more, that the size of these Fermi arcs increases, which opens a lot of opportunities to utilize them to change the properties. And lastly, antimonium niobium, it's a weak topological insulator, which we also measured at this last beam time. We managed to measure a lot of different materials. Here, it's very hard to cleave, but we managed to get a lucky cleave. And Susmita from the group of Sophie Borisenko in IFW Dresden, she managed to find that yes, we actually did see surface states. Careful comparison with calculations shows that they are there. So it's experimentally confirmed that it's a weak topological insulator. With that, I would like to thank you once again for the invitation and thank you for your attention. Maybe there are questions.
Thank you very much for your talk. So we have time for 1-2 questions. So
if no questions, maybe comment, because Volodya did not say it, that actually this FASUMA analyzer, it is actually our analyzer, and it will be developed, it will be installed here when they finish it assembling, let's say, because it will be possible to measure here whatever you like.
Yeah, I was just hurrying and I probably omitted this, but I meant to say that this is now in Dresden, but will be in Kyiv. It's not clear yet when it will be in Kyiv, maybe next year, but also, and it will be stationed in Kyiv as under Center of Excellence. So it will be open facility, I would say. And also important notice, probably worth to say that we plan to upgrade it, so likely there will be also prep chamber there and maybe even the laser. I see Valentin has a question.
Have a question,
Yeah, just very simple. So this iron, selenium, tellurium, what is temperature of superconducting transition?
13.5.
How much?
13.5.
And you manage to get it in like lab easily, or it's a lot of struggling such temperature? It's even
No. Look,
maybe it's
here.
Bessie.
Yeah, this is Bessie, like I mentioned, also 12 eV. It's not the laser, it's not the lamp. Maybe Xenon would be close. So yeah, it's Bessie, and this study which I was showing, yeah, it's all like here you see the KZ map, just the cut of it, also the second derivative to make it more visible. This is all synchrotron data. The other data which I was showing, yeah, there are some spectra from laser, but those we can go down to 3 Kelvin, maybe 2. So it's just normal liquid helium. If you have a very cool cryostat, you can go for a short time to 2 Kelvin.
And in Uranus that you measure these days, which temperature so you managed to achieve, like as well?
I don't remember.
Below 10.
Yeah, it was below 10. I don't remember if we reached 4, because it has different cryostat,
I
like specific
don't think
system.
that it was below 10.
I think it was 8.
Yes, I think it was 8. I also can confirm it.
I remember
But
for sure
it's
that
not a sample temperature, it's probably...
Yeah. I mean, of course, you always need to remember that it's sample on the manipulator, and on the sample it's a bit more higher.
You see the gap, right? So that
No,
you can
we did not see
judge
the gap
For this, no, because with rhodium it has lower temperature TC.
No,
I think
just because of a resolution matter, we could not see the gap there. It is not the place where we could see the gap. Maybe for more careful experiment, maybe, but we just our beam time was more somehow overview beam time.
Yeah.
We look on different materials, and we did not focus on gap. Gap, it's a separate story, of course.
Thank you. Very interesting.
But I believe that this would be possible to see, maybe not in iron tellurium cylinder, but in pristine LiFeS. I think it would be possible to see superconducting gap on Solaris, because pristine LiFeS is 18 Kelvin, and
No,
the gap is
I meant platinum bismuth, not this. This, of course.
Yeah. I just wanted to make it clear that it has the size of 6 MeV, so it would be definitely visible.
So thank you very much, but I think we can move discussion to some other time, because we are now collecting some delays. And next speaker, thank you, Vladimir. And then there will be next speaker, which will be Serhiy Chernov, and he will present also about new end station, new DAISY beamline, which would also able to perform RPS and resonance RIXS studies in DAISY.
Sorry. Yeah. Thank you for hosting me, especially for my late submission, nevertheless. And I want to start with motivation for this study. And I was thinking a lot, like, what should I put on this? I should put a very striking figure that shows all the hot topics, quantum materials, superconductors, spin charge density waves, and so on. And all these figures are somehow either not very scientific or not very impressive. And then I decided to just put a phase diagram of this cuprate material, and that shows many of these phases actually, and a very complicated behavior of these phase transitions. And depending, they are also very tunable depending on different parameters like temperature, doping, stress, pressure, and so on. And by chance, the figure that I liked the most was published by Alexander Kordyuk 10 years ago in his compilation study. So when you start thinking about how to study these materials, in former times, basically an ARPES was a very powerful tool alone, which could help you to study like semiconductors or metals or even topological states. But now as we move to study more exotic materials and more exotic phenomena like collective excitations or collective behavior of electrons and their interaction with lattice and spin waves and other elementary excitations, RIXS is thought to be a method of choice for this collective phenomena. And it would be nice to combine both in one experiment somehow. And so this is what I'm going to talk about today. So, and I would like to start with ARPES, which is in the topic of my presentation. And I simply called it ARPES, but in general, what I do here is called momentum microscopy specialist scientist at DAISY. And momentum microscopy is like an advanced version of ARPES, at least we call it so. that allows you to speed up the measurement a lot, but more on this later. So we have two of these momentum microscope currently installed at Petro 3 at DAISY. One is at hard X-ray beamline at P22 that goes from 2.4 to 6 keV, while the beamline itself goes higher, but the microscope we typically don't use above 6 keV. And both of these microscopes can go to cryo temperatures below 30 Kelvin and perform UHV experiments. And the specialty of hard X-ray measurements is, of course, long inelastic mean free path of electrons that increases the information depth. So this helps you to study varied interfaces and true bulk states, which I'm not going to talk about now, and I don't have even a picture because I don't have time for this. And then there is soft X-ray beamline PO4 that shines more in high resolution measurements of momentum microscopy of bands, basically. So what is a momentum microscope? So normal ARPAS we have seen today already a couple of times, which is based on a hemisphere approach. But this is already not so novel approach called momentum microscope. It's been around for like 10 years now, developed or first shown in mines, especially the time of flight version of it. And it utilizes this property of the electrostatic immersive lens in front of the sample, which you can hear in the cutout. And what it does something analogical to an optical lens, that in the backfocal plane of this accelerating lens, a reciprocal image is formed. And then basically what you would like to image the reciprocal image is to project this plane onto your detector. Let me find the cursor here. Yes. Yeah, onto your detector. And we do this through a couple of stages of zoom optics that lets you change the magnification. And probably it's also worth mentioning that here in the projection optics, you can also switch between two modes. One is the K mode, which you see displayed here, and the other one is a well-known P mode, so real space imaging of the sample. And when you combine this time-of-flight momentum microscope with, oh no, it doesn't work. Yes, with a time-resolved detection of your signal using a delay line detector in this case, you can acquire 3D signal in one go. Basically, in this case, it is the position of the detector, which encodes the K coordinate, K parallel coordinate of the signal, and time of flight, which encodes the binding energy. And for instance, here is a model measurement. This data probably could be taken within 5 minutes or so in our lab with an HHG source at 25 eV with a flux of something about 3 times 10 to 11 photons per second. So this then takes only minutes for the whole 3D stack of, for the whole breeder zone or even more, and several EV widths. And yeah, but that's not all that comes out from the sample when you shoot it with light. Ultrasonics. So there is also photons re-emitted, which can be elastically or inelastically scattered. And one would like to analyze that to actually find out what they spend their energy on, the photons. And usually at Synhrotron, this is done using RIXS spectrometers. So the usual way would be to put a diffraction gradient after your sample and analyze this outgoing scattered X-ray light. So basically build a huge spectrometer after your sample. And yeah, the resolution of the spectrometer depends on its size directly, or in some cases, there are attempts to build a clever spectrometers like this one at DESY at PO1, which uses a very specific spherical variable line density gradient, but they have their own downsides. So there is always a search for something better, and one more or less obvious way is like, what if we convert our X-ray signal into something that we can control better, like electrons? And this idea is not very new. It's been around for like 60 years, probably more by now. So what if you shine X-ray light on a sample that you know very well, and then try to know in the intrinsic spectrum of this sample, try to reconstruct the incident spectrum of light. And within last decade or so, there have been quite some advances in this direction, and people also developed methods for numerical deconvolution of spectra, so this all becomes possible now. And people already calculated the probable efficiency of this kind of detection, that you probably will lose some orders of magnitude on converting actually the signal from photons to electrons. But on the other hand, we can use the PIM capabilities of our sample, or at least just collect electrons from a huge solid angle part, and this will increase efficiency back. So in the end, it should be a comparable efficiency to standard spectrometers. And at PO4, the first pilot experiments have been done a little bit more than a year ago, and they have shown promising results in an A-sphere end station, which is a normal ARPIS hemisphere. And so this project got continuation, and so this microscope appeared, which is now the same approach, but inside of a momentum microscope instead of a hemisphere, to further improve the collection efficiency. So what you see here is a converter foil, so called, these are thin films that are illuminated with X-rays on the backside, and photoelectron signal is taken from the front side of this converter foil. So you treat it as a sample, more or less, and you work in PIM mode, so you can actually resolve the real space of this converter foil on your detector. So now you have, with our microscope, you have, again, a three-dimensional signal. X and Y position would encode the angles of incidence. So the K vector actually of your elementary excitation, if you're observing a magnon, for instance. So you could, in an ideal case, see a dispersion already on the converter foil. And the third coordinate is still the time of flight, which gives you the energy loss of your signal. So, and with this size of the converter, we can cover approximately this angular range of the signal. And so we have tested 3 different converter foils because, yeah, they all should be promising. This is, you can see them here: gold, silver, and platinum. So, and in gold, one would use gold for F lines as a kernel function or as your observed spectrum, and see how it is modified when you illuminate it with an unknown spectrum or the spectrum of your interest that you want to study. In case of silver, it is the 3D spectrum, and platinum is the Fermi age. Platinum is very good in this case because it has a very high density of states at the Fermi age, and also within some range, the density of states is more or less flat next to the Fermi level. So the deconvolution should be simple. And so we tested these three, and in this case, the best results we have got with the silver film, because the peaks are a bit narrower than the gold peaks, and also they are spaced a little bit wider apart, which gives us more convenient deconvolution with less noise afterwards. So, and platinum, actually, the deconvolution method is not yet ready for this kind of kernel function. It's still something we need to work on it. And so after deconvolving this result here, we observe a spectrum which actually corresponds to already known measured spectrum of calcium copper oxide. I haven't mentioned the sample, but in this case, it's not extremely important. It's just a test sample. And yeah, the measured energy resolution of this method combined appeared to be slightly worse than 100 milli-eV, which would be probably a state of the art a couple of years ago, but right now on arXiv there is a paper from ESRF with this really taken with this huge spectrometer, which is presented an energy resolution of about 30 milli-eV, I think. So there is still room for improvement. So, and the next steps would be, we're having a beam time really soon, where we will improve our data. The RPS mode of this instrument still needs to be commissioned. So as I said, the plan is to use RPS and RIXS back-to-back to study what actually happens and how actually these phase transitions act on the sample electron structure and collector excitations. So the microscope has been already modified slightly, so it needs also another commissioning. Now it should have more collection efficiency and bring better results, just because deconvolution is really dependent on noise. So having lower noise will also improve energy resolution, hopefully. Yeah, that's basically it. And yeah, another thing, when we have enough statistics, we can try to actually deconvolve different parts of the converters of the converter surface and see whether we can see any dispersion of these magnons that we detected here. And with this, I want to thank you for your attention and ask for your questions.
Thank you very much for an interesting and fascinating talk about your progress in energy resolution and about possibilities which can be done in this material. And next, so do we have time probably for one question? Is there any questions in the So then probably I have a question, more technical one about the spectral range. So you have two end station, one is more softer, another one is more harder, yes?
Correct.
And for softer one, okay, it's 10, there was a problem, so it's around 10 milli-electron volt. Okay, it's very
Yeah, it is not reached on a daily basis or routinely, but it is possible. So routinely, it's probably 50 milli-eV resolution or better, but we also have had recently some troubles when it is sometimes worse. And yeah.
And it's classical PGM, yes?
Yeah. It's a variable.
So you have a variable gratings, yes?
Yes, exactly.
And
Yes.
they are focusing, yes, beam.
Yes, so
You don't have elliptical mirror.
no.
Okay,
The focusing on the slit is done by the grating itself, yes, because of the variable line density.
Okay, so you have, because
focusing
for
on the slit.
Ukrainian beamline, we were considering, because we have range from 500 to, in the best case, to 2 or 3, and we were considering of having possibility of XPS or probably this Pesuma RPS. And it would be nice probably to understand your experience in PGM. Probably it can be option for us as well to have the such a, not such good, but at least down to 100 millieV X-ray energy bandwidth. Okay.
Yes, we can talk about this.
Thank you very much. Any other questions?
I actually, not a question. Thank you for a very informative talk. I just was lost somewhere, not at the middle, but later. But I actually interested to ask more how the system works, but it takes time. Therefore, I didn't understand this geometry actually, and why it should work. But okay, it is a separate story. But it's interesting that it works in your case, at the DAISY, yes, and we could read it and apply if interested, right, for the beam time.
Yes, yes. I really wanted to encourage everyone to apply for beam times here.
Okay, thank you.
P22, where you can study buried interfaces and kept samples, and hopefully, yeah.
These are interesting energy range, which you wanted to some ideas to check about spectral, the distribution of the total spectral weight on over the whole brilliant zone. It would be interesting to see what cooperates for me.
I think for us it might be even more interesting the P04 because like it's high energy ARPAs, but it's like we usually measure with lower energies, and 250 is already a lot, but still can be very interesting.
And then the question, so this is P04. Of course, it's very high resolution, but the variable lens density grating, I forgot how to, but you understand. There is collaboration with Bessie, you got it, or it's your own development?
For this, I cannot tell you. So,
okay.
Of course, I'm here since 2 years. Yes, and of course the beamline has been built. I think they have. No, I cannot help.
No problem, no problem. It was just curiosity. Just considering similar, not similar, but somehow approach. We need to monochromate in the spectral region, and we were looking for options. But thank you very much. It's very interesting. Okay, so then we are going to the next talk, which will be also related to DAISY, but from Ukrainian user of DAISY, which would be the Professor Larisa Homenkova, who would speak about Synhrotron VUV study of luminescent properties in mangan-doped zinc oxide and zirconium oxide ceramics.
Good afternoon. Do you hear me?
Yes, yes.
Good. And did you see my screen?
Yes.
Perfect.
Perfect.
Okay. Today I will speak about, thank you for your introduction, Danylo. So I just will speak today about our recent results, which we got in July this year, using synchrotron facilities in DAISY. We used P66 beamline for photoluminescence at Petra 3. And this is work done with tight collaboration between several researchers from different countries and different cities of Ukraine. So we were doing our samples. Thank you to a team of Daisy of the P66 beamline, who help us a lot for photoluminescence study, and the people from the Nano Center who Arno Jeromin, who help us with microscopy study, and 2 colleagues who help us with infrared spectra and with calculation of DX spectra. So first of all, I would like to acknowledge the support from NEPHEW project, which help us to come to be in DAISY and to participate in these interesting experiments, and all the DAISY office DAISY user office support for kind regarding us in this place. So today I will speak about materials that are combining properties of zinc oxide and zirconium oxide. First of all, why we are going in this direction? First of just to say about few properties of zinc oxide and zirconium oxide. Both materials are wide bandgap materials. Zinc oxide is a good known semiconductor with strong ultraviolet emission and visible emission usually connected with different defects. And it's very often used in photocatalysis, in different sensors, in luminescent ceramics, in transparent coatings, and in some medicine and biological applications. For zirconium oxide, it's more wider band materials, and its band gap is going up to 6.4 eV. And it has good thermal stability, good structural stability, but very low photoluminescence intensity, especially when we excite by usual sources what we use in all our labs, like lasers, ultraviolet lasers, and so on. And zirconium oxide has also good potential application for catalysis. It's usually used for oxygen sensors. It's used in electrolytes, for solid oxide fuel cells, for transparent protective coatings for solar cells, because it's very hard and it's protect from mechanical destroying of the solar cells. It can be used in thermal batteries and a lot of applications. And what is interesting in these composite materials? First of all, they are using for thermal barriers. And they are very considered that they have similar properties with magnesium-doped zirconium oxide that are usually going for thermal barriers. And a lot of people now more concentrated in the application for photoluminescence, or for sensing of the luminescence, or for emission of the luminescence. And zirconium oxide doped with zinc is usually considered in powder-like form. So it's easy to produce. You mix two initial solutions, you produce either zinc oxide covered by zirconium oxide or vice versa, and you have good forms in powders for photocatalysis. In solid-like form, they are less they're less addressed, and there are some announcements about luminescent ceramics and about protective luminescence coatings for windows. Our goal was to get insight in the effect of sintering conditions on the formation of ceramic materials and to monitor the light emitting properties under ultraviolet excitation. Why we go exactly for effect of sintering conditions? It is known that zirconium oxide has a monoclinic structure, and to stabilize tetragonal or cubic structure at room temperature, you need to dope these materials with subvalent impurities. In this case, zinc can go like subvalent substitution of zirconium, and in the temperature range used for ceramic production, we can be faced with two processes: good diffusion of zinc and formation of some stoichiometric solid solution, or we can have two different phases like zinc oxide and zirconium oxide, or if we use high temperature, we can evaporate zinc. So combining this knowledge, we were going to produce our samples, and we use starting powders in their pure form. We bought zirconium oxide and zinc oxide. We use them as they are. We did not use any additional cleaning. We mix them in this work in ratio 2:1. So like produce zirconium to zinc to zirconium, or 4 materials. And we dope with manganese. We would like to achieve some emission. Usually manganese emit very well in the red spectral range. And we use manganese sulfide that to get some amount of manganese inside the ceramics. And the amount of manganese we consider to be between 0.01 atomic percent up to 1 atomic percent. After mixing of the powders, their preparation, drying, we compacted them in some pellets with axial pressure, and we sintered them at different temperatures, starting from 1100 up to 1500 during 3 hours in air. And we have our samples. You can see this in the picture. So we have a set of samples without manganese and with doping with manganese. You see that we have different colors, and sometimes we have some kind of reddish or orange colors, or brown colors, but for some high temperatures you see that we have only white color. So we use different optical characterization techniques and different microscopic characterization, as well as photoluminescent study. So let's go for first, what we can do at home. We did a preliminary investigation of characteristic of our samples with Raman scattering spectroscopy. Just to remind you that if we have zinc oxide, we have specific vibration bands. Usually we have active phonons, and the most intense is E2 high. And it usually appears at 437 reciprocal centimeters. And for zirconium oxide, we have different active Raman modes depending on the crystalline structure of zirconium. The most active bands are for monoclinic zirconium structure. We have less amount of vibrations for tetragonal and very broad spectra for cubic zirconium oxide. And if we will compare the spectra, what we got for some our samples, I will not show for all the samples, it's just only some presenting. They are more or less similar from 1300 degrees Celsius annealing up to 1500 degrees Celsius. But for 1100, we have mixture of these two Raman spectra, zinc oxide and zirconium oxide. And we can say, or we can suppose, that we have no formation of definite solid solution, and we still have in our materials zinc oxide phase and zirconium oxide phase, and maybe some penetration of zinc in zirconium lattice. And for high temperature, we have really very huge contribution of monoclinic phase, but it became to be more and more intense with increasing of the temperature, of sintering temperature, and appearance of this small peak at 750 reciprocal centimeters is the evidence of the existence of this phase in our materials. We have just only very, very small contribution at around 265 reciprocal centimeters that is usually attributed to appearance of tetragonal phase. And what we think that we still have this phase due to penetration of zinc in zirconium oxide. So based on preliminary Raman scattering spectra, we can say that we have samples mostly with monoclinic structure, and some contribution of tetragonal structure cannot be ruled out. But we did also infrared investigation of our samples with Fourier transform infrared reflection spectra. And I show you example of this spectra obtained for the samples annealed at different temperatures. And you can see that if we have zinc ore vibration bands, usually appeared in the range between 300 to 600 reciprocal centimeters, while zirconium oxide vibration bands are appeared in wider range. So it's like covered these bands. You can see that for 1100 degrees Celsius, we have reflection from the surface of our samples, and it looks like we have only like contribution of zinc oxide and just little contribution of zirconium oxide bands. When we increasing temperature of sintering of our ceramics, we can be sure that we see some additional bands belongs to zirconium oxide, and the peak, this minimum position, it's close to 810 to 820 reciprocal centimeters, and this is feature of the appearance of tetragonal phase. All other bands here are features of monoclinic phase, except this one. The Brody peak appeared between 500 and 600 reciprocal centimeters is the feature of appearance of tetragonal phase. So actually, TIR spectra supported the results obtained by Raman spectroscopy, and we can say that our ceramics has monoclinic structure mostly, but there are some formation of tetragonal phase, and formation of solid state solution starts at 1300 degrees Celsius. So to see what we have in our samples, we just were going for scanning electron microscopy to understand what we have in samples. You can see that from if we increase in temperature of sintering, we see that we have increasing the grain sizes and they become larger and larger, and we have good sintering. But we still have, even at high temperature, we still have porosity in our samples. And when we increase in manganese content, I would not say that it will favor sintering of the samples very much, but the ceramics became to be more and more dense. And if to go closely, to see closely, we see that for ceramics sintering at 1100 degrees Celsius, they are combined, they are first of all porous, and combined from very, very small particles sintered each other. And manganese content probably does not give a lot of effect. When we increase in when we increase in sintering temperature, we have really huge growth of the grains. And besides the big grains, we have small particles here. And if you have a look on this image, it looks like that these particles appear due to evaporation of some substances and their recondensation on the surface of the samples. And for 1500 degrees C annealing, we see that we have really very big grains. This is about like between 5 micron up to this is about 6 micron grains, and they became to be well sintered. So we want to see what we have inside our ceramics. So we just clip our surface, our samples, and we took images from the cleft surface. So it's not like preparation of full cross-section observation. This is just on the cleft surface. You see that all the ceramics sintered at low temperature, they are really very porous. There are a lot of pores inside and not so well sintered grains. With increasing of the temperature, you see that we have bigger and bigger sizes of the grains, good sintering, good crystallization, but you see here some kind of free grow of the grains. This means that we have some large pores in our materials, and we have this is free growth of the grains inside. So just to conclude about electron microscopy observation, the grain morphology and porosity vary with sintering temperature. The higher the temperature, the larger the grains, and there are the porosity, and porosity is observable. For zinc oxide, we can suppose that zinc can act as sintering object, and it can affect the grain growth. But what we can say that when we sintered our ceramics, we use probably quite high heating rate for our furnace, and probably the porosity is caused by some kind of evaporation of zinc at higher temperature, like between 13 and 1500 degrees Celsius. And probably this can be the so fast heating can be the reason of appearance of the porosity. But what about chemical composition of our materials? So we took plan view of our ceramic surface and we try to understand where we are. So if you have a look on the contribution of elements here, you see carbon. Carbon was used to produce a very thin film, about 10 nanometers, just to avoid any charging of the zirconium oxide surface, because this is dielectric, it's charged a lot, and usually it does not allow to get good results. So contribution of carbon is coming from the covering film. Then we have a ratio between zinc and zirconium. This is in weighted percent. And you see that for 1100 degrees Celsius, we still have more or less similar contribution between these two elements, similar ratio between these two elements. But just we jump for 13 degrees Celsius, 1300 degrees Celsius, you see that we have a losing of zinc over all the samples. And the more manganese content, we lost more and more zinc. So we can say that increasing of annealing of sintering temperature results in some zinc evaporation. But what we can say that if we have a look on some tiny sinks here, the small, very small particles are zinc enriched. And the largest particles or grains has more zirconium and less zinc. And unfortunately, we cannot detect manganese content because it's below limit of the detection. But what we discovered that if we look on the bottom surface of our ceramic, so this is the surface what was attached to the load in which we did sintering of the samples. We saw that we have penetration of aluminum and silicon in our materials for all the samples, whatever the manganese content. And we think that there is some interaction during sintering treatment at so high temperatures, and we have contribution of these elements. But the comparison with contribution of zinc, it's still quite high. So it does mean that if we have no free surface, we hamper possibility for zinc to be evaporated, and it's still inside the grains. And finally, if we had a look on the these grains in tiny sinks, we see also some zinc appeared in small particles, but there are zinc staying close to the grain boundaries or at grain boundaries. So there are some grains like here, they stay fully with zinc. So this means that when we doing our sintering our ceramics, there are several factors which will affect their optical properties. But anyway, there is a question, where is our manganese? We used usual ultraviolet visible optical absorption spectroscopy to understand if we have manganese inside our ceramics. And you can see here on the left image that for these absorbance spectra, you see specific bands as I mark to band H of zinc oxide, and this is another one increasing in intensity. This is belongs to band H of zirconium oxide. And when we increasing manganese content, we see that we have increasing in intensity of the band between 450 nanometers up to 700 nanometers here. And we have another intensity increase, and this can be due to formation of additional oxygen vacancies in zirconium oxide phase due to penetration of subvalent ions. This can be either both manganese and zinc, but as we see in zinc oxide, zinc is a bit evaporated. And how to check the effect of sintering temperature? Up to 1100 degrees Celsius, we have abrupt H belongs to zinc oxide, and here abrupt for zirconium. So this is like two-phase system. Then we have penetration of manganese. There is band here, and appearance of this is exciton from zinc oxide. So we have two-phase system also with additional increasing in band gap of zirconium. And at high temperature, we have really decreasing in contribution of zinc oxide, and we have enough contribution. We still have contribution of manganese, and we still have contribution of zirconium. So we can say that using optical absorption spectroscopy, we can check whether we have sintered ceramic or we have two-phase system. And manganese appeared as separate band in our materials, which can contribute in optical absorption. And why we used we used also photoluminescence investigation. We performed it at home using blue laser with 410 nanometers excitation, and we did see the real manganese emission close to this. It's close to the red emission band, but we decided to do investigation using ultraviolet excitation because we could not separate contribution of even manganese in zirconium oxide or contribution of zinc oxide or different phases. And if you can have a look here, first of all, we studied undoped ceramics. So for excitation from 120 to 230, we saw two specific bands. One is with very sharp peaks, and this belongs to zinc oxide excitonic emission band. And we have one green band, quite narrow here, with a maximum in vicinity of 520 nanometers. And if we compare exactly this emission spectra and this emission spectra with those what we observe in pure zirconium oxide with the same monoclinic structure, you see this is green emission appeared in pure zirconium oxide. So for ultraviolet excitation below 230 nanometers, we have two bands, one from zinc oxide and another green band. This is from zirconium oxide. But when we increase excitation wavelengths, we exactly see the contribution of green emission wide or broad band, and spectrum looks like this green shown green line, and you see that this emission is excited by the wavelengths close to 300 nanometers. So in this case, what we can say is that we have using this ultraviolet excitation, we can distinguish what emission we have in our materials just by variation of the excitation light wavelengths. Even for zirconium oxide, for pure zirconium oxide, variation between 160 to 200 and 240 nanometers change spectrum very much. So we know that band excited by 240 nanometers, it's around 520 nanometers with maximum, and it belongs to zirconium oxide. But broadband, like here, belongs to zinc oxide. Usually this band was connected with different defects, but some complexes of defects, for instance, like complex with zinc interstitials or some oxygen vacancies, this is a debatable nature up to now, but anyway, if we have some zinc interstitials in our materials, we can say that this is really zinc oxide band. And if to have a look on effect of manganese doping, we check first of all for manganese doped zirconium oxide. Appearance of manganese was checked by electronic paramagnetic resonance spectra. So we see very sharp peaks, 6 lines from manganese 4+, and this is broad lines belongs to manganese 2+, which stay in our material. And if have a look on the photoluminescent spectra, we also have specific band close to 300 nanometers excited by the ultraviolet light up to 230 nanometers, and then green emission like close to 500 nanometers. So this band a bit shifted in comparison with what I showed you before. But when we increase sintering temperature, we exactly got the same emission, and we have emission from 300 to 400 nanometers excited by light from 120 nanometers up to 230 nanometers. And then we have excitation for larger wavelengths, and we see that we have green band less, okay, let's
Sorry,
say, more
I'm
narrow.
sorry to interrupt, but I think we're running really behind the schedule, and Danylo cannot turn on his camera right now. Oh, he can actually.
Okay, I nearly finish.
Thank you, thank you.
Yeah. So, and just to compare our samples with solid solutions, you can see that when we have doping with manganese, we still have contribution from zinc oxide, and we have contribution from narrow bands depending on the excitation wavelengths. But what is interesting, when we increase in manganese content, we see the new band appeared here. It's close to orange range, and we saw the reabsorption of some lines, and this can be due to manganese absorption. So this emission can be reabsorbed by manganese ions. But for this, we need a bit more study. So it's just to conclude that manganese incorporation allowed to get another emission, more broad, but with the concentration of manganese, this emission can be reabsorbed. Just to say you, this is really very fresh result, and we would like to continue this investigation to go deeply inside, and we would like to see if some another defects can contribute in this emission. So just to conclude, I would like to show you that for some specific materials, it's necessary, especially wide bandgap materials, we need to use specific facilities, and the synchrotron facilities in DAISY, it was very perfect for us to understand where we are. I just want to say that usually if we have possibility to analyze excitonic emission maps, we can manage with the pathway for excitation of different defects or different emission center. But I would like to say that we need a bit more investigation to go deeply in the excitation luminescence mechanism. Once again, I would like to acknowledge DAISY office, user office for our help, Nephew project for our help, and all our colleagues who helped us to continue this research. Thank you for your attention.
Thank you very much for the talk. Unfortunately, as was mentioned, we probably don't have much time for questions because, but I think if there will be any, we can have very time for one short question, but in the case if there will be any questions in future, please contact organizing committee and we will send them to the speaker. Thank you very much for your talk, and next talk will and the last talk of this session, and it will be actually the single talk which will be done on site at Taras Shevchenko National University of Kyiv, and it will be done by Ukrainian researcher Mr. Ihor Sukhenko, and he was recently a user at SOLARIS Synhrotron, and it will be probably about results, and it's the title you can read that it's copper site occupancy and valence in lead apatite measured by X-ray absorption spectroscopy at the Astra beamline at SOLARIS.
Can you hear me online?
Yes, amazing.
Okay. Hello, dear colleagues. So tomorrow, not tomorrow, today, I'm going to tell you about the peculiarities of the incorporation of copper into the lattice of lead apatites. And first of all,
does it work? Okay, supposed to.
Sorry, technical issues.
I'm sorry for that.
Okay, it's fine.
Does it work?
Yeah. Thank you. First of all, what is an apatite? Actually, this is the structural class of materials with its basic structure you can see on the screen. It consists of bricks of tetrahedral structural blocks like phosphorus O4 or vanadium O4, and the metallic scaffold of like lead or calcium or other types of metals. And one of the peculiarities of this family of materials is their ability to host a wide range of so-called isomorphic substitutions, which means that you can dope or substitute different atoms in a large degree of stoichiometric coefficient without ruining the structure. So the motivation for our this current experiment was the proposed non-trivial electronic properties of some of the members of this class, and notably copper-doped lead apatites. It was theoretically it was predicted that they should host strongly correlated flat bands with symmetry-protected Weyl crossings and non-trivial quantum geometry and magnetism, and at some point even superconductivity was postulated and whatnot. But this up to till today it was not realized experimentally. So our idea was to check maybe it was a structural. There was a structural reason for that. Maybe there was an electronic reason for that, and we synthesized a whole bunch of different apatite samples doped with copper that contained vanadium, phosphorus as those PO4 tetrahedra, as well as hydroxyl, fluorine, chlorine, bromine, and iodine as the anions, anion halogen ions. Right. So why the copper site occupancy? Why it matters? Actually, in the apatite crystal structure, there are two inequivalent positions that copper atom may occupy. In the literature, those are called first and second position. So I will refer to them as copper 1 and copper 2. And basically, the calculation of electronic structure shows that it's only when copper is in the first position, only then the compound is going to be metallic, and only then those stipulated electronic features may be realized. Otherwise, it's just going to be a superconductor, interesting or not, we don't know, but not as interesting, at least. Previously, those ratios of site occupancy were estimated through DFT calculations and total energy estimates. So we basically compared which configuration had lower energy, and for most of them, it turned out that the first position, which we actually would like to see, was preferential, but the difference was really small, smaller than the room temperature energy scale. Then we applied for beam time on SOLARIS for the X-ray absorption spectroscopy beam line, which was Astra, and Astra is a perfect beam line for that. So yeah, I'll skip the theory part because we don't have any time. So yeah, and our request was granted for, we got the beam time actually this October. It was when we went to measure the spectra. And briefly about the method. So actually you have your sample and an incoming X-ray beam is hitting the sample. The X-ray photons are getting absorbed by the electronic shell of the atom in question, and then you see the absorption spectrum, and the absorption spectrum has two major parts. So first part is so-called XANES, which is X-ray absorption near edge structure, and the second longer part is called EXAFS, which is extended X-ray absorption fine structure. And the XANES part, from that you can discern chemical valence state, mostly some structural information as well, but mostly it's used as an indicator of the valence and the electronic state. while exahash range is more about structural information. So how it works is when the X-ray photon gets absorbed, an electron, a core electron gets excited, and it gets expelled from the atom, and during this process, an electron wave propagates throughout the lattice, and it interferes with itself basically. And this interference pattern, it is highly modulated by the lattice of the sample. So those modulations are what are causing those oscillations that you can see on the green part of the picture. And you can then decipher them and get the structural information from them. And this is basically how we are going to use where our copper atom sits. Yeah, that's it. So, and then, yeah, several photos of the experiment itself. So this is the Astra beam line. This is the I think it's considered 10 to X-ray from 2 to 15 kilo electron volts mostly. We were mostly recording the Kh excitation of copper, which is the 9,000 electron volts. Yeah, so these are our samples. We had 10 samples in total. So we had a small group of 3 people at the site, and the whole beam time was just 48 hours, but we managed to record everything we planned. So there is that. And this is the control station for the Astra beam line. Yeah, so right. Unfortunately, as these results are very, very fresh, the spectra were recorded just, well, basically exactly a month ago. We didn't really have the time to make all of the rigorous analysis that it requires, but I'll share with you some preliminary, really preliminary data we have. So about the Xane's age, those kind of pre-spike first part of the absorption spectrum I told you about, that mostly tells us about the valence. So yeah, naturally we expected copper to be in 2+ valence state, because this is the default state for a metal to be in the apatite layers. But in fact, in the literature, there were some controversies even about that. So, well, some people stipulated that copper might even be at some interstitial sites in the neutral state and so on. But here we observed that indeed in all samples we checked, the structure of the Xane's region was mostly compatible with the 2+ excitation states. And if one compares it with the standard samples like copper oxide, the features and the shape of the curve basically repeats the standard curve for the copper 2+ state. And what's also interesting that you can actually simulate the Xane's age in density functional theory, which kind of sounds surprising, because yeah, this is the excitation or the excited state, and the DFT is a ground state theory. But the trick is that you need to simulate to the potential with a hole in the core level, and then you do what's called a GPO calculation, and then you can simulate this curve. So basically, the theoretical curve, you can see here, obviously all the features are very exaggerated in the experiment. They're not as sharp, but the idea is that you do see the features, right? And if your Xane's was of the different excitation state, of different valence, you won't see those. So basically, it's a
in the DFT simulation, you need to just demonstrate the presence of certain features, not necessarily their amplitude or position in energy. Just your shapes have to be more or less similar, right? And about the exhaust part, the structural information on the site occupancy I told you about. So basically, these are preliminary fits of a certain structural model, idealistic model that we have for those materials. And it was fitted to the experimental data. Actually, at this point, what I show you here is that which model fits the experimental data best, the one with the copper at first site or the second site. So here in green squares, you can see those samples that with which we were able to fit the spectrum with the first site model. And the red one is that for which the second site works best. And the yellow ones are those for which only the combination of two models work for the fitting. Right, so basically the initial total energy DFT estimates were more or less confirmed because we did indeed estimate that most of the samples would prefer the first position as highlighted in green. We also estimated the contrary to be the case for iodine samples, the last one, two of the last ones on the right. And we also estimated a very small difference in the occupancy for the hydroxyl samples. So it more or less lines up with theoretical estimate, except for vanadium iodine sample. But again, these results are very preliminary at this point because they're very fresh. So the work is still ongoing to develop a more quantitative statistical pipeline for really making a quantitative estimate of the ratio of those site occupancy. And with this, I think my brief report comes to an end. Basically, in conclusion, I should say that most of the samples that were measured were synthesized for the first time, especially the vanidates. I mean, for the first time, this combination with copper and all those halogens and so on. We obtained good quality data at the Astra beam line with the, well, in the reciprocal space up to 12 reverse angstrom, which is considered more or less good for exhausts, given the relatively small percentage of copper, like by mass and by stoichiometry overall. Also, successful incorporation of copper, what I mean by that is that copper was, by all accounts, indeed replacing lead in the lattice and not ending up in some chaotic clusters or interstitials and so on. Copper 2+ valence was confirmed, more or less, and the initial estimates of the site reference, as I showed you on the previous slides. Right, so I acknowledge the support for NRFU for the overall project, and what's important, the support of nephews for the actually for our travel and accommodation of our group for this experiment, and as well for my training at the ERS program with the different experiment in spring. The one that were shown, the results of which were shown by Volodymyr Bezguba. I was also there thanks to ERS program. Thank you for attention. I would be glad to answer your questions.
Okay.
Thank you very much for your amazing talk, and I think that is the best example of all our workshops and probably the best results. because you had talked like during the previous USyNC workshop about and there was possibility to do a synchrotron research on your sample, and finally, probably thanks to partially nephew program and Ukrainian Synchrotron community, you managed to have such experiment as SOLARIS, and it's very wonderful, which I can say. So I have a question. It's more technical question. So you were looking only to the copper KH, I guess, yeah?
Yes.
Beta, I guess, or doesn't matter. But did you consider other? So the story was about this copper states, but have you any limitation in the spectral range of Astra, or did you? Did you feel that it's necessary to have some harder X-ray wavelengths to investigate other elements of your compound, or
Well,
initial idea to study only copper H?
good question. Actually, we managed to also record vanadium spectra for KH of vanadium as well, because we had some extra time during the very end of the beam time. So we also measured vanadium KH as well. I just didn't show those spectra because because there weren't that much time and so on. Technically, the switching between the edges is realized by changing the crystal that monochromatizes the beam and actually sets the window for selecting the energy range, and it is done by the beamline scientists only.
So it's I guess manual, because vanadium H is around 5.4 kilo-electron volt.
Yeah, exactly, yes, something like that. And we even had to do it in light vacuum, like in a little bit of vacuum, as opposed to copper, which was done on atmosphere. And as for a more highly energetic edges, good question. I think for our particular experiment, I don't really see how it would help, because here we really focus on copper, and copper was like we needed to know its immediate surrounding and its electronic state. So here it wasn't as crucial, I would say. Well,
okay, and another very like technical question. So at Astra beamline, if I understand correctly, the beam size is quite big. It's I don't remember exactly, but there's definitely more than few millimeters. And was it advantage or disadvantage for you? What is your sample size, and do you prefer to have smaller beam size, or this was the ideal one in terms of experiment and signal over noise data results?
I see. Well, actually, if I remember well from the conversation with the beamline scientists, their beam size is in hundreds of micrometers, and it's less than a millimeter. But anyway,
yeah,
not much less. Right. For our experiment, it wasn't a hurdle because we had our samples were polycrystalline pellets, and the size of the pellet is half a centimeter, and you have those powders mixed in those pellets, and I mean the wide beam is not a problem for this sort of experiment, but I see how, for example, if we had some sort of monocrystalline samples, which we are actually planning to grow from those powders, right? At some point, there it will probably hurt, but because you cannot get them to be that large. Usually it's but here it wasn't a problem.
Okay, perfect, amazing. Thank you very much for a wonderful talk. Any other questions?
To organizers for the invitation and for the setting up of this beautiful workshop.
Do we have any other questions from audience? Looks like there is no question, but we hope that next Ukrainian Synchrotron workshop there will be a new result from you. It's very promising. And I think we are about to close our Ukrainian Synchrotron workshop, and I would like to invite Alexander Kordyuk for a few final words. And probably after Marcin as well.
Yeah, I see if Marcin is here. Actually, it was it impressed me that actually I want again to thank Danylo for organization. It was rather, let's say, coherent, although the first part for me was incoherent due to external disturbances, but actually it was quite nice, and it will be especially nice if we will be able to publish this recording if they succeeded with if this Zoom is succeeded with recording, then it would be very instructive. I thank all the speakers. It is very useful for us, for Ukraine. It's your support and your participation in this workshop to develop our research in this synchrotron-based research in Ukraine. So just want to thank all the participants again and ask also someone else, Marcin, it's nice that you are still here, your impression about microphone is not working somehow.
Probably.
Now it is, yeah.
It still doesn't work?
It still doesn't work, I guess.
That was Danylo voice. Okay.
Can we just switch off somewhere here on her?
Can you hear me?
Yes.
Okay. So I'm sorry I wasn't present all the time, but from what I heard, it was very interesting, and I was happy to see that there are results from Solaris, but also from DESI. It's very active, so it really motivates us also to hard work on MAVKA construction. That we see that there are more and more users in Ukraine. We're very happy about that, and I wish you all the best, and hope to see you all or more people during the next meeting soon. Thank you.
So thank you again to everyone, most of all to students who were able to survive all workshop at the Code Faculty building. And we are ending our first day of the Photonics and Optics in Symposium, and we end in our workshop, and this time we will announce the date much earlier for next year, and it will be around the November if nothing would happen. And thank you very much again, and if participants of workshop are interested, you're always welcome to join other sessions during the next days, especially tomorrow and the day after. Thank you very much.
Okay. Thank you. Bye-bye.
Thank you. Bye. Stay safe.
Thank you, everyone. Goodbye.